Appendix I of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melissa. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix I, the Stock Printer. In these modern days, when the stock ticker is in universal use, one seldom, if ever, hears the name of Edison coupled with a little instrument whose chatterings have such tremendous import to the whole world. It is of much interest, however, to remember the fact that it was by reason of his notable work in connection with this device that he first became known as an inventor. Indeed, it was through the intrinsic merits of his improvements in stock tickers that he made his real entree into commercial life. The idea of the ticker did not originate with Edison, as we have already seen in Chapter VII of the preceding narrative, but at the time of his employment with the Western Union in Boston in 1868, the crudities of the early forms made an impression on his practical mind, and he got out an improved instrument of his own, which he introduced in Boston through the aid of a professional promoter. Edison, then only 21, had less business experience than the promoter, through whose manipulation he soon lost his financial interest in this early ticker enterprise. The narrative tells of his coming to New York in 1869, and immediately plunging into the business of gold and stock reporting. It was at this period that his real work on stock printers commenced, first individually and later as a co-worker with F. L. Pope. This inventive period extended over a number of years, during which time he took out 46 patents on stock printing instruments and devices, 2 of such patents being issued to Edison and Pope as joint inventors. These various inventions were mostly in the line of development of the art, as it progressed during these early years, but out of it all came the Edison Universal Printer, which entered into very extensive use, and which is still used throughout the United States and in some foreign countries to a considerable extent at this very day. Edison's inventive work on stock printers has left its mark upon the art as it exists at the present time. In his earlier work, he directed his attention to the employment of a single circuit system, in which only one wire was required, the 2 operations of setting the type wheels and of printing being controlled by separate electromagnets, which were actuated through polarized relays, as occasion required, one polarity energizing the electromagnet controlling the type wheels, and the opposite polarity energizing the electromagnet controlling the printing. Later on, however, he changed over to a 2-wire circuit, such as shown in Figure 2 of this article, in connection with the universal stock printer. In the earliest days of the stock printer, Edison realized the vital commercial importance of having all instruments recording precisely alike at the same moment, and it was he who first devised, in 1869, the unison stop, by means of which all connected instruments could at any moment be brought to zero from the central transmitting station, and thus be made to work in correspondence with the central instrument and with one another. He also originated the idea of using only one inking pad and shifting it from side to side to ink the type wheels. It was also in Edison's stock printer that the principle of shifting type wheels was first employed. Hence it will be seen that, as in many other arts, he made a lasting impression in this one by the intrinsic merits of the improvements resulting from his work therein. We shall not attempt to digest the 46 patents above named, nor to follow Edison through the progressive steps which led to the completion of his universal printer, but shall simply present a sketch of the instrument itself, and follow with a very brief and general explanation of its theory. The Edison Universal Printer, as it virtually appears in practice, is illustrated in Figure 1 below, from which it will be seen that the most prominent parts are the 2 type wheels, the inking pad, and the paper tape feeding from the reel, all appropriately placed in a substantial framework. The electromagnets and other actuating mechanism cannot be seen plainly in this figure, but are produced diagrammatically in Figure 2, and somewhat enlarged for convenience of explanation. It will be seen that there are 2 electromagnets, one of which, Tm, is known as the type magnet, and the other, Pm, as the press magnet, the former having to do with the operation of the type wheels, and the latter with the pressing of the paper tape against them. As will be seen from the diagram, the armature A of the type magnet has an extension arm, on the end of which is an escarpment engaging with a toothed wheel placed at the extremity of the shaft carrying the type wheels. This extension arm is pivoted at B. Hence, as the armature is alternately attracted when current passes around its electromagnet and drawn up by the spring on cessation of current, it moves up and down, thus actuating the escarpment and causing a rotation of the toothed wheel in the direction of the arrow. This, in turn, brings any desired letters or figures on the type wheels to a central point, where they may be impressed upon the paper tape. One type wheel carries letters, and the other one figures. These two wheels are mounted rigidly on a sleeve carried by the wheel shaft. As it is desired to print from only one type wheel at a time, it becomes necessary to shift them back and forth from time to time, in order to bring the desired characters in line with the paper tape. This is accomplished through the movements of a 3-arm rocking lever attached to the wheel sleeve at the end of the shaft. This lever is actuated through the agency of 2 small pins carried by an arm projecting from the press lever, PL. As the latter moves up and down, the pins play upon the underside of the lower arm of the rocking lever, thus canting it and pushing the type wheels to the right or left, as the case may be. The operation of shifting the type wheels will be given further on. The press lever is actuated by the press magnet. From the diagram it will be seen that the armature of the latter has a long pivoted extension arm, or platen, trough-like in shape, in which the paper tape runs. It has already been noted that the object of the press lever is to press this tape against that character of the type wheel centrally located above it at the moment. It will at once be perceived that this action takes place when current flows through the electromagnet and its armature is attracted downward, the platen again dropping away from the type wheel as the armature is released upon cessation of current. The paper feed is shown at the end of the press lever and consists of a push dog, or pawl, which operates to urge the paper forward as the press lever descends. The worm gear, which appears in the diagram on the shaft, near the toothed wheel, forms part of the unison stop above referred to, but this device is not shown in full in order to avoid unnecessary complications of the drawing. At the right-hand side of the diagram, Figure 2, is shown a portion of the transmitting apparatus at a central office. Generally speaking, this consists of a motor-driven cylinder having metallic pins placed at intervals and arranged spirally around its periphery. These pins correspond in number to the characters on the type wheels. A keyboard, not shown, is arranged above the cylinder, having keys lettered and numbered corresponding to the letters and figures on the type wheels. Upon depressing any one of these keys, the motion of the cylinder is arrested when one of its pins is caught and held by the depressed key. When the key is released, the cylinder continues in motion. Hence, it is evident that the revolution of the cylinder may be interrupted as often as desired by manipulation of the various keys in transmitting the letters and figures which are to be recorded by the printing instrument. The method of transmission will presently appear. In the sketch, Figure 2, there will be seen, mounted upon the cylinder shaft, 2 wheels made up of metallic segments insulated from each other, and upon the hubs of these wheels are 2 brushes which connect with the main battery. Resting upon the periphery of these 2 segmental wheels, there are 2 brushes to which are connected the wires which carry the battery current to the type magnet and press magnet respectively, as the brushes make circuit by coming in contact with the metallic segments. It will be remembered that upon the cylinder there are as many pins as there are characters on the type wheels of the ticker, and one of the segmental wheels, W, has a like number of metallic segments, while upon the other wheel, W', there are only 1/2 that number. The wheel W controls the supply of current to the press magnet, and the wheel W' to the type magnet. The type magnet advances the letter and figure wheels 1 step when the magnet is energized, and a succeeding step when the circuit is broken. Hence, the metallic contact surfaces On wheel prime are, as stated, only half as many as on the wheel W, which controls the press magnet. It should be borne in mind, however, that the contact surfaces and insulated surfaces on wheel W prime are together equal in number to the characters on the type wheels, but the retractile spring of Tm does half the work of operating the escarpment. On the other hand, the wheel W has the full number of contact surfaces because it must provide for the operative closure of the press magnet circuit whether the brush B prime is in engagement with a metallic segment or an insulated segment of the wheel W prime. As the cylinder revolves, the wheels are carried around with its shaft and current impulses flow through the wires to the magnets as the brushes make contact with the metallic segments of these wheels. One example will be sufficient to convey to the reader an idea of the operation of the apparatus. Assuming, for instance, that it is desired to send out the letters AM to the printer, let us suppose that the pin corresponding to the letter A is at one end of the cylinder and near the upper part of its periphery, and that the letter M is about the center of the cylinder and near the lower part of its periphery. The operator of the keyboard would depress the letter A, whereupon the cylinder would in its revolution bring the first named pin against the key. During the rotation of the cylinder, a current would pass through wheel W prime and actuate Tm, drawing down the armature and operating the escarpment, which would bring the type wheel to a point where the letter A would be central as regards the paper tape. When the cylinder came to rest, current would flow through the brush of wheel W to Pm, and its armature would be attracted, causing the platen to be lifted and thus bringing the paper tape in contact with the type wheel and printing the letter A. The operator next sends the letter M by depressing the appropriate key. On account of the position of the corresponding pin, the cylinder would make nearly half a revolution before bringing the pin to the key. During this half revolution, the segmental wheels have also been turning, and the brushes have transmitted a number of current impulses to Tm, which have caused it to operate the escarpment a corresponding number of times, thus turning the type wheels around to the letter M. When the cylinder stops, current once more goes to the press magnet, and the operation of lifting and printing is repeated. As a matter of fact, current flows over both circuits as the cylinder is rotated, but the press magnet is purposely made to be comparatively sluggish, and the narrowness of the segments on wheel W tend to diminish the flow of current in the press circuit until the cylinder comes to rest, when the current continuously flows over that circuit without interruption and fully energizes the press magnet. The shifting of the type wheels is brought about as follows. On the keyboard of the transmitter, there are two characters known as dots, namely the letter dot and the figure dot. If the operator presses one of these dot keys, it is engaged by an appropriate pin on the revolving cylinder. Meanwhile, the type wheels are rotating, carrying with them the rocking lever, and current is pulsating over both circuits. When the type wheels have arrived at the proper point, the rocking lever has been carried to a position where its lower arm is directly over one of the pins on the arm extending from the platen to the press lever. The cylinder stops, and current operates the sluggish press magnet, causing its armature to be attracted, thus lifting the platen and its projecting arm. As the arm lifts upward, the pin moves along the underside of the lower arm of the rocking lever, thus causing it to cant and shift the type wheels to the right or left as desired. The principles of operation of this apparatus have been confined to a very brief and general description, but it is believed to be sufficient for the scope of this article. Note: the illustrations in this article are reproduced from American Telegraphy and Encyclopedia of the Telegraph by William Mavor, Jr., by permission of Mavor Publishing Company, New York. End of Appendix I.
Appendix II. The Quadruplex and Phonoplex. Edison, His Life and Inventions. This is a LibriVox recording, All LibriVox recordings are in the public domain. For more information or to volunteer, visit LibriVox.org. Recording by Anna Maria Viola. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix II. The Quadruplex and Phonoplex. Edison's work in stock printers and telegraphy had marked him as a rising man in the electrical art of the period, but his invention of quadruplex telegraphy in 1874 was what brought him very prominently before the notice of the public. Duplex telegraphy, or the sending of two separate messages in opposite directions at the same time over one line, was known and practiced previous to this time, but quadruplex telegraphy, or the simultaneous sending of four separate messages, two in each direction over a single line, had not been successfully accomplished, although it had been the subject of many an inventor's dream and the object of anxious efforts for many long years. In the early part of 1873, and for some time afterward, the system invented by Joseph Stearns was the duplex in practical use. In April of that year, however, Edison took up the study of the subject and filed two applications for patents. One of these applications embraced an invention by which two messages could be sent not only duplex, or in opposite directions as above explained, but could also be sent diplex, that is to say, in one direction simultaneously as separate and distinct messages over the one line. Thus there was introduced a new feature into the art of multiplex telegraphy, for whereas duplexing, accomplished by varying the strength of the current, permitted messages to be sent simultaneously from opposite stations, diplexing, achieved by also varying the direction of the current, permitted the simultaneous transmission of two messages from the same station and their separate reception at the distant station. The quadruplex was the tempting goal toward which Edison now constantly turned, and after more than a year's strenuous work he filed a number of applications for patents in the late summer of 1874. Among them was one which issued some years afterward as patent number 480,567, covering his well-known quadruplex. He had improved his own diplex, combined it with one of the Stearns duplex, and thereby produced a system by means of which four messages could be sent over a single line at the same time, two in each direction. As the reader will probably be interested to learn something of the theoretical principles of this fascinating invention, we shall endeavor to offer a brief and condensed explanation thereof, with as little technicality as the subject will permit. This explanation will necessarily be of somewhat elementary character for the benefit of the lay reader, whose indulgence is asked for an occasional reiteration introduced for the sake of clearness of comprehension, while the apparatus and the circuits are for the sake seemingly very intricate. The principles are really quite simple, and the difficulty of comprehension is more apparent than real if the underlying phenomena are studied attentively. At the root of all systems of telegraphy, including multiplex systems, there lies the single basic principle upon which their performance depends, namely, the obtaining of a slight mechanical movement at the more or less distant end of a telegraph line. This is accompanied through the utilization of the phenomena of electromagnetism. These phenomena are easy of comprehension and demonstration. If a rod of soft iron be wound around with a number of turns of insulated wire, and a current of electricity be sent through the wire, the rod will be instantly magnetized and will remain a magnet as long as the current flows. But when the current is cut off, the magnetic effect instantly ceases. This device is known as an electromagnet, and the charging and discharging of such a magnet may, of course, be repeated indefinitely, inasmuch a magnet that has the power of attracting to itself pieces of iron or steel, the basic importance of an electromagnet in telegraphy will be at once apparent when we consider the sounder, whose clicks are familiar to every ear. This instrument consists essentially of an electromagnet of horseshoe form, with its two poles close together and with its armature, a bar of iron, maintained in close proximity to the poles, but kept normally in a retracted position by a spring. When the distant operator presses down his key, the circuit is closed and a current passes along the line and through the generally two coils of the electromagnet, thus magnetizing the iron core. Its attractive power draws the armature toward the poles. When the operator releases the pressure on his key, the circuit is broken, current does not flow, the magnetic effect ceases, and the armature is drawn back by its spring. These movements give rise to the clicking sounds which represent the dots and dashes of the Morse or other alphabet as transmitted by the operator. Similar movements produced in like manner are availed of in another instrument known as the relay, whose office is to act practically as an automatic transmitter key, repeating the messages received in its coils and sending them on to the next section of the line, equipped with its own battery, or, when the message is intended for its own station, sending the message to an adjacent sounder included in a local battery circuit. With a simple circuit, therefore, between two stations and where an intermediate battery is not necessary, a relay is not used. Passing on to the consideration of another phase of the phenomena of electromagnetism, the reader's attention is called to Figure 1, in which will be seen on the left a simple form of electromagnet consisting of a bar of soft iron wound around with insulated wire through which a current is flowing from a battery. The arrows indicate the direction of flow. All magnets have two poles, north and south. A permanent magnet made of steel, which as distinguished from soft iron retains its magnetism for long periods, is so called because it's permanently magnetized, and its polarity remains fixed. In an electromagnet, the magnetism exists only as long as the current is flowing through the wire, and the polarity of the soft iron bar is determined by the direction of flow of current around it for the time being. If the direction is reversed, the polarity will also be reversed. Assuming, for instance, the bar to be end-on toward the observer, that end will be a south pole if the current is flowing from left to right, clockwise around the bar, or a north pole if flowing in the other direction, as illustrated at the right of the figure. It is immaterial which way wire is wound around the bar, the determining factor of polarity being the direction of the current. It will be clear, therefore, that if two equal currents be passed around a bar in opposite directions, Figure 3, they will tend to produce exactly opposite polarities and thus neutralize each other. Hence the bar would remain non-magnetic. As the path to the quadruplex passes through the duplex, let us consider the Stern's system, after noting one other principle, namely, that if more than one path is presented in which an electric current may complete its circuit, it divides in proportion to the resistance of each path. Hence, if we connect one pole of a battery with the earth, and from the other pole run to the earth two wires of equal resistance as illustrated in Figure 2, equal currents will traverse the wires. The above principles were employed in the Stern's differential duplex system in the following manner. Referring to Figure 3, suppose a wire, A, is led from a battery around a bar of soft iron from left to right, and another wire of equal resistance and equal number of turns, B, around from right to left. The flow of current will cause two equal opposing actions to be set up in the bar. One will exactly offset the other, and no magnetic effect will be produced. A relay thus wound is known as a differential relay, more generally called a neutral relay. The non-technical reader may wonder what use can possibly be made of an apparently non-operative piece of apparatus. It must be borne in mind, however, in considering a duplex system, that a differential relay is used at each end of the line and forms part of the circuit, and that while each relay must be absolutely unresponsive to the signals sent out from its home office, it must respond to signals transmitted by a distant office. Hence the next figure, 4, with its accompanying explanation, will probably make the matter clear. If another battery, D, be introduced at the distant end of the wire A, the differential or neutral relay becomes actively operative as follows. Battery C supplies wires A and B with equal current, but battery D doubles the strength of the current traversing wire A. This is sufficient to not only neutralize the magnetism which the current in wire B would tend to set up, but also by reason of the excess of current in wire A, to make the bar a magnet whose polarity would be determined by the direction of the flow of current around it. In the arrangement shown in Figure 4, the batteries are so connected that current flow is in the same direction, thus doubling the amount of current flowing through wire A. But suppose the batteries were so connected that the current from each set flowed in an opposite direction. The result would be that these currents would oppose and neutralize each other, and therefore none would flow in wire A. Inasmuch, however, as there is nothing to hinder, current would flow from battery C through wire B, and the bar would therefore be magnetized. Hence, assuming that the relay is to be actuated from the distant end, D, it is in a sense immaterial whether the batteries connected with wire A assist or oppose each other, as in either case the bar would be magnetized only through the operation of the distant key. A slight elaboration of Figure 4 will further illustrate the principle of the differential duplex. In Figure 5 are two stations, A, the home end, and B, the distant station to which a message is to be sent. The relay at each end has two coils, 1 and 2, number 1 in each case being known as the main line coil, and 2 as the artificial line coil. The latter in each case has in its circuit a resistance R to compensate for the resistance of the main line, so that there shall be no inequalities in the circuits. The artificial line, as well as that to which the two coils are joined, are connected to earth. There is a battery C and a key K. When the key is depressed, current flows through the relay coils at A, but no magnetism is produced as they oppose each other. The current, however, flows out through the main line coil over the line and through the main line coil 1 at B, completing its circuit to earth and magnetizing the bar of the relay, thus causing its armature to be attracted. On releasing the key, the circuit is broken and magnetism instantly ceases. It will be evident, therefore, that the operator at A may cause the relay at B to act without affecting its own relay. Similar effects would be produced from B to A if the battery and key were placed at the B end. If, therefore, like instruments are placed at each end of a line, as in Figure 6, we have a differential duplex arrangement by means of which two operators may actuate relays at the ends distant from them, without causing the operation of the relays at their home ends. In practice, this is done by means of a special instrument known as a continuity-preserving transmitter, or, usually, as a transmitter. This consists of an electromagnet, T, operated by a key, K, and separate battery. The armature lever, L, is long, pivoted in the center, and is bent over at the end. At a point little beyond its center is a small piece of insulating material to which is screwed a strip of spring metal, S. Conveniently placed with reference to the end of the lever is a bent metallic piece, P. having contact screw in its upper horizontal arm, and attached to the lower end of this bent piece is a post or standard to which the main battery is electrically connected. The relay coils are connected by wire to the spring piece S, and the armature lever is connected to earth. If the key is depressed, the armature is attracted and its bent end is moved upward, depressing the spring, which makes contact with the upper screw, which places the battery to the line and simultaneously breaks the ground connection between the spring and the upturned end of the lever, as shown on the left. When the key is released, the battery is again connected to earth. The compensating resistances and condensers necessary for a duplex arrangement are shown in the diagram. In Figure 6, one transmitter is shown as closed at A, while the other one is open. From our previous illustrations and explanations, it will be readily seen that, with the transmitter closed at station A, current flows via post P through S and to both relay coils at A, thence over the main line to main line coil at B, and down to earth through S and the armature lever with its grounded wire. The relay at A would be unresponsive, but the core of the relay at B would be magnetized and its armature respond to signals from A. In like manner, if the transmitter at B be closed, current would flow through similar parts and thus cause the relay at A to respond. If both transmitters be closed simultaneously, both batteries will be placed to the line, which would practically result in doubling the current in each of the mainline coils, in consequence of which both relays are energized and their armatures attracted through the operation of the keys at the distant ends. Hence, two messages can be sent in opposite directions over the same line simultaneously. The reader will undoubtedly see quite clearly from the above system, which rests upon varying the strength of the current, that the two messages could not be sent in the same direction over the one line at the same time. To accomplish this object, Edison introduced another and distinct feature, namely the using of the same current but also varying its direction of flow. That is to say, alternately reversing the polarity of the batteries as applied to the line, and thus producing corresponding changes in the polarity of another specially constructed type of relay called a polarized relay. To afford the reader a clear conception of such a relay, we would refer again to Figure 1 and its explanation, from which it appears that the polarity of a soft iron bar is determined not by the strength of the current flowing around it, but by the direction thereof. With this idea clearly in mind, the theory of the polarized relay, generally called polar relay as presented in the diagram, Figure 7, will be readily understood. As is a bar of soft iron bent as shown and wound around with insulated copper wire, the ends of which are connected with a battery B, thus forming an electromagnet, an essential part of this relay consists of a swinging permanent magnet, C, whose polarity remains fixed, that end between the terminals of the electromagnet being a north pole. Inasmuch as unlike poles of magnets are attracted to each other and like poles repelled, it follows that this north pole will be repelled by the north pole of the electromagnet, but will swing over and be attracted by its south pole. If the direction of flow of current be reversed by reversing the battery, the electromagnetic polarity also reverses and the end of the permanent magnet swings over to the other side. This is shown in the two figures of Figure 7. This device being a relay, its purpose is to repeat transmitted signals into a local circuit, as before explained. For this purpose there are provided at D and E a contact and a backstop, the former of which is opened and closed by the swinging permanent magnet, thus opening and closing the local circuit. Manifestly, there must be provided some convenient way for rapidly transposing the direction of the current flow, if such a device as the polar relay is to be used for the reception of telegraph messages, and this is accomplished by means of an instrument called a pole changer, which consists essentially of a movable contact piece connected permanently to the earth or grounded and arranged to connect one or the other pole of a battery to the line and simultaneously ground the other pole. This action of the pole changer is effected by movements of the armature of an electromagnet through the manipulation of an ordinary telegraph key by an operator at the home station, as in the operation of the transmitter above referred to. By a combination of the neutral relay and the polar relay, two operators, by manipulating two telegraph keys in the ordinary way, can simultaneously send two messages over one line in the same direction with the same current, one operator varying its strength and the other operator varying its polarity or direction of flow. This principle was covered by Edison's patent number 162,633 and was known as the diplex system, although in the patent referred to, Edison showed and claimed the adaptation of the principle to duplex telegraphy. Indeed, as a matter of fact, it was found that by winding the polar relay differently and arranging the circuits and collateral appliances appropriately, the polar duplex system was more highly efficient than the neutral system, and it is extensively used to the present day. Thus far we have referred to two systems, one the neutral or differential duplex, and the other the combination of the neutral and polar relays, making a diplex system. By one of these two systems, a single wire could be used for sending two messages in opposite directions, and by the other in the same direction or in opposite directions. Edison followed up his work on the diplex and combined the two systems into a quadruplex, by means of which four messages could be sent and received simultaneously over the one wire, two in each direction, thus employing 8 operators, 4 at each end, 2 sending and 2 receiving. The general principles of quadruplex telegraphy are based upon the phenomena which we have briefly outlined in connection with the neutral relay and the polar relay. The equipment of such a system at each end of the line consists of these two instruments, together with the special form of transmitter and the pole changer, and their keys for actuating the neutral and polar relays at the other or distant end. Besides these, there are the compensating resistances and condensers. All of these will be seen in the diagram, Figure 8. It will be understood, of course, that the polar relay, as used in the quadruplex system, is wound differently, and therefore its operation is somewhat similar in principle to that of the differentially wound neutral relay, in that it does not respond to the operation of the key at the home office, but only operates in response to the movements of the distant key. Our explanation has merely aimed to show the underlying phenomena and principles in broad outline without entering into more detail than was deemed absolutely necessary. It should be stated, however, that between the outline and the filling in of the details, there was an enormous amount of hard work, study, patient plodding, and endless experiments before Edison finally perfected his quadruplex system in the year 1874. If it were attempted to offer here a detailed explanation of the varied and numerous operations of the quadruplex, this article would assume the proportions of a treatise. An idea of their complexity may be gathered from the following, which is quoted from American Telegraphy and Encyclopedia of the Telegraph by William Maver, Jr. It may well be doubted whether in the whole range of applied electricity there occur such beautiful combinations, so quickly made, broken up, and others reformed, as in the operation of the Edison quadruplex. For example, it is quite demonstrable that during the making of a simple dash of the Morse alphabet by the neutral relay at the home station, the distant pole changer may reverse its battery several times. The home pole changer may do likewise, and the home transmitter may increase and decrease the electromotive force of the home battery repeatedly. Simultaneously, and of course as a consequence of the foregoing actions, the home neutral relay itself may have had its magnetism reversed several times, and the signal, that is, the dash, will have been made partly by the home battery, partly by the distant and home batteries combined, partly by current on the main line, and partly by current on the artificial line, partly by the main line static current, partly by the condenser static current, and yet on a well-adjusted circuit the dash will have been produced on the quadruplex sounder as clearly as any dash on an ordinary single-wire sounder. We present a diagrammatic illustration of the Edison quadruplex battery key system in Figure 8 and refer the reader to the above or other textbooks if he desires to make a close study of its intricate operations. Before finally dismissing the quadruplex, and for the benefit of the inquiring reader who may vainly puzzle over the intricacies of the circuits shown in Figure 8, a hint as to an essential difference between the neutral relay, as used in the duplex and as used in the quadruplex, may be given. With the duplex, as we have seen, the current on the main line is changed in strength only when both keys at opposite stations are closed together, so that a current due to both batteries flows over the main line. When a single message is sent from one station to the other, or when both stations are sending messages that do not conflict, only one battery or the other is connected to the main line. But with the quadruplex, suppose one of the operators in New York, for instance, is sending reversals of current to Chicago. We can readily see how these changes in polarity will operate the polar relay at the distant station. But why will they not also operate the neutral relay at the distant station as well? This difficulty was solved by dividing the battery at each station into two unequal parts, the smaller battery being always in circuit with the pole changer, ready to have its polarity reversed on the main line to operate the distant polar relay. But the spring retracting the armature of the neutral relay is made so stiff as to resist these weak currents. If, however, the transmitter is operated at the same end, the entire battery is connected to the main line, and the strength of this current is sufficient to operate the neutral relay. Whether the part or all of the battery is alternately connected or disconnected from the main line by the transmitter, the current so varied in strength is subject to reversal of polarity by the pole changer. But the variations in strength have no effect upon the distant polar relay, because that relay, being responsive to changes in polarity of a weak current, is obviously responsive to corresponding changes in polarity of a powerful current. With this distinction before him, the reader will have no difficulty in following the circuits of Figure 8, bearing always in mind that by reason of the differential winding of the polar and neutral relays, neither of the relays at one station will respond to the home battery and can only respond to the distant battery, the polar relay responding when the polarity of the current is reversed, whether the current be strong or weak, and the neutral relay responding when the line current is increased, regardless of its polarity. It should be added that besides the system illustrated in Figure 8, which is known as the differential principle, the quadruplex was also arranged to operate on the Wheatstone bridge principle, but it is not deemed necessary to enter into its details. The underlying phenomena were similar, the difference consisting largely in the arrangement of the circuits and apparatus. Edison made another notable contribution to multiplex telegraphy some years later in the Phonoplex. The name suggests the use of the telephone, and such indeed is the case. The necessity for this invention arose out of the problem of increasing the capacity of telegraph lines employed in through and way service, such as upon railroads. In a railroad system, there are usually 2 terminal stations and a number of way stations. There is naturally much intercommunication, which would be greatly curtailed by a system having the capacity of only a single message at a time. The duplexes above described could not be used on a railroad telegraph system because of the necessity of electrically balancing the line, which, while entirely feasible on a through line, would not be practicable between a number of intercommunicating points. Edison's Phonoplex normally doubled the capacity of telegraph lines, whether employed on way business or through traffic, but in actual practice made it possible to obtain more than double service. It has been in practical use for many years on some of the leading railroads of the United States. The system is a combination of telegraphic apparatus and telephone receiver, although in this case the latter instrument is not used in the generally understood manner. It is well known that the diaphragm of a telephone vibrates with the fluctuations of the current energizing the magnet beneath it. If the make and break of the magnetizing current be rapid, the vibrations being within the limits of the human ear, the diaphragm will produce an audible sound. But if the make and break be as slow as with the ordinary Morse transmission, the diaphragm will be merely flexed and return to its original form without producing a sound. If, therefore, there be placed in the same circuit a regular telegraph relay and a special telephone, an operator may, by manipulating a key, operate the relay and its sounder without producing a sound in the telephone, as the makes and breaks of the key are far below the limit of audibility. But if through the same circuit by means of another key suitably connected there sent the rapid changes in current from an induction coil, it will cause a series of loud clicks in the telephone, corresponding to the signals transmitted, but this current is too weak to affect the telegraph relay. It will be seen, therefore, that this method of weak duplexing is practiced, not by varying the strength or polarity, but by sending 2 kinds of current over the wire. Thus, 2 sets of Morse signals can be transmitted by 2 operators over one line at the same time without interfering with each other, and not only between terminal offices, but also between a terminal office and any intermediate office, or between 2 intermediate offices alone. End of Appendix II. Recording by Anna Maria Viola. www.amvaudio.com.
Appendix III of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Heidi Preuss. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix III. Automatic Telegraphy. From the year 1848, when a Scotsman, Alexander Bain, first devised a scheme for rapid telegraphy by automatic methods, down to the beginning of the 70s, many other inventors had also applied themselves to the solution of this difficult problem, with only indifferent success. Cheap telegraphy being the slogan of the time, Edison became arduously interested in the subject and, at the end of 3 years of hard work, produced an entirely successful system, a public test of which was made on December 11, 1873, when about 12,000 words were transmitted over a single wire from Washington to New York in 22½ minutes. Edison's system was commercially exploited for several years by the Automatic Telegraph Company, as related in the preceding narrative. As a premise to an explanation of the principles involved, that the transmission of telegraph messages by hand at a rate of 50 words per minute is considered a good average speed. Hence, the availability of a telegraph line, as thus operated, is limited to this capacity, except as it may be multiplied by 2 with the use of the duplex, or by 4 with the quadruplex. Increased rapidity of transmission may, however, be accomplished by automatic methods, by means of which, through the employment of suitable devices, messages may be stamped in or upon a paper tape, transmitted through automatically acting instruments, and be received at distant points in visible characters upon a similar tape at a rate 20 or more times greater, a speed far beyond the possibilities of the human hand to transmit or the ear to receive. In Edison's system of automatic telegraphy, a paper tape was perforated with a series of round holes, so arranged and spaced as to represent Morse characters, forming the words of the message to be transmitted. This was done in a special machine of Edison's invention called the perforator, consisting of a series of punches operated by a bank of keys, typewriter fashion. The paper tape passed over a cylinder and was kept in regular motion so as to receive the perforations in proper sequence. The perforated tape was then placed in the transmitting instrument, the essential parts of which were a metallic drum and a projecting arm carrying two small wheels, which by means of a spring were maintained in constant pressure on the drum. The wheels and drum were electrically connected in the line over which the message was to be sent, current being supplied by batteries in the ordinary manner. When the transmitting instrument was in operation, the perforated tape was passed over the drum in continuous progressive motion. Thus, the paper passed between the drum and the two small wheels, and, as dry paper is a non-conductor, current was prevented from passing until a perforation was reached. As the paper passed along, the wheels dropped into the perforations, making momentary contacts with the drum beneath, and causing momentary impulses of current to be transmitted over the line in the same way that they would be produced by the manipulation of the telegraph key, but with much greater rapidity. The perforations being so arranged as to regulate the length of the contact, the result would be the transmission of long and short impulses corresponding with the dots and dashes of the Morse alphabet. The receiving instrument at the other end of the line was constructed upon much the same general lines as the transmitter, consisting of a metallic drum and reels for the paper tape. Instead of the two small contact wheels, however, a projecting arm carried an iron pin or stylus, so arranged that its point would normally impinge upon the periphery of the drum. The iron pin and the drum were respectively connected so as to be in circuit with the transmission line and batteries. As the principle involved in the receiving operation was electrochemical decomposition, the paper tape upon which the incoming message was to be received was moistened with a chemical solution readily decomposable by the electric current. This paper, while still in a damp condition, was passed between the drum and the stylus in continuous progressive motion. When an electrical impulse came over the line from the transmitting end, current passed through the moistened paper from the iron pin, causing chemical decomposition, by reason of which the iron would be attacked and would mark a line on the paper. Such a line would be long or short, according to the duration of the electrical impulse. Inasmuch as a succession of such impulses coming over the line owed their origin to the perforations in the transmitting tape, it followed that the resulting marks upon the receiving tape would correspond thereto in their respective lengths. Hence, the transmitted message was received on the tape in visible dots and dashes representing characters of the Morse alphabet. The system will, perhaps, be better understood by reference to the following diagrammatic sketch of its general principles. Some idea of the rapidity of automatic telegraphy may be obtained when we consider the fact that with the use of Edison's system in the early 70s, it was common practice to transmit and receive from 3,000 or 4,000 words a minute over a single line between New York and Philadelphia. This system was exploited through the use of a moderately paid clerical force. In practice there was employed such a number of perforating machines as the exigency of business demanded. Each machine was operated by a clerk who translated the message into telegraphic characters and prepared the transmitting tape by punching the necessary perforations therein. An expert clerk could perforate such a tape at the rate of 50 to 60 words per minute. At the receiving end, the tape was taken by other clerks who translated the Morse characters into ordinary words, which were written on message blanks for delivery to persons for whom the messages were intended. This latter operation, copying as it was called, was not consistent with truly economical business practice. Edison therefore undertook the task of devising an improved system whereby the message, when received, would not require translation and rewriting, but would automatically appear on the tape in plain letters and words, ready for instant delivery. The result was his automatic Roman letter system, the basis for which included the above-named general principles of perforated transmission tape and electrochemical decomposition. Instead of punching Morse characters in the transmission tape, however, it was perforated with a series of small round holes forming Roman letters. The verticals of these letters were originally 5 holes high. The transmitting instrument had 5 small wheels or rollers instead of 2, for making contacts through the perforations and causing short electrical impulses to pass over the lines. At first, 5 lines were used to carry these impulses to the receiving instrument, where there were 5 iron pins impinging on the drum. By means of these pins, the chemically prepared tape was marked with dots corresponding to the impulses as received, leaving upon it a legible record of the letters and words transmitted. For the purposes of economy and investment in maintenance, Edison devised subsequently a plan by which the number of conducting lines was reduced to 2 instead of 5. The verticals of the letters were perforated only 4 holes high, and the 4 rollers were arranged in pairs, one pair being slightly in advance of the other. There were, of course, only 4 pins at the receiving instrument. 2 were of iron and 2 of tellurium. It being the gist of Edison's plan to effect the marking of the chemical paper by one metal with a positive current and by the other metal with a negative current. In the following diagram, which shows the theory of this arrangement, it will be seen that both the transmitting rollers and the receiving pins are arranged in pairs, one pair in each case being slightly in advance of the other. Of these receiving pins, one pair, 1 and 3, are of iron, and the other pair, 2 and 4, are of tellurium. Pins 1, 2, and 3, 4 are electrically connected together in other pairs, and then each of these pairs is connected with one of the main lines that runs respectively to the middle of the groups of batteries at the transmitting end. The terminals of these groups of batteries are connected respectively to the 4 rollers which impinge upon the transmitting drum, the negatives being connected to 5 and 7, and the positives to 6 and 8, as denoted by the letters N and P. The transmitting and receiving drums are respectively connected to earth. In operation, the perforated tape is placed on the transmission drum and the chemically prepared tape on the receiving drum. As the perforated tape passes over the transmission drum, the advance rollers 6 or 8 first close the circuit through the perforations, and a positive current passes from the batteries through the drum and down to the ground, thence through the earth at the receiving end up to the other drum and back to the batteries via the tellurium pins 2 or 4 and the line wire. With this positive current, the tellurium pins make marks upon the paper tape, but the iron pins make no mark. In the merest fraction of a second, as the perforated paper continues to pass over the transmission drum, rollers 5 or 7 close the circuit through other perforations, and current passes in the opposite direction, over the line wire, through pins 1 or 3, and return through the earth. In this case, the iron pins mark the paper tape, but the tellurium pins make no mark. It will be obvious, therefore, that as the rollers are set so as to allow of currents of opposite polarity to be alternately and rapidly sent by means of the perforations, the marks upon the tape at the receiving station will occupy their proper relative positions, and the aggregate result will be letters corresponding to those perforated in the transmission tape. Edison subsequently made further improvements in this direction, by which he reduced the number of conducting wires to 1, but the principles involved were analogous to the one just described. This Roman letter system was in use for several years on lines between New York, Philadelphia, and Washington, and was so efficient that a speed of 3,000 words a minute was attained on the line between the first two named cities. Inasmuch as there were several proposed systems of rapid automatic telegraphy in existence at the time Edison entered the field, but none of them in practical commercial use, it becomes a matter of interest to inquire wherein they were deficient and what constituted the elements of Edison's success. The chief difficulties in transmission of Morse characters had been 2 in number, the most serious of which was that on the receiving tape the characters would be prolonged and run into one another, forming a draggled line and thus rendering the message unintelligible. This arose from the fact that on account of the rapid succession of electric impulses there was not sufficient time between them for the electric action to cease entirely. Consequently, the line would not clear itself and become surcharged, as it were, the effect being an attenuated prolongation of each impulse as manifested in a weaker continuation of the mark on the tape, thus making the whole message indistinct. These secondary marks were called tailings. For many years electricians had tried in vain to overcome this difficulty. Edison devoted a great deal of thought and energy to the question, in the course of which he experimented through 120 consecutive nights in the year of 1873 on the line between New York and Washington. His solution of the problem was simple but effectual. It involved the principle of inductive compensation. In a shunt circuit with the receiving instrument, he introduced electromagnets. The pulsations of the current passed through the helices of these magnets, producing an augmented marking effect upon the receiving tape. But upon the breaking of the current, the magnet, in discharging itself of the induced magnetism, would set up momentarily a countercurrent of opposite polarity. This neutralized the tailing effect by clearing the line between pulsations, thus allowing the telegraphic characters to be clearly and distinctly outlined upon the tape. Further elaboration of this method was made later by the addition of rheostats, condensers, and local opposition batteries on long lines. The other difficulty above referenced to was one that had also occupied considerable thought and attention of many workers in the field, and related to the perforating of the dash in the transmission tape. It involved mechanical complications that seemed to be insurmountable, and up to the time Edison invented his perforating machine, no really good method was available. He abandoned the attempt to cut dashes as such in the paper tape, but instead punched 3 round holes, so arranged as to form a triangle. A concrete example is presented in the illustration below, which shows a piece of tape with perforations representing the word same. The philosophy of this will at once be perceived when it is remembered that the 2 wheels running upon the drum of the transmitting instrument were situated side by side, corresponding in distance to the 2 rows of holes. When a triangle of 3 holes, intended to form the dash, reached the wheels, one of them dropped into a lower hole. Before it could get out, the other wheel dropped into the hole at the apex of the triangle, thus continuing the connection, which was still further prolonged by the first wheel dropping into the third hole. Thus an extended contact was made, which, by transmitting a long impulse, resulted in the marking of a dash upon the receiving tape. This method was in successful commercial use for some time in the early 70s, giving a speed of from 3,000 to 4,000 words a minute over a single line, but later on was superseded by Edison's Roman letter system above referred to. The subject of automatic telegraphy received a vast amount of attention from investors at the time it was in vogue. None was more earnest or indefatigable than Edison, who during the progress of his inventions took out 38 patents on various inventions relating thereto, some of them covering chemical solutions for the receiving paper. This of itself was a subject of much importance, and a vast amount of research and labor was expended upon it. In the laboratory notebooks there are recorded thousands of experiments showing that Edison's investigations not only included an enormous number of chemical salts and compounds, but also an exhaustive variety of plants, flowers, roots, herbs, and barks. It seems inexplicable at first view that a system of telegraphy sufficiently rapid and economical to be practically available for important business correspondence should have fallen into disuse. This, however, is made clear, so far as concerns Edison's inventions at any rate, in Chapter 8 of the preceding narrative. End Appendix III. Appendix IV of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Heidi Preuss. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix IV. Wireless Telegraphy. Although Mr. Edison has taken no active part in the development of the more modern wireless telegraphy, and his name has not occurred in connection therewith, the underlying phenomena had been noted by him many years in advance of the art, as will presently be explained. The authors believe that this explanation will reveal a status of Edison in relation to the subject that has thus far been unknown to the public. While the term wireless telegraphy, as now applied to the modern method of electrical communication between distant points, without intervening conductors, is self-explanatory, it is also applicable, strictly speaking, to the previous art of telegraphing to and from moving trains, and between points not greatly remote from each other, and not connected together with wires. The latter system, described in Chapter 23, and in a succeeding article of this appendix, was based upon the phenomena of electromagnetic or electrostatic induction between conductors separated by more or less space, whereby electric impulses of relatively low potential and low frequency set up in one conductor were committed inductively across the air to another conductor, and there received through the medium of appropriate instruments connected therewith. As distinguished from this system, however, modern wireless telegraphy, so-called, has basis in the utilization of electric or ether waves in free space, such waves being set up by electric oscillations or surgings of comparatively high potential and high frequency, produced by the operation of suitable electrical apparatus. Broadly speaking, these oscillations arise from disruptive discharges of an inductive coil, or other form of oscillator, across an air gap, and their character is controlled by the manipulation of a special type of circuit breaking key, by means of which long and short discharges are produced. The electric or etheric waves thereby set up are detected and received by another special form of apparatus, more or less distant, without any intervening wires or conductors. In November 1875, Edison, while experimenting in his Newark laboratory, discovered a new manifestation of electricity through mysterious sparks which could be produced under conditions unknown up to that time. Recognizing at once the absolutely unique character of the phenomena, he continued his investigations enthusiastically over 2 months, finally arriving at a correct conclusion as to the oscillatory nature of the hitherto unknown manifestations. Strange to say, however, the true impact and practical applicability of these phenomena did not occur to his mind. Indeed, it was not until more than 12 years afterwards, in 1887, upon the publication of the notable work of Professor H. Hertz, proving the existence of electric waves in free space, that Edison realized the fact that the fundamental principle of aerial telegraphy had been within his grasp in the winter of 1875. For although the work of Hertz was more profound and mathematical than that of Edison, the principle involved and the phenomena observed were practically identical. In fact, it may be remarked that some of the methods and experimental apparatus were quite similar, especially the dark box with micrometer adjustment used by both in observing the spark. Footnote 25. 25. During the period in which Edison exhibited his lightning system at the Paris Exposition in 1881, his representative, Mr. Charles Batchelor, repeated Edison's remarkable experiments of the winter of 1875 for the benefit of a great number of European savants, using with other apparatus the original dark box with micrometer adjustment. There is not the slightest intention on the part of the authors to detract in the least degree from the brilliant work of Hertz. On the contrary, to ascribe to him the honor that is his due in having given mathematical direction and certainty to so important a discovery. The adaptation of the principles thus elucidated, and the subsequent development of the present wonderful art by Marconi, Branly, Lodge, Slaby, and others, are now too well known to call for further remark at this place. Strange to say, that although Edison's early experiments in etheric force called forth extensive comment and discussion in the public prints of the period, they seem to have been generally overlooked when the work of Hertz was published. At a meeting of the Institution of Electrical Engineers, held in London on May 16, 1889, at which there was a discussion on the celebrated paper of Professor Sir Oliver Lodge on lightning conductors. However, the chairman, Sir William Thomson, Lord Kelvin, made the following remark. We all know how Faraday made himself a cage 6 feet in diameter, hung it up in mid-air in the theatre of the Royal Institution, went into it, and, as he said, lived in it and made experiments. It was a cage with tinfoil hanging all around it. It was not a complete metallic enclosing shell. Faraday had a powerful machine working in the neighborhood, giving all varieties of gradual working up and discharges by impulsive rush, and whether it was a sudden discharge of ordinary insulated conductors or of Leyden jars in the neighborhood outside the cage, or electrification and discharge of the cage itself, he saw no effect on his most delicate gold-leaf electroscopes in the interior. His attention was not directed to look for Hertz sparks, or probably he might have found them in the interior. Edison seems to have noticed something of the kind in what he called the etheric force. His name etheric may 13 years ago have seemed to many people absurd, but now we are all beginning to call these inductive phenomena etheric. With these preliminary observations, let us now glance briefly at Edison's laboratory experiments, of which mention has been made. On the first manifestation of the unusual phenomena in November 1875, Edison's keenness of perception led him at once to believe that he had discovered a new force. Indeed, the earliest entry of this discovery in the laboratory notebook bore that caption. After a few days of further experiment and observation, however, he changed it to etheric force, and the further records thereof, all in Mr. Bachelor's handwriting, were under that heading. The publication of Edison's discovery created considerable attention at the time, calling forth a storm of general ridicule and incredulity. But a few scientific men of the period, whose experimental methods were careful and exact, corroborated his deductions after obtaining similar phenomena by repeating his experiments with intelligent precision. Among these was the late Dr. George M. Beard, a noted physicist, who entered enthusiastically into the investigation and, in addition to a great deal of independent experiment, spent much time with Edison at his laboratory. Dr. Beard wrote a treatise of some length on the subject, in which he concurred with Edison's deduction that the phenomena were the manifestation of oscillations, or rapidly reversing waves of electricity, which did not respond to the usual tests. Edison had observed the tendency of this force to diffuse itself in various directions through the air and through matter, hence the name etheric that he had provisionally applied to it. Edison's laboratory notes on this striking investigation are fascinating and voluminous, but cannot be reproduced in full for lack of space. In view of the latter practical application of the principles involved, however, the reader will probably be interested in perusing the few extracts therefrom, as illustrated by facsimiles of the original sketches from the laboratory notebook. As the full significance of the experiments shown by these extracts may not be apparent to a lay reader, it may be stated by way of premise that ordinarily a current only follows a closed circuit. An electric bell or electric light is a familiar instance of this rule. There is in each case an open wire circuit, which is closed by pressing the button or turning the switch, thus making a complete and uninterrupted path in which the current may travel and do its work. Until the time of Edison's investigations of 1875, now under consideration, electricity had never been known to manifest itself except through a closed circuit. But as the reader will see from the following excerpts, Edison discovered a hitherto unknown phenomenon, namely, that under certain conditions the rule would be reversed and electricity would pass through space and through matter entirely unconnected with its point of origin. In other words, he had found the forerunner of wireless telegraphy. Had he then realized the full import of his discovery, all he needed was to increase the strength of the waves and to provide a very sensitive detector like the coherer in order to have anticipated the principal developments that came many years afterwards. With these explanatory observations, we will now turn to the excerpts referred to, which are as follows. November 22, 1875. New force. In experimenting with a vibrator magnet, consisting of a bar of stub steel, fastened at one end and made to vibrate by means of a magnet, we noticed a spark coming from the cores of the magnet. This we have noticed often in relays and stock printers, when there were little iron filings between the armature and core, and more often in our new electric pen, and we have always come to the conclusion that it was caused by strong induction. But when we noticed it on this vibrator, it seemed so strong that it struck us forcibly there might be something more than induction. We now found that if we touched any metallic part of the vibrator or magnet, we got the spark. The larger the body of iron touched to the vibrator, the larger the spark. We now connected a wire to X, the end of the vibrating rod, and we found we could get a spark from it by touching a piece of iron to it. And one of the more curious phenomena is that if you turn the wire around on itself and let the point of the wire touch any other portion of itself, you get a spark. By connecting X to the gas pipe, we drew sparks from the gas pipes in any part of the room by drawing an iron wire over the brass jet of the cock. This is simply wonderful, and a good proof that the cause of the spark is a true unknown force. November 23, 1815. New force. The following very curious result was obtained with it. The vibrator shown in Figure 1 and battery were placed on insulated stands, and a wire connected to X, tried both copper and iron, carried over to the stove about 20 feet distant. When the end of the wire was rubbed on the stove, it gave out splendid sparks. When permanently connected to the stove, sparks could be drawn from the stove by a piece of wire held in the hand. The point X of the vibrator was now connected to the gas pipe, and still sparks could be drawn from the stove. Put a coil of wire over the end of rod X and passed the ends of spool through galvanometer without affecting it in any way. Tried a 6 ohm spool. Add a 200 ohm. We now tried all the metals, touching each one in turn to the point X. Here follows a list of metals and the character of sparks obtained with each. By increasing the battery from 8 to 12 cells, we get a spark when the vibrating magnet is shunted with 3 ohms. Cannot taste the least shock at B, yet between carbon points the spark is very vivid. As will be seen, X has no connection with anything. With a glass rod 4 feet long, well rubbed with a piece of silk over a hot stove, with a piece of battery carbon secured to one end, we received vivid sparks into the carbon when the other end was held in the hand with the handkerchief. Yet the galvanometer, chemical paper, the sense of shock in the tongue, and a gold leaf electroscope, which would diverge at 2 feet from a half-inch spark plate glass machine, were not affected in the least by it. A piece of coal held to the wire showed faint sparks. We had a box made thus, whereby 2 points could be brought together within a dark box provided with an eyepiece. The points were iron, and we found the sparks were very irregular. After testing some time, 2 lead pencils found more regular and very much more vivid. We then substituted the graphite points instead of iron. 26. 26. The dark box had micrometer screws for delicate adjustment of the carbon points, and was thereafter largely used in this series of investigations for better study of the spark. When Mr. Edison's experiments were repeated by Mr. Bachelor, who represented him at the Paris Exposition of 1881, the dark box was employed for a similar purpose. After recording a considerable number of other experiments, the laboratory notes go on to state: November 30, 1875, etheric force. We found the addition of battery to the Stubbs wire vibrator greatly increased the volume of the spark. Several persons could obtain sparks from the gas pipe at once, each spark being equal in volume and brilliancy to the spark drawn by a single person. Edison now grasped the gas pipe, and with the other hand holding a piece of metal, he touched several other metallic substances, obtained sparks, showing that the force passed through his body. December 3, 1875, etheric force. Charlie Edison hung to the glass pipe with feet above the floor, and with a knife got sparks from the pipe he was hanging on. We now took the wire from the vibrator in one hand, and stood on a block of paraffin 18 inches square and 6 inches thick. Holding a knife in the other hand, we drew sparks from the stovepipe. We now tried the crucial test of passing the etheric current through the sciatic nerve of a frog just killed. Previous to trying, we tested its sensibility by current from a single Bunsen cell. We put in resistance up to 500,000 ohms, and the twitching was still perceptible. We tried the induced current from our induction coil, having one cell on primary, the spark jumping about 1/50th of an inch, the terminal of the secondary connected to the frog, and it straightened out in violence. We arranged frogs' legs to pass etheric force through. We placed legs on an inverted beaker and held the two ends of the wire on glass rods 8 inches long. On connecting one to the sciatic nerve and the other to the fleshy part of the leg, no movement could be discerned, although brilliant sparks could be obtained on the graphite points when the frog was in current. Dr. Beard was present when this was tried. December 5, 1875. Etheric force. 3 persons grasping hands and standing upon blocks of paraffin 12 inches square and 6 thick drew sparks from the adjoining stove when another person touched the sounder with any piece of metal. A galvanoscopic frog giving contractions with one cell through the water rheostats was placed in circuit. When the wires from the vibrator and the gas pipe were connected, slight contractions were noticed, sometimes very plain and marked, showing the apparent presence of electricity, which from the high insulation seemed improbable. Dr. Beard, who was present, inferred from the way the leg contracted that it moved on both opening and closing the circuit. To test this, we disconnected the wire between the frog and the battery, and placed instead of a vibrating sounder a simple Morse key and a sounder taking the etheric from armature. The spark was now tested in dark box and found to be very strong. It was then connected to the nerves of the frog, but no movement of any kind could be detected upon working the key, although the brilliancy and power of the spark were undiminished. The thought then occurred to Edison that the movement of the frog was due to mechanical vibrations from the vibrator, which gives probably 250 vibrations per second, passing through the wires and irritating the sensitive nerves of the frog. Upon disconnecting the battery wires and holding a tuning fork giving 326 vibrations per second to the base of the sounder, the vibrations over the wire made the frog contract nearly every time. The contraction of the frog's legs may be with considerable safety be said to be caused by these mechanical vibrations being transmitted through the conducting wires. Edison thought that the longitudinal vibrations caused by the sounder produced a more marked effect, and proceeded to try out his theory. The very next entry in the laboratory notebook bears the same date as the above, December 5, 1875, and is entitled Longitudinal Vibrations, and reads as follows. We took a long iron wire 1/16 of an inch in diameter, and rubbed it lengthways with a piece of leather with resin on for about 3 feet, backwards and forwards. About 10 feet away we applied the wire to the back of the neck, and it gives a horrible sensation, showing the vibrations are conducted through the wire. The following experiment illustrates notably the movement of the electric waves through free space. December 26, 1875. Etheric force. An experiment tried tonight gives a curious result. A is a vibrator, B, C, D, and E are sheets of tinfoil hung on insulating strands. The sheets are about 12 by 8 inches. B and C are 26 inches apart, C and D 48 inches, and D and E 26 inches. B is connected to the vibrator and E to point in dark box, the other point to ground. We received sparks at intervals although insulated by such space. With the above, our extracts must close, although we have given but a few of the interesting experiments tried at the time. It will be noticed, however, that these records show such progression in little over a month. Just after the item last above extracted, the Edison shop became greatly rushed on telegraphic inventions, and not many months afterwards came the removal to Menlo Park. Hence the etheric force investigations were sidetracked for other matters deemed to be more important at that time. Dr. Beard, in his previously mentioned treatise, refers on page 27 to the views of others who have repeated Edison's experiments and observed the phenomena, and in a footnote says, Professor Houston, of Philadelphia, among others, has repeated some of these physical experiments and has adopted in full, and after but a partial study of the subject, the hypothesis of rapidly reversed electricity, as suggested in my letter to the Tribune of December 8th, and further claims priority of discovery because he observed the spark of this when experimenting with a Ruhmkorff coil 4 years ago. To this claim, if it be seriously entertained, the obvious reply is that thousands of persons probably had seen this spark before it was discovered by Mr. Edison. It had been seen by Professor Nefer, who supposed, and still supposes, it is the spark of the extra current. It has been seen by my friend Professor J. E. Smith, who assumed, as he tells me without examination, that it was inductive electricity breaking through bad insulation. It had been seen, as has been stated, by Mr. Edison many times before he thought it was worthy of study. It was undoubtedly seen by Professor Houston, who, like so many others, failed to even suspect its meaning, and thus missed an important discovery. The honor of a scientific discovery belongs not to him who first sees a thing, but to him who first sees it with expert eyes, not to him even who drops an original suggestion, but to him who first makes that suggestion fruitful of results. If to see with the eyes a phenomenon is to discover the law of which that phenomenon is a part, then every schoolboy who before the time of Newton ever saw an apple fall was a discoverer of the law of gravitation. Edison took out only one patent on long-distance telegraphy without wires. While the principle involved therein, induction, was not precisely analogous to the above, or to the present system of wireless telegraphy, it was a step forward in the process of the art. The application was filed May 23, 1885. At the time he was working on induction telegraphy, 2 years before the publication of the work of Hertz. But the patent, number 465971, was not issued until December 29, 1891. In 1903 it was purchased from him by Marconi Wireless Telegraph Company. Edison has always had a great admiration for Marconi and his work, and a warm friendship exists between the two men. During the formative period of the Marconi Company, attempts were made to influence Edison to sell this patent to an opposing concern. But his regard for Marconi and belief in the fundamental nature of his work were so strong that he refused flatly, because in the hands of an enemy the patent might be used inimically to Marconi's interests. Edison's ideas, as expressed in the specification of this patent, show very clearly the close analogy of his system to that now in vogue. As they were filed in the Patent Office several years before the possibility of wireless telegraphy was suspected, it will undoubtedly be of interest to give the following extract therefrom. I have discovered that if sufficient elevation be obtained to overcome the curvature of the earth's surface, and to reduce to the minimum the earth's absorption, electric telegraphing or signaling between distant points can be carried on by induction without the use of wires connecting such distant points. This discovery is especially applicable to telegraphing across bodies of water, thus avoiding the use of submarine cables, or for communicating between vessels at sea, or between vessels at sea and points of land. But it is also applicable to electric communication between distant points on land, it being necessary, however, on land, with the exception of communication over open prairie, to increase the elevation in order to reduce the minimum the induction absorbing effect of houses, trees, and elevations in the land itself. At sea, from an elevation of 100 feet, I can communicate electrically at great distance, and since this elevation, or one sufficiently high, can be had by utilizing the masts of ships, signals can be sent and received between ships separated a considerable distance, and by repeating the signals from ship to ship, communication can be established between points at any distance apart or across the largest seas and even oceans. The collision of ships in fog can be prevented by this character of signaling, by the use of which also the safety of a ship in approaching a dangerous coast in foggy weather can be assured. In communicating between points on land, poles of great height can be used, or captive balloons. At these elevated points, whether upon the masts of ships, upon poles or balloons, condensing surfaces of metal or other conductor of electricity are located. Each condensing surface is connected with earth by an electrical conducting wire. On land, this earth connection would be one of usual character in telegraphy. At sea, the wire would run to one or more metal plates on the bottom of the vessel, where the earth connection would be made with the water. The high-resistance secondary circuit of an induction coil is located in circuit between the condensing surface and the ground. The primary circuit of the induction coil includes a battery and a device for transmitting signals, which may be a revolving circuit breaker operated continually by a motor of any suitable kind, either electrical or mechanical, and a key, normally short-circuiting the circuit breaker or secondary coil. For receiving signals, I locate in said circuit, between the condensing surface and the ground, a diaphragm sounder, which is preferably one of my Electromotograph telephone receivers. The key normally short-circuiting the revolving circuit breaker, no impulses are produced in the induction coil until the key is depressed. When a large number of impulses are produced in the primary, and by means of the secondary corresponding impulses or variations in tension, are produced at the elevated condensing surface, producing thereat electrostatic impulses. These electrostatic impulses are transmitted inductively to the elevated condensing surface at the distant point, and are made audible by the electromotograph connected to the ground circuit with such distant condensing surface. The accompanying illustrations are reduced facsimiles of the drawings attached to the above patent, number 465971. End of Appendix IV.
Appendix V of Edison, his Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Anna Simon. Edison, his Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix V. The Electromotograph. In solving a problem that at the time was thought to be insurmountable, and in the adaptability of its principles to the successful overcoming of apparently insuperable difficulties subsequently arising in other lines of work, this invention is one of the most remarkable of the many that Edison has made in his long career as an inventor. The object primarily sought to be accomplished was the repeating of telegraphic signals from a distance without the aid of a galvanometer or an electromagnetic relay to overcome the claims of the Page patent referred to in the preceding narrative. This object was achieved in the device described in Edison's basic patent number 158,787, issued January 19, 1875, by the substitution of friction and anti-friction for the presence and absence of magnetism in a regulation relay. It may be observed, parenthetically, for the benefit of the lay reader, that in telegraphy the device known as the relay is a receiving instrument containing an electromagnet adapted to respond to the weak line current. Its armature moves in accordance with electrical impulses, or signals, transmitted from a distance, and, in so responding, operates mechanically to alternately close and open a separate local circuit in which there is a sounder and a powerful battery. When used for true relaying purposes, the signals received from a distance are in turn repeated over the next section of the line, the powerful local battery furnishing current for this purpose. As this causes a loud repetition of the original signals, it will be seen that relaying is an economic method of extending a telegraph circuit beyond the natural limits of its battery power. At the time of Edison's invention, as related in Chapter 9 of the preceding narrative, There existed no other known method than the one just described for the repetition of transmitted signals, thus limiting the application of telegraphy to the pleasure of those who might own any patent controlling the relay, except on simple circuits where a single battery was sufficient. Edison's previous discovery of differential friction of surfaces through electrochemical decomposition was now adapted by him to produce motion at the end of a circuit without the intervention of an electromagnet. In other words, he invented a telegraph instrument having a vibrator controlled by electrochemical decomposition to take the place of a vibrating armature operated by an electromagnet, and thus opened an entirely new and unsuspected avenue in the art. Edison's Electromotograph comprised an ingeniously arranged apparatus in which two surfaces, normally in contact with each other, were caused to alternately adhere by friction or slip by reason of electrochemical decomposition. One of these surfaces consisted of a small drum or cylinder of chalk, which was kept in a moistened condition with a suitable chemical solution and adapted to revolve continuously by clockwork. The other surface consisted of a small pad which rested with frictional pressure on the periphery of the drum. This pad was carried on the end of a vibrating arm whose lateral movement was limited between two adjustable points. Normally, the frictional pressure between the drum and the pad would carry the latter with the former as it revolved, but if the friction were removed, a spring on the end of the vibrator arm would draw it back to its starting place. In practice, the chalk drum was electrically connected with one pole of an incoming telegraph circuit, and the vibrating arm and pad with the other pole. When the drum rotated, the friction of the pad carried the vibrating arm forward, but an electrical impulse coming over the line would decompose the chemical solution with which the drum was moistened, causing an effect similar to the lubrication, and thus allowing the pad to slip backward freely in response to the pull of its retractile spring. The frictional movements of the pad with the drum were comparatively long or short, and corresponded with the length of the impulses sent in over the line. Thus, the transmission of Morse dots and dashes by the distant operator resulted in movements of corresponding length by the frictional pad and vibrating arm. This brings us to the gist of the ingenious way in which Edison substituted the action of electrochemical decomposition for that of the electromagnet to operate a relay. The actual relaying was accomplished through the medium of two contacts making connection with a local or relay circuit. One of these contacts was fixed, while the other was carried by the vibrating arm, and, as the latter made its forward and backward movements, these contacts were alternately brought together or separated, thus throwing in and out of circuit the battery and sounder in the local circuit and causing a repetition of the incoming signals. The other side of the local circuit was permanently connected to an insulated block on the vibrator. This device not only worked with great rapidity, but was extremely sensitive, and would respond to currents too weak to affect the most delicate electromagnetic relay. It should be stated that Edison did not confine himself to the working of the electromotograph by the slipping of surfaces through the action of incoming current, but by varying the characters of the surfaces in contact, the frictional effect might be intensified by the electrical current. In such a case, the movements would be the reverse of those above indicated, but the end sought, namely, the relaying of messages, would be attained with the same certainty. While the principal object of this invention was to accomplish the repetition of signals without the aid of an electromagnetic relay, the instrument devised by Edison was capable of use as a recorder also, by employing a small wheel inked by a fountain wheel and attached to the vibrating arm through suitable mechanism. By means of this adjunct, the dashes and dots of the transmitted impulses could be recorded upon a paper ribbon passing continuously over the drum. The electromotograph is shown diagrammatically in figures 1 and 2, in plan and vertical section respectively. The reference letters in each case indicate identical parts, A being the chalk drum, B the paper tape, C the auxiliary cylinder, D the vibrating arm, E the frictional pad, F the spring, G and H the two contacts, I and J the two wires leading to local circuit, K a battery, and L an ordinary telegraph key. The two last named, K and L, are shown to make the sketch complete, but in practice would be at the transmitting end, which might be hundreds of miles away. It will be understood, of course, that the electromotograph is a receiving and relaying instrument. Another notable use of the electromotograph principle was in its adaptation to the receiver in Edison's loud-speaking telephone, on which United States Patent number 221,957 was issued November 25, 1879. A chalk cylinder moistened with a chemical solution was revolved by hand or a small motor. Resting on the cylinder was a palladium-faced pen or spring, which was attached to a mica diaphragm in a resonator. The current passed from the main line through the pen to the chalk and to the battery. The sound waves impinging upon the distant transmitter varied the resistance of the carbon button therein, thus causing corresponding variations in the strength of the battery current. These variations, passing through the chalk cylinder, produced more or less electrochemical decomposition, which in turn caused differences of adhesion between the pen and cylinder, and hence gave rise to mechanical vibrations of the diaphragm, by reason of which the speaker's words were reproduced. Telephones so operated repeated speaking and singing in very loud tones. In one instance, spoken words and the singing of songs originating at a distance were heard perfectly by an audience of over 5,000 people. The loud-speaking telephone is shown in section, diagrammatically, in the sketch, figure 3, in which A is the chalk cylinder mounted on a shaft, B. The palladium-faced pen or spring, C, is connected to diaphragm D. The instrument in its commercial form is shown in figure 4. End of Appendix V.
Appendix VI of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Comerford Martin. Appendix VI. The Telephone. On April 27, 1877, Edison filed in the United States Patent Office an application for a patent on a telephone, and on May 3, 1892, more than 15 years afterward, patent number 474230 was granted thereon. Numerous other patents have been issued to him for improvements in telephones, but the one above specified may be considered as the most important of them, since it is the one that first discloses the principle of the carbon transmitter. This patent embodies but two claims, which are as follows. 1. In a speaking telegraph transmitter, the combination of a metallic diaphragm and disc of plumbago or equivalent material, the contiguous faces of said disc and diaphragm being in contact, substantially as described. 2. As a means for effecting a varying surface contact in the circuit of a speaking telegraph transmitter, the combination of two electrodes, one of plumbago or similar material, and both having broad surfaces in vibrating contact with each other, substantially as described. The advance that was brought about by Edison's carbon transmitter will be more apparent if we glance first at the state of the art of telephony prior to his invention. Bell was undoubtedly the first inventor of the art of transmitting speech over an electric circuit, but, with his particular form of telephone, the field was circumscribed. Bell's telephone is shown in the diagrammatic sectional sketch, figure 1. In the drawing, M is a bar magnet contained in the rubber case L, a bobbin, or a coil of wire B, surrounds one end of the magnet. A diaphragm of soft iron is shown at D, and E is the mouthpiece. The wire terminals of the coil B connect with the binding screws C. The next illustration shows a pair of such telephones connected for use, the working parts only being designated by the above reference letters. It will be noted that the wire terminals are here put to their proper uses, two being joined together to form a line of communication, and the other two being respectively connected to ground. Now, if we imagine a person at each one of the instruments, figure 2, we shall find that when one of them speaks, the sound vibrations impinge upon the diaphragm and cause it to act as a vibrating armature. By reason of its vibrations, this diaphragm induces very weak electric impulses in the magnetic coil. These impulses, according to Bell's theory, correspond in form to the sound waves, and, passing over the line, energize the magnetic coil at the receiving end, thus giving rise to corresponding variations in magnetism, by reason of which the receiving diaphragm is similarly vibrated so as to reproduce the sounds. A single apparatus at each end is therefore sufficient, performing the double function of transmitter and receiver. It will be noticed that in this arrangement no battery is used. The strength of the impulses transmitted is therefore limited to that of the necessarily weak induction currents generated by the original sounds, minus any loss arising by reason of resistance in the line. Edison's carbon transmitter overcame this vital or limiting weakness by providing for independent power on the transmission circuit, and by introducing the principle of varying the resistance of that circuit with changes in the pressure. With Edison's telephone there is used a closed circuit on which a battery current constantly flows, and in that circuit is a pair of electrodes, one or both of which is carbon. These electrodes are always in contact with a certain initial pressure, so that current will always be flowing over the circuit. One of the electrodes is connected with the diaphragm on which the sound waves impinge, and the vibrations of this diaphragm cause corresponding variations in pressure between the electrodes, and thereby effect similar variations in the current which is passing over the line to the receiving end. This current, flowing around the receiving magnet, causes corresponding impulses therein, which, acting upon its diaphragm, effect a reproduction of the original vibrations, and hence of the original sounds. In other words, the essential difference is that with Bell's telephone the sound waves themselves generate the electric impulses, which are therefore extremely faint. With Edison's telephone the sound waves simply actuate an electric valve, so to speak, and permit variations in a current of any desired strength. A second distinction between the two telephones is this. With the Bell apparatus, the very weak electric impulses generated by the vibration of the transmitting diaphragm pass over the entire line to the receiving end, and in consequence, the possible length of line is limited to a few miles, even under ideal conditions. With Edison's telephone, the battery current does not flow on the main line, but passes through the primary circuit of an induction coil, from the secondary of which corresponding impulses of enormously higher potential are sent out on the main line to the receiving end. In consequence, the line may be hundreds of miles in length. No modern telephone system is in use today that does not use these characteristic features, the varying resistance and the induction coil. The system inaugurated by Edison is shown by the diagram, figure 3, in which the carbon transmitter, the induction coil, the line, and the distant receiver are respectively indicated. In figure 4, an early form of the Edison carbon transmitter is represented in a sectional view. The carbon disc is represented by the black portion E near the diaphragm, A, placed between two platinum plates D and G, which are connected in the battery circuit as shown by the lines. A small piece of rubber tubing B is attached to the center of the metallic diaphragm, and presses lightly against an ivory piece, F, which is placed directly over one of the platinum plates. Whenever, therefore, any motion is given to the diaphragm, it is immediately followed by a corresponding pressure upon the carbon, and by a change of resistance in the latter, as described above. It is interesting to note the position which Edison occupies in the telephone art from a legal standpoint. To this end, the reader's attention is called to a few extracts from a decision of Judge Brown in 2 suits brought in the United States Circuit Court, District of Massachusetts, by the American Bell Telephone Company against the National Telephone Manufacturing Company et al. And Century Telephone Company et al. Reported in Federal Reporter 109, page 976, a sec. These suits were brought on the Berliner patent, which, it was claimed, covered broadly the electrical transmission of speech by variations of pressure between opposing electrodes in constant contact. The Berliner patent was declared invalid, and in the course of a long and exhaustive opinion, in which the state of art and the work of Bell, Edison, Berliner, and others was fully discussed, the learned judge made the following remarks. The carbon electrode was the invention of Edison. Edison preceded Berliner in the transmission of speech. The carbon transmitter was an experimental invention of a very high order of merit. Edison, by countless experiments, succeeded in advancing the art. That Edison did produce speech with solid electrodes before Berliner is clearly proven. The use of carbon in a transmitter is, beyond controversy, the invention of Edison. Edison was the first to make apparatus in which carbon was used as one of the electrodes. The carbon transmitter displaced Bell's magnetic transmitter, and, under several forms of construction, remained the only commercial instrument. The advance in the art was due to the carbon electrode of Edison. It is conceded that the Edison transmitter as apparatus is a very important invention. An immense amount of painstaking and highly ingenious experiment preceded Edison's successful result. The discovery of the availability of carbon was unquestionably invention, and it resulted in the first practical success in the art. End of Appendix VI.
Appendix VII. Edison's Tasimeter. From Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Comerford Martin. Appendix VII. Edison's Tasimeter. This interesting and remarkable device is one of Edison's many inventions not generally known to the public at large, chiefly because the range of its application has been limited to the higher branches of science. He never applied for a patent on the instrument, but dedicated it to the public. The device was primarily intended for use in detecting and measuring infinitesimal degrees of temperature, however remote, and its conception followed Edison's researches on the carbon telephone transmitter. Its principle depends on the variable resistance of carbon in accordance with the degree of pressure to which it is subjected. By means of this instrument, pressures that are otherwise inappreciable and undiscoverable may be observed and indicated. The detection of small variations of temperatures is brought about through the changes which heat or cold will produce in a sensitive material placed in contact with a carbon button, which is put in circuit with a battery and a delicate galvanometer. In this sketch, Figure 1, there is illustrated, partly in section, the form of tasimeter which Edison took with him to Rawlins, Wyoming, in July 1878, on the expedition to observe the total eclipse of the sun. The substance on whose expansion the working of the instrument depends is a strip of some material extremely sensitive to heat, such as vulcanite, shown at A, and firmly clamped at B. Its lower end fits into a slot in a metal plate, C, which in turn rests upon a carbon button. This latter and the metal plate are connected in an electric circuit, which includes a battery and a sensitive galvanometer. A vulcanite or other strip is easily affected by differences of temperature, expanding and contracting by reason of the minutest changes. Thus, an infinitesimal variation in its length through expansion or contraction changes the pressure on the carbon and affects the resistance of the circuit to a corresponding degree, thereby causing a deflection of the galvanometer, a movement of the needle in one direction denoting expansion and in the other contraction. The strip, A, is first put under a slight pressure, deflecting the needle a few degrees from zero. Any subsequent expansion or contraction of the strip may readily be noted by further movements of the needle. In practice, and for measurements of a very delicate nature, the tasimeter is inserted in one arm of a Wheatstone bridge, as shown at A in the diagram, Figure 2. The galvanometer is shown at B in the bridge wire, and at C, D, and E there are shown the resistances in other arms of the bridge, which are adjusted to equal the resistance of the tasimeter circuit. The battery is shown at F. This arrangement tends to obviate any misleading deflections that might arise through changes in the battery. The dial on the front of the instrument is intended to indicate the exact amount of physical expansion or contraction of the strip. This is ascertained by means of a micrometer screw, S, which moves a needle, T, in front of the dial. This screw engages with a second and similar screw, which is so arranged as to move the strip of vulcanite up or down. After a galvanometer deflection has been obtained through the expansion or contraction of the strip by reason of a change of temperature, a similar deflection is obtained mechanically by turning the screw S one way or the other. This causes the vulcanite strip to press more or less upon the carbon button, and thus produces the desired change in the resistance of the circuit. When the galvanometer shows the desired deflection, the needle, T, will indicate upon the dial, in decimal fractions of an inch, the exact distance through which the strip has been moved. With such an instrument as the above, Edison demonstrated the existence of heat in the corona at the above-mentioned total eclipse of the sun, but exact determinations could not be made at that time, because the tasimeter adjustment was too delicate, and at the best the galvanometer deflections were so marked that they could not be kept within the limits of the scale. The sensitiveness of the instrument may be easily comprehended when it is stated that the heat of the hand 30 feet away from the cone-like funnel of the tasimeter will so affect the galvanometer as to cause the spot of light to leave the scale. This instrument can also be used to indicate minute changes of moisture in the air by substituting a strip of gelatin in place of the vulcanite. When so arranged, a moistened piece of paper held several feet away will cause a minute expansion of the gelatin strip, which affects the pressure on the carbon and causes a variation in the circuit sufficient to throw the spot of light from the galvanometer mirror off the scale. The tasimeter has been used to demonstrate heat from remote stars, suns, such as Arcturus. End of Appendix VII.
Appendix VIII of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix VIII. The Edison Phonograph. The first patent that was ever granted on a device for permanently recording the human voice and other sounds, and for reproducing the same audibly at any future time, was United States Patent Number 200251, issued to Thomas A. Edison on February 19, 1878, the application having been filed December 24, 1877. It is worthy of note that no references whatever were cited against the application while under examination in the Patent Office. This invention, therefore, marked the very beginning of an entirely new art, which, with the new industries attendant upon its development, has since grown to occupy a position of worldwide reputation. That the invention was of a truly fundamental character is also evident from the fact that although all talking machines of today differ very widely in refinement from the first crude but successful phonograph of Edison, their performance is absolutely dependent upon the employment of the principles stated by him in his patent number 200251. Quoting from the specification attached to this patent, we find that Edison said, "The invention consists in arranging a plate, diaphragm, or other flexible body capable of being vibrated by the human voice or other sounds, in conjunction with a material capable of registering the movements of such vibrating body by embossing or indenting or altering such material in such a manner that such register marks will be sufficient to cause a second vibrating plate or body to be set in motion by them, and thus reproduce the motions of the first vibrating body." It will be at once obvious that these words describe perfectly the basic principle of every modern phonograph or other talking machine, irrespective of its manufacture or trade name. Edison's first model of the phonograph is shown in the following illustration. It consisted of a metallic cylinder, having a helical indenting groove cut upon it from end to end. This cylinder was mounted on a shaft supported on two standards. This shaft at one end was fitted with a handle, by means of which the cylinder was rotated. There were two diaphragms, one on each side of the cylinder, one for being recorded and the other for reproducing speech or other sounds. Each diaphragm had attached to it a needle. By means of the needle, attached to the recording diaphragm, indentations were made in a sheet of tinfoil stretched over the peripheral surface of the cylinder when the diaphragm was vibrated by reason of speech or other sounds. The needle on the other diaphragm subsequently followed these indentations, thus reproducing the original sounds. Crude as this first model appears in comparison with machines of later development and refinement, it embodied their fundamental essentials, and was in fact a complete practical phonograph from the first moment of its operation. The next step toward the evolution of the improved phonograph of today was another form of tinfoil machine, as seen in the illustration. It will be noted that this was merely an elaborate form of the first model, and embodied several mechanical modifications, among which was the employment of only one diaphragm for recording and reproducing. Such was the general type of phonograph used for exhibition purposes in America and other countries in the 3 or 4 years immediately succeeding the date of this invention. In operating the machine, the recording diaphragm was advanced nearly to the cylinder, so that, as the diaphragm was vibrated by the voice, the needle would prick or indent a wave-like record in the tinfoil that was on the cylinder. The cylinder was constantly turned during the recording, and in turning was simultaneously moved forward. Thus the record would be formed on the tinfoil in a continuous spiral line. To reproduce this record, it was only necessary to again start at the beginning and cause the needle to retrace its path in the spiral line. The needle, in passing rapidly in contact with the recorded waves, was vibrated up and down, causing corresponding vibrations of the diaphragm. In this way, sound waves similar to those caused by the original sounds would be set up in the air, thus reproducing the original speech. The modern phonograph operates in a precisely similar way, the only difference being details of refinement. Instead of tinfoil, a wax cylinder is employed, the record being cut thereon by a cutting tool attached to a diaphragm, while the reproduction is effected by means of a blunt stylus similarly attached. The cutting tool and stylus are devices made of sapphire, a gem next in hardness to a diamond, and they have to be cut and formed to an exact nicety by means of diamond dust, most of the work being performed under high-powered microscopes. The minute proportions of these devices will be apparent by a glance at the accompanying illustrations, in which the object on the left represents a common pin, and the object on the right the cutting tool and reproducing stylus, all actual sizes. In the next illustration, Figure 4, there is shown in the upper sketch, greatly magnified, the cutting or recording tool in the act of forming the record, being vibrated rapidly by the diaphragm, and in the lower sketch, similarly enlarged, a representation of the stylus travelling over the record thus made, in the act of effecting a reproduction. From the late summer of 1878 and to the fall of 1887, Edison was intensely busy on the electric light, electric railway, and other problems, and virtually gave no attention to the phonograph. Hence, just prior to the latter named period, the instrument was still in its tinfoil age. But he then began to devote serious attention to the development of an improved type that should be of greater commercial importance. The practical results are too well known to call for further comment. That his efforts were not limited in extent may be inferred from the fact that since the fall of 1887 to the present writing he has been granted in the United States 104 patents relating to the phonograph and its accessories. Interesting as the numerous inventions are, it would be a work of supererogation to digest all these patents in the present pages. as they would represent not only the inception but also the gradual development and growth of the wax record type of phonograph from its infancy to its present perfected machine, and records now so widely known all over the world. From among these many inventions, however, we will select 2 or 3 as examples of ingenuity and importance in their bearing upon present perfection of results. One of the difficulties of reproduction for many years was the trouble experienced in keeping the stylus in perfect engagement with the wave-like record, so that every minute vibration would be reproduced. It should be remembered that the deepest cut of the recording tool is only about 1/3 the thickness of tissue paper. Hence it will be quite apparent that the slightest inequality in the surface of the wax would be sufficient to cause false vibration, and thus give rise to distorted effects in such music or other sounds as were being reproduced. To remedy this, Edison added an attachment which is called a floating weight, and is shown at A in the illustration above. The function of the floating weight is to automatically keep the stylus in close engagement with the record, thus ensuring accuracy of reproduction. The weight presses the stylus to its work, but because of its mass cannot respond to the extremely rapid vibrations of the stylus. They are therefore communicated to the diaphragm. Some of Edison's most remarkable inventions are revealed in a number of interesting patents relating to the duplication of phonograph records. It would be obviously impossible, from a commercial standpoint, to obtain a musical record from a high-class artist and sell such an original to the public, as its cost might be from $100 to several $1,000s. Consequently, it is necessary to provide some way by which duplicates be made cheaply enough to permit their purchase by the public at a reasonable price. The making of a perfect original musical or other record is a matter of no small difficulty, as it requires special technical knowledge and skill gathered from many years of actual experience. But in the exact copying or duplication of such a record, with its millions of microscopic waves and subwaves, the difficulties are enormously increased. The duplicates must be microscopically identical with the original. They must be free from false vibrations or other defects, although both original and duplicates are of such easily defaceable material as wax, and the process must be cheap and commercial, not a scientific laboratory possibility. For making duplicates it was obviously necessary to first secure a mould carrying the record in negative or reversed form. From this could be moulded or cast positive copies which would be identical with the original. While the art of electroplating would naturally suggest itself as the means of making such a mould, an apparently insurmountable obstacle appeared on the very threshold. Wax, being a non-conductor, cannot be electroplated unless a conducting surface be first applied. The coatings ordinarily used in electrodeposition were entirely out of the question on account of coarseness, the deep waves of the record being less than 1/1000th of an inch in depth, and many of them probably 10 to 100 times as shallow. Edison finally decided to apply a preliminary metallic coating of infinitesimal thinness, and accomplish this object by a remarkable process known as the vacuous deposit. With this he applied to the original record a film of gold, probably no thicker than 1/300,000th of an inch, or several hundred times less than the depth of an average wave. 300 such layers, placed one on top of the other, would make a sheet no thicker than tissue paper. The process consists in placing in a vacuum 2 leaves or electrodes of gold, and between them the original record. A constant discharge of electricity of high tension between the electrodes is effected by means of an induction coil. The metal is vaporized by this discharge, and is carried by it directly toward and deposited upon the original record, thus forming the minute film of gold above mentioned. The record is constantly rotated until its entire surface is coated. A sectional diagram of the apparatus, Fig. 6, will aid to a clearer understanding of this ingenious process. After the gold film is formed in the manner described above, a heavy backing of baser metal is electroplated upon it, thus forming a substantial mould, from which the original record is extracted by breakage or shrinkage. Duplicate records in any quantity may now be made from this mould by surrounding it with a cold water jacket and dipping it in a molten wax-like material. This congeals on the record surface just as melted butter would collect on a cold knife, and when the mould is removed, the surplus wax falls out, leaving a heavy deposit of the material which forms the duplicate record. Numerous ingenious inventions have been made by Edison, providing for a variety of rapid and economical methods of duplication, including methods of shrinking a newly made copy to facilitate its quick removal from the mould, methods of reaming, of forming ribs on the interior, and for many other important and essential details, which limits of space will not permit of elaboration. Those mentioned above are but fair examples of the persistent and effective work he has done to bring the phonograph to its present state of perfection. In perusing Chapter 10 of the foregoing narrative, the reader undoubtedly noted Edison's clear apprehension of the practical uses of the phonograph, as evidenced by his prophetic utterances in the article written by him for the North American Review in June 1878. In view of the crudity of the instrument at that time, it must be acknowledged that Edison's foresight, as vindicated by later events, was most remarkable. No less remarkable was his intensely practical grasp of mechanical possibilities of future types of the machine, for we find in one of his early patents, No. 1644 of 1878, the disc form of phonograph, which, some 10 to 15 years later, was supposed to be a new development in the art. This disc form was also covered by Edison's application for a United States patent filed in 1879. This application met with some merely minor technical objections in the Patent Office, and seems to have passed into the abandoned class for want of prosecution, probably because of being overlooked in the tremendous pressure arising from his development of his electric lighting system. End of Appendix VIII.
Appendix IX of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Jerome Lawson, January 2008. Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Comerford Martin. Appendix IX, The Incandescent Lamp. Although Edison's contributions to human comfort and progress are extensive in number and extraordinarily vast and comprehensive in scope and variety, the universal verdict of the world points to his incandescent lamp and system of distribution of electrical current as the central and crowning achievements of his life up to this time. This view would seem entirely justifiable when we consider the wonderful changes in the conditions of modern life that have been brought about by the widespread employment of these inventions and the gigantic industries that have grown up and been nourished by their worldwide application. That he was in this instance a true pioneer and creator is evident as we consider the subject, for the United States Patent number 223898, issued to Edison on January 27, 1880, for an incandescent lamp, was of such fundamental character that it opened up an entirely new and tremendously important art, the art of incandescent electric lighting. This statement cannot be successfully controverted, for it has been abundantly verified after many years of costly litigation. If further proof were desired, it is only necessary to point to the fact that, after 30 years of most strenuous and practical application in the art by the keenest intellects in the world, every incandescent lamp that has ever since been made, including those of modern days, is still dependent upon the employment of the essentials disclosed in the above-named patent, namely, a filament of high resistance enclosed in a sealed glass globe exhausted of air, with conducting wires passing through the glass. The incandescent lamp is such a simple-appearing article, merely a filament sealed in a glass globe, that its intrinsic relation to the art of electric lighting is far from being apparent at sight. To the lay mind, it would seem that this must have been the obvious device to make in order to obtain electric light by incandescence of carbon or other material. But the reader has already learned from the preceding narrative that prior to its invention by Edison, such a device was not obvious, even to the most highly trained experts of the world at that period. Indeed, it was so far from being obvious that, for some time after he had completed practical lamps and was actually lighting them up 24 hours a day, such a device and such a result were declared by these same experts to be an utter impossibility. For a short while, the world outside of Menlo Park held Edison's claims in derision. His lamp was pronounced a fake, a myth, possibly a momentary success magnified to the dignity of a permanent device by an overenthusiastic inventor. Such criticism, however, did not disturb Edison. He knew that he had reached the goal. Long ago, by a close process of reasoning, he had clearly seen that the only road to it was through the path he had traveled, and which was now embodied in the philosophy of his incandescent lamp, namely a filament, or carbon, of high resistance and small radiating surface, sealed into a glass globe exhausted of air to a high degree of vacuum. In originally committing himself to this line of investigation, he was well aware that he was going in a direction diametrically opposed to that followed by previous investigators. Their efforts had been confined to low-resistance burners of large radiating surface for their lamps, but he realized the utter futility of such devices. The tremendous problems of heat and the prohibitive quantities of copper that would have been required for conductors of such lamps would be absolutely out of the question in commercial practice. He was convinced from the first that the true solution of the problem lay in a lamp which should have as its illuminating body a strip of material which would offer such a resistance to the flow of electric current that it could be raised to a high temperature, incandescence, and be of such small cross-section that it would radiate but little heat. At the same time, such a lamp must require a relatively small amount of current, in order that comparatively small conductors could be used, and its burner must be capable of withstanding the necessarily high temperatures without disintegration. It is interesting to note that these conceptions were in Edison's mind at an early period of his investigations, when the best expert opinion was that the subdivision of the electric current was an ignis fatuus. Hence we quote the following notes he made, November 15, 1878, in one of the laboratory notebooks. A given straight wire having 1 ohm resistance and certain length is brought to a given degree of temperature by given battery. If the same wire be coiled in such a manner that but 1/4 of its surface radiates, its temperature will be increased 4 times with the same battery, or 1/4 of this battery will bring it to the temperature of straight wire. Or the same given battery will bring a wire whose total resistance is 4 ohms to the same temperature as straight wire. This was actually determined by trial. The amount of heat lost by a body is in proportion to the radiating surface of that body. If 1 square inch of platina be heated to 100 degrees, it will fall to, say, 0 in 1 second, whereas if it was at 200 degrees it would require 2 seconds. Hence, in the case of incandescent conductors, if the radiating surface be 12 inches and the temperature on each inch be 100, or 1200 for all, if it is so coiled or arranged that there is but 1/4 or 3 inches of radiating surface, then the temperature on each inch will be 400. If reduced to 3/4 of an inch, it will have on that 3/4 of an inch 1600 degrees Fahrenheit, notwithstanding the original total amount was but 1200, because the radiation has been reduced to 3/4 or 75 units. Hence, the effect of the lessening of the radiation is to raise the temperature of each remaining inch not radiating to 125 degrees. If the radiating surface should be reduced to 33 seconds of an inch, the temperature would reach 6400 degrees Fahrenheit. To carry out this law to the best advantage in regard to platina, etc., then with a given length of wire to quadruple the heat, we must lessen the radiating surface to 1/4, and to do this in a spiral, 3/4 must be within the spiral and 1/4 outside for radiating. Hence, a square wire or other means, such as a spiral within a spiral, must be used. These results account for the enormous temperatures of the electric arc with 1 horsepower. As for instance, if 1 horsepower will heat 12 inches of wire to 1000 degrees Fahrenheit, and this is concentrated to have 1/4 of the radiating surface, it would reach a temperature of 4000 degrees or sufficient to melt it. But, supposing it infusible, the further concentration to 1/8 its surface, it would reach a temperature of 16,000 degrees, and to 1/32 its surface, which would be about the radiating surface of the electric arc, it would reach 64,000 degrees Fahrenheit. Of course, when light is radiated in great quantities, not quite these temperatures would be reached. Another curious law is this. It will require a greater initial battery to bring an iron wire of the same size and resistance to a given temperature than it will a platinum wire in proportion to their specific heats. And in the case of carbon, a piece of carbon 3 inches long and 1/8 diameter, with a resistance of 1 ohm, will require a greater battery power to bring it to a given temperature than a cylinder of thin platinum foil of the same length, diameter, and resistance, because the specific heat of carbon is many times greater. Besides, if I am not mistaken, the radiation of a roughened body for heat is greater than a polished one like platina. Proceeding logically upon these lines of thought, and following them out through many ramifications, we have seen how he at length made a filament of carbon of high resistance and small radiating surface, and through a concurrent investigation of the phenomena of high vacua and occluded gases, was able to produce a true incandescent lamp. Not only was it a lamp as a mere article, a device to give light, but it was also an integral part of his great and complete structure of lighting, to every part of which it bore a fixed and definite ratio, and in relation to which it was the keystone that held the structure firmly in place. The work of Edison on incandescent lamps did not stop at this fundamental invention, but extended through more than 18 years of a most intense portion of his busy life. During that period he was granted 149 other patents on the lamp and its manufacturer. Although very many of these inventions were of the utmost importance and value, we cannot attempt to offer a detailed exposition of them in this necessarily brief article, but must refer the reader, if interested, to the patents themselves, a full list being given at the end of this appendix. The outline sketch will indicate the principal patents covering the basic features of the lamp. The litigation on the Edison lamp patents was one of the most determined and stubbornly fought contests in the history of modern jurisprudence. Vast interests were at stake. All of the technical, expert, and professional skill and knowledge that money could procure or experience devise were availed of in the bitter fights that raged in the courts for many years. And although the Edison interests had spent from first to last nearly $2 million, and had only about 3 years left in the life of the fundamental patent, Edison was thoroughly sustained as to priority by the decisions in the various suits. We shall offer a few brief extracts from some of these decisions. In a suit against the United States Lighting Company, United States Circuit Court for the Southern District of New York, July 14, 1891, Judge Wallace said, in his opinion, "The futility of hoping to maintain a burner in vacuo with any permanency had discouraged prior inventors, and Mr. Edison is entitled to the credit of obviating the mechanical difficulties which disheartened them. He was the first to make a carbon of materials, and by a process which was especially designed to impart high specific resistance to it. The first to make a carbon in a special form for the special purpose of imparting to it high total resistance, and the first to combine such a burner with the necessary adjuncts of lamp construction to prevent its disintegration and give it sufficiently long life. By doing these things he made a lamp which was practically operative and successful, the embryo of the best lamps now in commercial use, and but for the subdivision of the electric light by incandescence would still be nothing but the ignis fatuus which it was proclaimed to be in 1879 by some of the reamed experts who are now witnesses to belittle his achievement and show that it did not rise to the dignity of an invention. It is impossible to resist the conclusion that the invention of the slender thread of carbon as a substitute for the burners previously employed opened the path to the practical subdivision of the electric light. An appeal was taken in the above suit to the United States Circuit Court of Appeals, and on October 4, 1892, the decree of the lower court was affirmed. The judges, Lacombe and Shipman, in a long opinion reviewed the facts and the art, and said, inter alia, Edison's invention was practically made when he ascertained the theretofore unknown fact that carbon would stand high temperature, even, when very attenuated, if operated in a high vacuum, without the phenomenon of disintegration. This fact he utilized by the means which he has described, a lamp having a filamentary carbon burner in a nearly perfect vacuum. In a suit against the Boston Incandescent Lamp Company et al. In the United States Circuit Court for the District of Massachusetts, decided in favor of Edison on June 11, 1894, Judge Colt, in his opinion, said, among other things, Edison made an important invention. He produced the first practical incandescent electric lamp. The patent is a pioneer in the sense of the patent law. It may be said that his invention created the art of incandescent electric lighting. Opinions of other courts, similar in tenor to the foregoing, may be cited, but it would be merely in the nature of reiteration. The above are sufficient to illustrate the direct clearness of judicial decision on Edison's position as the founder of the art of electric lighting by incandescence. End of Appendix 9. Recording by Jerome Lawson. January 2008.
Appendix 10 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melissa. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix 10. Edison's Dynamo work. At the present writing, when, after the phenomenally rapid electrical development of 30 years, we find on the market a great variety of modern forms of efficient current generators, advertised under the names of different inventors, none, however, bearing the name of Edison, a young electrical engineer of the present generation might well inquire whether the great inventor had ever contributed anything to the art beyond a mere type of machine formerly made and bearing his name, but not now marketed except second-hand. For adequate information he might search in vain the books usually regarded as authorities on the subject of dynamo electric machinery, for with slight exceptions there has been a singular unanimity in the omission of writers to give Edison credit for his great and basic contributions to heavy current technics, although they have been universally acknowledged by scientific and practical men to have laid the foundation for the efficiency of and to be embodied in all modern generators of current. It might naturally be expected that the essential facts of Edison's work would appear on the surface of his numerous patents of dynamo electric machinery, but such is not necessarily the case, unless they were carefully studied in the light of the state of the art as it existed at the time. While some of these patents, especially the earlier ones, cover specific devices embodying fundamental principles that not only survive to the present day, but actually lie at the foundation of the art as it now exists, there is no revelation therein of Edison's preceding studies of magnets, which extended over many years, nor of his later systematic investigations and deductions. Dynamo electric machines of a primitive kind have been invented and were in use to a very limited extent for arc lighting and electroplating for some years prior to the summer of 1819, when Edison, with an embryonic lighting system in mind, cast about for a type of machine technically and commercially suitable for the successful carrying out of his plans. He found absolutely none. On the contrary, all of the few types then obtainable were uneconomical, indeed wasteful, in regard to efficiency. The art, if indeed there can be said to have been an art at that time, was in chaotic confusion, and only because of Edison's many years' study of the magnet was he enabled to conclude that insufficiency in quantity of iron in the magnets of such machines, together with poor surface contacts, rendered the cost of magnetization abnormally high. The heating of solid armatures, the only kind then known, and poor insulation in the commutators also gave rise to serious losses. But perhaps the most serious drawback lay in the high resistance armature, based upon the highest scientific dictum of the time, that in order to obtain the maximum amount of work from a machine, the internal resistance of the armature must equal the resistance of the exterior circuit, although the application of this principle entailed the useless expenditure of at least 50% of the applied energy. It seems almost incredible that a little over 30 years ago, the sum of scientific knowledge in regard to dynamo electric machines was so meager that the experts of the period should settle upon such a dictum as this, but such was the fact, as will presently appear. Mechanical generators of electricity were comparatively new at that time. Their theory and practice were very imperfectly understood. Indeed, it is quite within the bounds of truth to say that the correct principles were befogged by reason of the lack of practical knowledge of their actual use. Electricians and scientists of the period have been accustomed for many years past to look to the chemical battery as the source from which to obtain electrical energy, and in the practical application of such energy to telegraphy and kindred uses, much thought and ingenuity had been expended in studying combinations of connecting such cells so as to get the best results. In the textbooks of the period, it was stated as a settled principle that in order to obtain the maximum work out of a set of batteries, the internal resistance must approximately equal the resistance of the exterior circuit. This principle and its application in practice were quite correct as regards chemical batteries, but not as regards dynamo machines. Both were generators of electrical current, but so different in construction and operation that rules applicable to the practical use of the one did not apply with proper commercial efficiency to the other. At the period under consideration, which may be said to have been just before dawn of the day of electric light, the philosophy of the dynamo had been seen only in mysterious, hazy outlines, just emerging from the darkness of departing night. Perhaps it is not surprising, then, that the dynamo was loosely regarded by electricians as the practical equivalent of a chemical battery, that many of the characteristics of performance of the chemical cell were also attributed to it, and that if the maximum work could be gotten out of a set of batteries when the internal and external resistances were equal, and this was commercially the best thing to do, so must it also be with a dynamo. It was by no miracle that Edison was far and away ahead of his time when he undertook to improve the dynamo. He possessed of absolute knowledge far beyond that of his contemporaries. This he had acquired by the hardest kind of work and incessant experimentation with magnets of all kinds during several years preceding, particularly in connection with his study of automatic telegraphy. His knowledge of magnets was tremendous. He had studied and experimented with electromagnets in enormous variety, and knew their peculiarities in charge and discharge, lag, self-induction, static effects, condenser effects, and various other phenomena connected therewith. He had also made collateral studies of iron, steel, copper, insulation, winding, etc. Hence, by reason of this extensive work and knowledge, Edison was naturally in a position to realize that utter commercial impossibility of the then best dynamo machine in existence, which had an efficiency of only 40% and was constructed on the cut and try principle. He was also naturally in a position to assume the task he set out to accomplish, of undertaking to plan and build an improved type of machine that should be commercial in having an efficiency of at least 90%. Truly a prodigious undertaking in those dark days, when from the standpoint of Edison's large experience, the most practical and correct electrical treatise was contained in the Encyclopaedia Britannica, and in a German publication which Mr. Upton had brought with him after he had finished his studies with the illustrious Helmholtz. It was at this period that Mr. Upton commenced his association with Edison, bringing to the great work the very latest scientific views and the assistance of the higher mathematics, to which he had devoted his attention for several years previously. As some account of Edison's investigations in this connection has already been made in Chapter 12 of the narrative, we shall not enlarge upon them here, but quote from An Historical Review by Charles L. Clark, Laboratory Assistant at Menlo Park, 1880 to 81, Chief Engineer of the Edison Electric Light Company, 1881 to 84. In June 1879 was published the account of the Edison dynamo electric machine that survived in the art. This machine went into extensive commercial use, and was notable for its very massive and powerful field magnets, an armature of extremely low resistance as compared with the combined external resistance of the supply mains and lamps. By means of the large masses of iron in the field magnets, and closely fitted joints between the several parts thereof, the magnetic reluctance of the iron parts of the magnetic circuit was reduced to a minimum, and the required magnetization effected with the maximum economy. At the same time, Mr. Edison announced the commercial necessity of having the armature of the dynamo of low resistance, as compared with the external resistance, in order that a large percentage of the electrical energy developed should be utilized in the lamps, and only a small percentage lost in the armature, albeit this procedure reduced the total generating capacity of the machine. He also proposed to make the resistance of the supply mains small, as compared with the combined resistance of the lamps in multiple arc, in order to still further increase the percentage of energy utilized in the lamps. And likewise to this end, the combined resistance of the generator armatures in multiple arc was kept relatively small by adjusting the number of generators operating in multiple at any time to the number of lamps then in use. The field magnet circuits of the dynamos were connected in multiple with a separate energizing source, and the field current and strength of field were regulated to maintain the required amount of electromotive force upon the supply mains under all conditions of load, from the maximum to the minimum number of lamps in use, and to keep the electromotive force of all machines alike. Among the earliest of Edison's dynamo experiments were those relating to the core of the armature. He realized at once that the heat generated in a solid core was a prolific source of loss. He experimented with bundles of iron wires variously insulated, also with sheet iron rolled cylindrically and covered with iron wire wound concentrically. These experiments and many others were tried in a great variety of ways, until, as the result of all this work, Edison arrived at the principle which has remained in the art to this day. He split up the iron core of the armature into thin laminations, separated by paper, thus practically suppressing Foucault currents therein and resulting heating effect. It was in his machine also that mica was used for the first time as an insulating medium in a commutator. Footnote. The commercial manufacture of built-up sheets of mica for electrical purposes was first established at the Edison Machine Works, Gork Street, New York, in 1881. End footnote. Elementary as these principles will appear to the modern student or engineer, they were denounced as nothing short of absurdity at the time of their promulgation, especially so with regard to Edison's proposal to upset the then settled dictum that the armature resistance should be equal to the external resistance. His proposition was derided in the technical press of the period, both at home and abroad. As public opinion can be best illustrated by actual quotation, we shall present a characteristic instance. In the Scientific American of October 18, 1879, there appeared an illustrated article by Mr. Upton on Edison's dynamo machine, in which Edison's views and claims were set forth. A subsequent issue contained a somewhat acrimonious letter of criticism by a well-known maker of dynamo machines. At the risk of being lengthy, we must quote nearly all this letter. I can scarcely conceive it as possible that the article on the above subject, Edison's electric generator, in last week's Scientific American, could have been written from statements derived from Mr. Edison himself, inasmuch as so many of the advantages claimed for the machine described, and statements of the results obtained, were so manifestly absurd as to indicate on the part of both writer and prompter a positive want of knowledge of the electric circuit and the principles governing the construction and operation of electric machines. It is not my intention to criticize the design or construction of the machine, not because they are not open to criticism, as I am now and have been for many years engaged in the manufacture of electric machines, but rather to call attention to the impossibility of obtaining the described results without destroying the doctrine of the conservation and correlation of forces. It is stated that the internal resistance of the armature of this machine is only 1/2 ohm. On this fact, and the disproportion between this resistance and that of the external circuit, The theory of the alleged efficiency of the machine is stated to be based, for we are informed that, while this generator in general principle is the same as in the best well-known forms, still there is an all-important difference, which is that it will convert and deliver for useful work nearly double the number of foot-pounds that any other machine will under like conditions. The writer of this critical letter then proceeds to quote Mr. Upton's statement of this efficiency. Now the energy converted is distributed over the whole resistance. Hence, if the resistance of the machine be represented by 1, and the exterior circuit by 9, then of the total energy converted, 9/10 will be useful, as it is outside of the machine, and 1/10 is lost in the resistance of the machine. After this, the critic goes on to say, how anyone acquainted with the laws of the electric circuit can make such statements is what I cannot understand. The statement last quoted is mathematically absurd. It implies either that the machine is capable of increasing its own electromotive forces 9 times without an increased expenditure of power, or that external resistance is not resistance to the current induced in the Edison machine. Does Mr. Edison, or anyone for him, mean to say that little r divided by n enables him to obtain n times E, and that C is not equal to E divided by the quantity of little r divided by n plus big R? If so, Mr. Edison has discovered something more than perpetual motion, and Mr. Keeley had better retire from the field. Further on, the writer, Mr. Upton, gives us another example of this mode of reasoning, when emboldened and satisfied with the absurd theory above exposed, he endeavors to prove the cause of the inefficiency of the Siemens and other machines. Couldn't the writer of the article see that since C equals E divided by the quantity of little r plus big R, that by big R divided by n, or by making big R equal little r, the machine would, according to his theory, have returned more useful current to the circuit than could be due to the power employed, and in the ratio indicated, so that there would actually be a creation of force. In conclusion, allow me to say that if Mr. Edison thinks he has accomplished so much by the reduction of the internal resistance of his machine, that he has much more to do in this direction before his machine will equal in this respect others already in the market. Another participant in the controversy on Edison's generator was a scientific gentleman, who in a long article published in the Scientific American in November 1879, gravely undertook to instruct Edison in the ABC of electrical principles, and then proceeded to demonstrate mathematically the impossibility of doing what Edison had actually done. This critic concludes with a gentle rebuke to the inventor for ill-timed jesting, and a suggestion to furnish authentic information. In the light of facts, as they were and are, this article is so full of humor that we shall indulge in a few quotations. It commences in ABC fashion as follows. Electrical machines convert mechanical into electrical energy. The ratio of yield to consumption is the expression of the efficiency of the machine. How many foot-pounds of electricity can be got out of 100 foot-pounds of mechanical energy? Certainly not more than 100. Certainly less. The facts and laws of physics, with the assistance of mathematical logic, never fail to furnish precious answers to such questions. The would-be critic then goes on to tabulate tests of certain other dynamo machines by a committee of the Franklin Institute in 1879, the results of which showed that these machines returned about 50% of the applied mechanical energy, ingeniously remarking, why is it that when we have produced the electricity, half of it must slip away? Some persons will be content if they are told simply that it is a way which electricity has of behaving. But there is a satisfactory, rational explanation which I believe can be made plain to persons of ordinary intelligence. It ought to be known to all those who are making or using machines. I am grieved to observe that many persons who talk and write glibly about electricity do not understand it. Some even ignore or deny the fact to be explained. Here followed his explanation, after which he goes on to say, at this point plausibly comes in a suggestion that the internal part of the circuit be made very small and the external part very large.
Why not, say, make the internal part 1 and the external 9, thus saving 9/10 and losing only 1/10? Unfortunately, this suggestion is not practical. A fallacy is concealed in it. He then goes on to prove his case mathematically, to his own satisfaction, following it sadly by condoling with, and a warning to Edison. But about Edison's electric generator, no one capable of making the improvements in the telegraph and telephone, for which we are indebted to Mr. Edison, could be other than an accomplished electrician. His reputation as a scientist, indeed, is besmirched by the newspaper exaggerations, and no doubt he will be more careful in future. But there is a danger nearer home, indeed in his very household. The writer of page 242, the original article, is probably a friend of Mr. Edison, but possibly, alas, a wicked partner. Why does he say such things as these? Mr. Edison claims that he realizes 90% of the power applied to his machine in external work. Perhaps the writer is a humorist, and had in his mind Colonel Sanders, etc., which he could not keep out of a serious discussion. But such jests are not good. Mr. Edison has built a very interesting machine, and he has the opportunity of making a valuable contribution to the electrical arts by furnishing authentic accounts of its capabilities. The foregoing extracts are unavoidably lengthy, but viewed in the light of facts, serve to illustrate most clearly that Edison's conceptions and work were far and away ahead of the comprehension of his contemporaries in the art, and that his achievements in the line of efficient dynamo design and construction were indeed truly fundamental and revolutionary in character. Much more of similar nature to the above could be quoted from other articles published elsewhere, but the foregoing will serve as instances, generally representing all. In the controversy which appeared in the columns of the Scientific American, Mr. Upton, Edison's mathematician, took up the question on his side, and answered the critics by further elucidations of the principles on which Edison had founded such remarkable and radical improvements in the art. The type of Edison's first dynamo-electric machine, the description of which gave rise to the above controversy, is shown in Figure 1. Any account of Edison's work on the dynamo would be incomplete did it omit to relate his conception and construction of the great, direct-connected, steam-driven generator that was the prototype of the colossal units which are used throughout the world today. In the demonstrating plant installed and operated by him at Menlo Park in 1880, 10 dynamos of 8 horsepower each were driven by a slow-speed engine through a complicated system of countershafting, and to quote from Mr. Clark's Historical Review, it was found that a considerable percentage of the power of the engine was necessarily wasted in friction by this method of driving, and to prevent this waste, and thus increase the economy of his system, Mr. Edison conceived the idea of substituting a single large dynamo for the several small dynamos, and directly coupling it with the driving engine, and at the same time preserve the requisite high armature speed by using an engine of the high-speed type. He also expected to realize still further gains in economy from the use of a large dynamo in place of several small machines by a more than correspondingly lower armature resistance, less energy for magnetizing the field, and for other minor reasons. To the same end, he intended to supply steam to the engine under a much higher boiler pressure than was customary in stationary engine driving at that time. The construction of the first one of these large machines was commenced late in the year 1880. Early in 1881 it was completed and tested, but some radical defects in armature construction were developed, and it was also demonstrated that a rate of engine speed too high for continuously safe and economical operation had been chosen. The machine was laid aside. An accurate illustration of this machine, as it stood in the engine room at Menlo Park, is given in Van Nostrand's Engineering Magazine, Volume 25, opposite page 439, and a brief description is given on page 450. With the experience thus gained, Edison began, in the spring of 1881, at the Edison Machine Works, Gork Street, New York City, the construction of the first successful machine of this type. This was the great machine known as Jumbo No. 1, which is referred to in the narrative as having been exhibited at the Paris International Electrical Exposition, where it was regarded as the wonder of the electrical world. An intimation of some of the tremendous difficulties encountered in the construction of this machine has already been given in preceding pages, hence we shall not now enlarge on the subject, except to note in passing that the terribly destructive effects of the spark of self-induction and the arcing following it were first manifested in this powerful machine, but were finally overcome by Edison after a strenuous application of his powers to the solution of the problem. It may be of interest, however, to mention some of its dimensions and electrical characteristics, quoting again from Mr. Clark. The field magnet has 8 solid cylindrical cores, 8 inches in diameter and 57 inches long, upon each of which was wound an exciting coil of 3.2 ohms resistance, consisting of 2,184 turns of No. 10 BWG insulated copper wire, disposed in 6 layers. The laminated iron core of the armature, formed of thin iron discs, was 33 3/4 inches long, and had an internal diameter of 12.5 inches and an external diameter of 26 7/16 inches. It was mounted on a 6-inch shaft. The field poles are 33 3/4 inches long and 27.5 inches inside diameter. The armature winding consisted of 146 copper bars on the face of the core, connected into a closed coil winding by means of 73 copper discs at each end of the core. The cross-sectional area of each bar was 0.2 square inch, their average length was 42.7 inches, and the copper end discs were 0.065 inches thick. The commutator had 73 sections. The armature resistance was 0.0092 ohm, of which 0.0055 ohm was in the armature bars and 0.0037 ohm in the end discs. An illustration of the next latest type of this machine is presented in Figure 2. Begin footnote. Had Edison, in Upton's Scientific American article in 1879, proposed such an exceedingly low armature resistance for this immense generator, although its ratio was proportionate to the original machine, his critics might possibly have been sufficiently indignant as to be unable to express themselves coherently. End footnote. The student may find it interesting to look up Edison's United States patent numbers 242,898, 263,133, 263,146, and 246,647, bearing upon the construction of the jumbo. Also, illustrated articles in the technical journals of the time, among which may be mentioned Scientific American, Volume 45, page 367, Engineering, London, Volume 32, pages 409 and 419, the Telegraphic Journal and Electrical Review, London, Volume 9, pages 431 through 433 and 436 through 446, La Nature, Paris, 9th year, Part 2, pages 408 through 409, Zeitschrift für angewandte Elektrizitätslehre, Munich and Leipzig, Volume 4, pages 4 through 14, and Drudge's Electrical Illumination, 1882, Volume 1, page 261. The further development of these great machines later on, and their extensive practical use, are well known and need no further comment, except in passing it may be noted that subsequent machines had each a capacity of 1,200 lamps of 16-candle power, and that the armature resistance was still further reduced to 0.0039 ohm. Edison's clear insight into the future, as illustrated by his persistent advocacy of large direct-connected generating machines, is abundantly vindicated by present-day practice. His jumbo machines of 175 horsepower, so enormous for their time, have served as prototypes, and have been succeeded by generators which have constantly grown in size and capacity, until at this time, 1910, it is not uncommon to employ such generating units of a capacity of 14,000 kilowatts, or about 18,666 horsepower. We have not entered into specific descriptions of the many other forms of dynamo machines invented by Edison, such as the multipolar, the disc dynamo, and the armature with 2 windings, for substation distribution. Indeed, it is not possible within our limited space to present even a brief digest of Edison's great and comprehensive work on the dynamo-electric machine, as embodied in his extensive experiments and in over 100 patents granted to him. We have therefore confined ourselves to the indication of a few salient and basic features, leaving it to the interested student to examine the patents and the technical literature of the long period of time over which Edison's labors were extended. Although he has not given any attention to the subject of generators for many years, an interesting instance of his incisive method for overcoming minor difficulties occurred while the present volumes were under preparation, 1910. Carbon for commutator brushes had been superseded by graphite in some cases, the latter material being found much more advantageous electrically. Trouble developed, however, for the reason that while carbon was hard and would wear away the mica insulation simultaneously with the copper, graphite, being softer, would wear away only the copper, leaving ridges of mica, and thus causing sparking through unequal contact. At this point, Edison was asked to diagnose the trouble and provide a remedy. He suggested the cutting out of the mica pieces almost to the bottom, leaving the commutator bars separated by air spaces. This scheme was objected to on the ground that particles of graphite would fill these air spaces and cause a short circuit. His answer was that the air spaces constituted the value of his plan, as the particles of graphite falling into them would be thrown out by the action of centrifugal force as the commutator revolved. And thus it occurred as a matter of fact, and the trouble was remedied. This idea was subsequently adopted by a great manufacturer of generators. End of Appendix X. Recording by Melissa.
Appendix XI of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melissa. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix 11. The Edison Feeder System. To quote from the preamble of the specifications of United States Patent Number 264,642, issued to Thomas A. Edison September 19, 1882, this invention relates to a method of equalizing the tension, or pressure, of the current through an entire system of electric lighting or other translation of electric force, preventing what is ordinarily known as a drop in those portions of the system the more remote from the central station. The problem which was solved by the Edison feeder system was that relating to the equal distribution of current on a large scale over extended areas, in order that a constant and uniform electrical pressure could be maintained in every part of the distribution area without prohibitory expenditure for copper for mains and conductors. This problem had a twofold aspect, although each side was inseparably bound up in the other. On the one hand, it was obviously necessary in a lighting system that each lamp should be of a standard candle power, and capable of interchangeable use on any part of the system, giving the same degree of illumination at every point, whether near to or remote from the source of electrical energy. On the other hand, this must be accomplished by means of a system of conductors so devised and arranged that while they would ensure the equal pressure thus demanded, their mass and consequent cost would not exceed the bounds of practical and commercially economical investment. The great importance of this invention can be better understood and appreciated by a brief glance at the state of the art in 1878 to 79, when Edison was conducting the final series of investigations which culminated in his invention of the incandescent lamp and system of lighting. At this time, and for some years previously, the scientific world had been working on the subdivision of the electric light, as it was then termed. Some leading authorities pronounced it absolutely impossible of achievement on any extended scale, while a very few others, of more optimistic mind, could see no gleam of light through the darkness, but confidently hoped for future developments by such workers as Edison. The earlier investigators, including those up to the period above named, thought of the problem as involving the subdivision of a fixed unit of current, which, being sufficient to cause illumination by one large lamp, might be divided into a number of smaller units whose aggregate light would equal the candle power of this large lamp. It was found, however, in their experiments, that the contrary effect was produced, for with every additional lamp introduced in the circuit, the total candle power decreased instead of increasing. If they were placed in series, the light varied inversely as the square of the number of lamps in circuit, while if they were inserted in multiple arc, the light diminished as the cube of the number in circuit. The idea of maintaining a constant potential and of proportioning the current to the number of lamps in circuit did not occur to most of these early investigators as a feasible method of overcoming the supposed difficulty. Footnote. M. Fontaine, in his book on electric lighting, 1877, showed that with the current of a battery composed of 16 elements, one lamp gave an illumination equal to 54 burners, whereas two similar lamps, if introduced in parallel or multiple arc, gave the light of only 6½ burners in all, 3 lamps of only 2 burners in all, 4 lamps of only 3/4 of 1 burner, and 5 lamps of 1/4 of a burner. End footnote. It would also seem that although the general method of placing experimental lamps in multiple arc was known at this period, the idea of drop of electrical pressure was imperfectly understood, if indeed realized at all, as the most important item to be considered in attempting the solution of the problem. As a matter of fact, the investigators preceding Edison do not seem to have conceived the idea of a system at all. Hence it is not surprising to find them far astray from the correct theory of subdivision of the electric current. It may easily be believed that the term subdivision was a misleading one to these early experimenters. For a very short time Edison also was thus misled, but as soon as he perceived that the problem was one involving the multiplication of current units, his broad conception of a system was born. Generally speaking, all conductors of electricity offer more or less resistance to the passage of current through them, and in the technical terminology of electrical science, the word drop, when used in reference to a system of distribution, is used to indicate a fall or a loss of initial electrical pressure arising from the resistance offered by the copper conductors leading from the source of energy to the lamps. The result of this resistance is to convert or translate a portion of the electrical energy into another form, namely heat, which in the conductors is useless and wasteful and to some extent inevitable in practice, but is to be avoided and remedied as far as possible. It is true that in an electric lighting system there is also a fall or loss of electrical pressure which occurs in overcoming the much greater resistance of the filament in an incandescent lamp. In this case there is also a translation of the energy, but here it accomplishes a useful purpose, as the energy is converted into the form of light through the incandescence of the filament. Such a conversion is called work, as distinguished from drop, although a fall of initial electrical pressure is involved in each case. The percentage of drop varies according to the quantity of copper used in conductors, both as to cross-section and length. The smaller the cross-sectional area, the greater the percentage of drop. The practical effect of this drop would be a loss of illumination in the lamps as we go further away from the source of energy. This may be illustrated by a simple diagram in which G is a generator, or source of energy, furnishing current at a potential or electrical pressure of 110 volts. 1 and 2 are main conductors, from which 110-volt lamps, L, are taken in derived circuits. It will be understood that the circuits represented in Figure 1 are theoretically supposed to extend over a large area. The main conductors are sufficiently large in cross-section to offer but little resistance in those parts which are comparatively near the generator, but as the current traverses their extended length, there is a gradual increase of resistance to overcome, and consequently the drop increases, as shown by the figures. The result of the drop in such a case would be that while the two lamps or groups nearest the generator would be burning at their proper degree of illumination, those beyond would give lower and lower candle power, successively, until the last lamp or group would be giving only about 2/3 the light of the first two. In other words, a very slight drop in voltage means a disproportionately great loss in illumination. Hence, by using a primitive system of distribution, such as that shown by Figure 1, the initial voltage would have to be so high, in order to obtain the proper candle power at the end of the circuit, that the lamps nearest the generator would be dangerously overheated. It might be suggested as a solution of this problem that lamps of different voltages could be used. But as we are considering systems of extended distribution employing vast numbers of lamps, as in New York City where millions are in use, it will be seen that such a method would lead to inextricable confusion, and therefore be absolutely out of the question. Inasmuch as the percentage of drop decreases in proportion to the increased cross-sections of the conductors, the only feasible plan would seem to be to increase their size to such dimensions as to eliminate the drop altogether, beginning with conductors of large cross-section and tapering off as necessary. This would indeed obviate the trouble, but on the other hand would give rise to a much more serious difficulty, namely, the enormous outlay for copper, an outlay so great as to be absolutely prohibitory in considering the electric lighting of large districts, as now practised. Another diagram will probably make this more clear. The reference figures are used as before, except that the horizontal lines extending from square marked G represent the main conductors. As each lamp requires and takes its own proportion of the total current generated, it is obvious that the size of the conductors to carry the current for a number of lamps must be as large as the sum of all the separate conductors which would be required to carry the necessary amount of current to each lamp separately. Hence, in a primitive multi-arc system, it was found that the system must have conductors of a size equal to the aggregate of the individual conductors necessary for every lamp. Such conductors might either be separate, as shown above, Figure 2, or be bunched together, or made into a solid tapering conductor, as shown in the following figure. The enormous mass of copper needed in such a system can be better appreciated by a concrete example. Some years ago, Mr. W. J. Jenks made a comparative calculation which showed that such a system of conductors, known as the tree system, to supply 8,640 lamps in a territory extending over so small an area as 9 city blocks, would require 803,250 pounds of copper, which at the then price of 25 cents per pound would cost $200,812.50. Such in brief was the state of the art, generally speaking, at the period above named, 1878 to 79. As early in the art as the latter end of the year 1878, Edison had developed his ideas sufficiently to determine that the problem of electric illumination by small units could be solved by using incandescent lamps of high resistance and small radiating surface, and by distributing currents of constant potential thereto in multiple arc by means of a ramification of conductors, starting from a central source and branching therefrom in every direction. This was an equivalent of the method illustrated in Figure 3, known as the tree system, and was, in fact, the system used by Edison in the first and famous exhibition of his electric light at Menlo Park around the Christmas period of 1879. He realized, however, that the enormous investment for copper would militate against the commercial adoption of electric lighting on an extended scale. His next inventive step covered the division of a large city district into a number of small substations, supplying current through an interconnected network of conductors, thus reducing expenditure for copper to some extent, because each distribution unit was small and limited the drop. His next development was the radical advancement of the state-of-the-art to the feeder system, covered by the patent now under discussion. This invention swept away the tree and other systems, and at one bound brought into being the possibility of effectively distributing large currents over extended areas with a commercially reasonable investment for copper. The fundamental principles of this invention were, first, to sever entirely any direct connection of the main conductors with the source of energy, and second, to feed current at a constant potential to central points in such main conductors by means of other conductors, called feeders, which were to be connected directly with the source of energy at the central station. This idea will be made more clear by reference to the following simple diagram, in which the same letters are used as before, with additions. In further elucidation of the diagram, it may be considered that the mains are laid in the street along a city block, more or less distant from the station, while the feeders are connected at one end with the source of energy at the station, their other extremities being connected to the mains at central points of distribution. Of course, this system was intended to be applied in every part of a district to be supplied with current, separate sets of feeders running out from the station to the various centers. The distribution mains were to be of sufficiently large size that between their most extreme points the loss would not be more than 3 volts. Such a slight difference would not make an appreciable variation in the candle power of the lamps. By the application of these principles, the inevitable but useless loss, or drop, required by economy might be incurred, but was localized in the feeders, where it would not affect the uniformity of illumination of the lamps in any of the circuits, whether near to or remote from the station, because any variations of loss in the feeders would not give rise to similar fluctuations in any lamp circuit. The feeders might be operated at any desired percentage of loss that would realize economy in copper, so long as they delivered current to the main conductors at the potential represented by the average voltage of the lamps. Thus, the feeders could be made comparatively small in cross-section. It will be at once appreciated that, inasmuch as the mains required to be laid only along the blocks to be lighted, and were not required to be run all the way to the central station, which might be half a mile or more away, the saving of copper by Edison's feeder system was enormous. Indeed, the comparative calculation of Mr. Jenks, above referred to, shows that to operate the same number of lights in the same extended area of territory, the feeder system would require only 128,739 pounds of copper, which, at the then price of 25 cents per pound, would cost only $39,185,000, or a savings of $168,627.50 for copper in this very small district of only 9 blocks. An additional illustration, appealing to the eye, is presented in the following sketch, in which the comparative masses of copper of the tree and feeder systems for carrying the same current are shown side by side. End of Appendix XI.
Appendix XII of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix XII, the 3-wire system. This invention is covered by United States Patent Number 274290, issued to Edison on March 20th, 1883. The object of the invention was to provide for increased economy in the quantity of copper employed for the main conductors in electric light and power installations of considerable extent, at the same time preserving separate and independent control of each lamp, motor, or other translating device upon any one of the various distribution circuits. Immediately prior to this invention, the highest state of the art of electrical distribution was represented by Edison's feeder system, which has already been described as a straight parallel or multiple arc system, wherein economy of copper was obtained by using separate sets of conductors, minus load, feeding current at standard potential or electrical pressure to the mains at centers of distribution. It should be borne in mind that the incandescent lamp, which was accepted at the time as a standard, and has so remained to the present day, was a lamp of 110 volts or thereabouts. In using the word standard, therefore, it is intended that the same shall apply to lamps of about that voltage, as well as to electrical circuits of the approximate potential to operate them. Briefly stated, the principle involved in the three-wire system is to provide main circuits of double the standard potential so as to operate standard lamps or other translating devices in multiple series of 2 to each series, and for the purpose of securing independent, individual control of each unit, to divide each main circuit into any desired number of derived circuits of standard potential, properly balanced, by means of a central compensating conductor which would be normally neutral, but designed to carry any minor excess of current that might flow by reason of any temporary unbalancing of either side of the main circuit. Reference to the following diagrams will elucidate this principle more clearly than words alone can do. For the purpose of increased lucidity, we will first show a plain multiple series system. In this diagram, G1S and G2S represent two generators, each producing current at a potential of 110 volts. By connecting them in series, this potential is doubled, thus providing a main circuit, P and N, of 220 volts. The figures marked L represent 8 lamps of 110 volts each, in multiple series of 2 in 4 derived circuits. The arrows indicate the flow of current. By this means each pair of lamps takes, together, only the same quantity or volume of current required by a single lamp in a single multiple arc system, and as the cross-section of a conductor depends upon the quantity of current carried, such an arrangement as the above would allow the use of conductors of only 1/4 the cross-section that would otherwise be required. From the standpoint of economy of investment, such an arrangement would be highly desirable, but considered commercially it is impractical, because the principle of independent control of each unit would be lost, as the turning out of a lamp in any series would mean the extinguishment of its companion also. By referring to the diagram, it will be seen that each series of 2 forms one continuous path between the main conductors, and if this path be broken at any one point, current will immediately cease to flow in that particular series. Edison, by his invention of the three-wire system, overcame this difficulty entirely, and at the same time conserved approximately the saving of copper, as will be apparent from the following illustration of that system in its simplest form. The reference figures are similar to those in the preceding diagram, and all conditions are also alike, except that a central compensating or balancing conductor, Pn, is here introduced. This is technically termed the neutral wire, and in the discharge of its functions lies the solution of the problem of economical distribution. Theoretically, a three-wire installation is evenly balanced by wiring for an equal number of lamps on both sides. If all these lamps were always lighted, burned, and extinguished simultaneously, the central conductor would, in fact, remain neutral, as there would be no current passing through it, except from lamp to lamp. In practice, however, no such perfect conditions can obtain, hence the necessity of the provision for balancing in order to maintain the principle of independent control of each unit. It will be apparent that the arrangement shown in Figure 2 comprises practically two circuits combined in one system, in which the central conductor, Pn, in case of emergency, serves in two capacities, namely as negative to generator, G1s, or as a positive to generator, G2s, although normally neutral. There are two sides to the system, the positive side being represented by the conductors P and Pn, and the negative side by the conductors Pn and N. Each side, if considered separately, has a potential of about 110 volts, yet the potential of the two outside conductors, P and N, is 220 volts. The lamps are 110 volts. In practical use, the operation of the system is as follows. If all the lamps were lighted, the current would flow along P and through each pair of lamps to N, and so back to the source of energy. In this case, the balance is preserved and the central wire remains neutral, as no return current flows through it to the source of energy. But let us suppose that one lamp on the positive side is extinguished. None of the other lamps is affected thereby, but the system is immediately thrown out of balance. And on the positive side, there is an excess of current to this extent which flows along or through the central conductor and returns to the generator, the central conductor thus becoming the negative of that side of the system for the time being. If the lamp extinguished had been one of those on the negative side of the system, results of a similar nature would obtain, except that the central conductor would for the time being become the positive of that side, and the excess of current would flow through the negative, N, back to the source of energy. Thus it will be seen that a three-wire system, considered as a whole, is elastic, in that it may operate as one when in balance and as two when unbalanced, but in either event giving independent control of each unit. For simplicity of illustration, a limited number of circuits, shown in Figure 2, has been employed. In practice, however, where great numbers of lamps are in use, as for instance in New York City, where about 7 million lamps are operated from various central stations, there is constantly occurring more or less change in the balance of many circuits extending over considerable distances, but of course there is a net result which is always on one side of the system or the other for the time being, and this is met by proper adjustment at the opposite generator in the station. In order to make the explanation complete, there is presented another diagram showing a three-wire system unbalanced. The reference figures are used as before, but in this case the vertical lines represent branches taken from the main conductors into buildings or other spaces to be lighted, and the loops between these branch wires represent lamps in operation. It will be seen from this sketch that there are 10 lamps on the positive side and 12 on the negative. Hence, the net result is an excess of current equal to that required by 2 lamps flowing through the central or compensating conductor, which is now acting as positive to generator G2s. The arrows show the assumed direction of flow of current throughout the system, and the small figures at the arrow heads the volume of that current expressed in the number of lamps which it supplies. The commercial value of this invention may be appreciated from the fact that the application of its principles there is effected a savings of 62.5% of the amount of copper over that which would be required for conductors in any previously devised two-wire system carrying the same load. This arises from the fact that by the doubling of potential the two outside mains are reduced to 1/4 the cross-section otherwise necessary. A saving of 75% would thus be assured, but the addition of a third or compensating conductor of the same cross-section as one of the outside mains reduces the total saving to 62.5%. The three-wire system is in universal use throughout the world at the present day. End of Appendix XII.
And good morning. Appendix XIII of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Heidi Preuss. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix XIII. Edison's Electric Railway. As narrated in Chapter 18, there were 2 electric railroads installed by Edison at Menlo Park, one in 1880, originally 1/3 of a mile long, but subsequently increased to about a mile in length, and the other in 1882, about 3 miles long. As the 1880 road was built very soon after Edison's notable improvements in dynamo machines, and as the art of operating them to the best advantage was then being developed, this early road was somewhat crude as compared with the railroad of 1882, but both were practicable and serviceable for the purpose of hauling passengers and freight. The scope of the present article will be confined to a description of the technical details of these 2 installations. The illustration opposite page 454 of the preceding narrative shows the first Edison locomotive and train of 1880 at Menlo Park. For the locomotive, a 4-wheel iron truck was used, and upon it was mounted one of the long Z-type 110-volt Edison dynamos with a capacity of 75 amperes, which was to be used as a motor. This machine was laid on its side, its armature being horizontal and located toward the front of the locomotive. We now quote from an article by Mr. E. W. Hammer, published in The Electrical World, New York, June 10, 1899, and afterwards elaborated and reprinted in a volume entitled Edisonia, compiled and published under the auspices of a committee of the Association of Edison Illuminating Companies in 1904. The gearing, originally employed, consisted of a friction pulley upon the armature shaft, another friction pulley upon the driven axle, and a 3rd friction pulley which could be brought in contact with the other 2 by a suitable lever. Each wheel of the locomotive was made with metallic rim and a center portion made of wood or papier-mâché. A 3-legged spider connected the metal rim of each front wheel to a brass hub upon which rested a collecting brush. The other wheels were subsequently so equipped. It was the intention, therefore, that the current should enter the locomotive wheels at one side, and after passing through the metal spiders, collecting brushes, and motor, would pass out through the corresponding brushes, spiders, and wheels to the other rail. As to the road, the rails were light and were spiked to ordinary sleepers with a gauge of about 3 1/2 feet. The sleepers were laid upon the natural grade, and there was comparatively no effort made to ballast the road. No special precautions were taken to insulate the rails from the earth or from each other. The road started about 50 feet away from the generating station, which in this case was the machine shop. 2 of the Z-type dynamos were used for generating the current, which was conveyed to the 2 rails of the road by underground conductors. On Thursday, May 13, 1880, at 4 o'clock in the afternoon, this historic locomotive made its first trip, packed with as many of the boys as could possibly find a place to hang on. Everything worked to a charm until, in starting up at one end of the road, the friction gearing was brought into action too suddenly, and it was wrecked. This accident demonstrated that some other method of connecting the armature with the driven axle should be arranged. As thus originally operated, the motor had its field circuit in permanent connection as a shunt across the rails, and this field circuit was protected by a safety catch made by turning up 2 bare ends of the wire in its circuit and winding a piece of fine copper wire across from one bare end to the other. The armature circuit had a switch in it which permitted the locomotive to be reversed by reversing the direction of current flow through the armature. After some consideration of the gearing question, it was decided to employ belts instead of the friction pulleys. Accordingly, Edison installed on the locomotive a system of belting, including an idler pulley which was used by means of a lever to tighten the main driving belt, and thus power was applied to the driven axle. This involved some slipping and consequent burning of belts. Also, if the belt were prematurely tightened, the burning out of the armature. This latter event happened a number of times, and proved to be such a serious annoyance that resistance boxes were brought out from the laboratory and placed upon the locomotive in series with the armature. This solved the difficulty. The locomotive would be started with these resistance boxes in circuit, and after reaching full speed, the operator could plug the various boxes out of circuit and in that way increase the speed. To stop, the armature circuit was opened by the main switch and the brake applied. This arrangement was generally satisfactory, but the resistance boxes scattered about the platform and footrests being in the way, Edison directed that some number 8 B and S copper wire be wound on the lower leg of the motor field magnet. By doing this, the resistance was put where it would take up the least room, and where it would serve as an additional field coil when starting the motor, and it replaced all the resistance boxes which had heretofore been in plain sight. The boxes under the seat were still retained in service. The coil of coarse wire was in series with the armature, just as the resistance boxes had been, and could be plugged in or out of circuit at the will of the locomotive driver. The general arrangement thus secured was operated as long as this road was in commission. On this short stretch of road there were many sharp curves and steep grades, and in consequence of the high speed attained, as high as 42 miles an hour, several derailments took place, but fortunately without serious results. 3 cars were in service during the entire time of operating this 1880 railroad, 1 a flat car for freight, 1 an open car with 2 benches placed back to back, and the 3rd a box car, familiarly known as the Pullman. This latter car had an interesting adjunct in an electric braking system, covered by Edison's patent number 248430. Each car axle had a large iron disc mounted on and revolving with it between the poles of a powerful horseshoe electromagnet. The pole pieces of the magnet were movable and would be attracted to the revolving disc when the magnet was energized, grasping the same and acting to retard the revolution of the car axle. Interesting articles on Edison's first electric railroad were published in the technical and other papers, among which may be mentioned the New York Herald, May 15 and July 23, 1880, the New York Graphic, July 27, 1880, and the Scientific American, June 6, 1880. Edison's second electric railroad of 1882 was more pretentious as regards length, construction, and equipment. It was about 3 miles long, of nearly standard gauge, and substantially constructed. Curves were modified, and grades eliminated where possible by the erection of numerous trestles. This road also had some features of conventional railroads, such as sidings, turntables, freight platform, and car house. Current was supplied to the road by underground feeder cables from the dynamo room of the laboratory. The rails were insulated from the ties by giving them 2 coats of Japan, baking them in the oven, and then placing them on pads of tar-impregnated muslin laid on the ties. The ends of the ties were not japanned, but were electroplated to give good contact surfaces for fish plates and copper bonds. The following notes of Mr. Frederick A. Scheffler, who designed the passenger locomotive for the 1882 road, throw an interesting light on its technical details. By May 1881, I was engaged by Mr. M. F. Moore, who was the first general manager of the Edison Company for isolated lighting, as a draftsman to undertake the work of designing and building Edison's electric locomotive No. 2. Previous to that time, I had been employed in the engineering department of Grant Locomotive Works, Paterson, New Jersey, and the Rhode Island Locomotive Works, Providence, Rhode Island. It was Mr. Edison's idea, as I understood it at the time, to build a locomotive along the general lines of steam locomotives, at least in outward appearance, and to combine in that respect the framework, truck, and other parts known to be satisfactory in steam locomotives at the same time. This naturally required the services of a draftsman accustomed to steam locomotive practice. Mr. Moore was a man of great railroad and locomotive experience, and his knowledge in that direction was of great assistance in the designing and building of this locomotive. At that time I had no knowledge of electricity. One could count so-called electrical engineers on his fingers then, and have some fingers left over. Consequently, the electrical equipment was designed by Mr. Edison and his assistants. The data and parts, such as motor, rheostat, switches, etc., were given to me, and my work was to design the supporting frame, axles, countershafts, driving mechanism, speed control, wheels, and boxes, cab, running board, pilot or cowcatcher, buffers, and even supports for the headlight. I believe I also designed a bell and supports. From this it will be seen that the locomotive had all the essential paraphernalia to make it look like a steam locomotive. The principal part of the outfit was the electric motor. At that time motors were curiosities. There were no electric motors, even for stationary purposes, except freaks built for experimental uses. This motor was made from the parts, such as fields, armature, communicator, shaft, and bearings, etc., of an Edison Z, or 60 light, dynamo. It was the only size of dynamo that the Edison Company had marketed at that time. As a motor, it was wound to run at maximum speed to develop a torque equal to about 15 horsepower with 220 volts. At the generating station at Menlo Park, 4 Z dynamos of 110 volts were used, connected 2 in series in multiple arc, giving a line voltage of 220. The motor was located in the front part of the locomotive, on its side, with the armature shaft across the frames, or parallel with the driving axles. On account of the high speed of the armature shaft, it was not possible to connect the driving axles direct, but this was an advantage in one way, as by introducing an intermediate countershaft corresponding to the well-known type of double reduction motor used on trolley cars since 1885, a fairly good arrangement was obtained to regulate the speed of the locomotive, exclusive of resistance in the electric circuit. Endless leather belting was used to transmit the power from the motor to the countershaft, and from the latter to the driving wheels, which were the front pair. A vertical idler pulley was mounted in a frame over the belt from motor to countershaft, terminating in a vertical screw and hand wheel for tightening the belt to increase speed, or the reverse to lower speed. This hand wheel was located in the cab, where it was easily accessible. The rough outline sketched below shows the location of the motor in relation to countershaft, belting, driving wheels, idler, etc. On account of both rails being used for circuits, the driving wheels had to be split circumferentially and completely insulated from the axles. This was accomplished by means of heavy wood blocks, well shellacked or otherwise treated to make them water and weatherproof, placed radially on the insides of the wheels and then substantially bolted to the hubs and rims of the latter. The weight of the locomotive was distributed over the driving wheels in the usual locomotive practice by means of springs and equalizers. The current was taken from the rims of the driving wheels by a three-pronged collector of brass against which flexible copper brushes were pressed, a simple manner of overcoming any inequalities of the roadbed. The late Mr. Charles T. Hughes was in charge of the track construction at Menlo Park. His work was excellent throughout, and the results were highly satisfactory so far as they could possibly be with the arrangement originally planned by Mr. Edison and his assistants. Mr. Charles L. Clark, one of the earliest electrical engineers employed by Mr. Edison, made a number of tests on this 1882 railroad. I believe that the engine driving the 4Z generators at the powerhouse indicated as high as 70 horsepower at the time the locomotive was actually in service. The electrical features of the 1882 locomotive were very similar to those of the earlier one already described. Shunt and series field windings were added to the motor, and the series windings could be plugged in and out of the circuit as desired. The series winding was supplemented by resistance boxes, also capable of being plugged in or out of circuit. These various electrical features are diagrammatically shown in Figure 2, which also illustrates the connection with the generating plant. We quote again from Mr. Hammer, who says, "The freight locomotive had single reduction gears, as is the modern practice, but the power was applied through a friction clutch. The passenger locomotive was very speedy, and 90 passengers have been carried at a time by it. The freight locomotive was not so fast, but could pull heavy trains at a good speed. Many thousand people were carried on this road during 1882. The general appearance of Mr. Edison's electric locomotive of 1882 is shown in the illustration opposite page 462 of the preceding narrative. In the picture, Mr. Edison may be seen in the cab, and Mr. Insull on the front platform of the passenger car." End of Appendix XIII.
Appendix 14 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Comerford Martin. Appendix 14. Train Telegraphy. While the one-time art of telegraphing to and from moving trains was essentially a wireless system, and allied in some of its principles to the art of modern wireless telegraphy through space, the two systems cannot, strictly speaking, be regarded as identical, as the practice of the former was based entirely on the phenomenon of induction. Briefly described in outline, the train telegraph system consisted of an induction circuit obtained by laying strips of metal along the top or roof of a railway car, and the installation of a special telegraph line running through parallel with the track and strung on poles of only medium height. The train, and also each signalling station, was equipped with regulation telegraph apparatus, such as battery, key, relay, and sounder, together with induction coil and condenser. In addition, there was a special transmitting device in the shape of a musical reed or buzzer. In practice, this buzzer was continuously operated at a speed of about 500 vibrations per second by an auxiliary battery. Its vibrations were broken by means of a telegraph key into long and short periods, representing Morse characters, which were transmitted inductively from the train circuit to the pole line or vice versa, and received by the operator at the other end through a high-resistance telephone receiver inserted in the secondary circuit of the induction coil. The accompanying diagrammatic sketch of a simple form of the system, as installed on a car, will probably serve to make this more clear. An insulated wire runs from the metallic layers on the roof of the car to switch S, which is shown open in the sketch. When a message is to be received on the car from a station more or less remote, the switch is thrown to the left to connect with a wire running to the telephone receiver T. The other wire from this receiver is run down to one of the axles and there permanently connected, thus making a ground. The operator puts the receiver to his ear and listens for the message, which the telephone renders audible in the Morse characters. If a message is to be transmitted from the car to a receiving station near or distant, the switch S is thrown to the other side, thus connecting with a wire leading to one end of the secondary of induction coil C. The other end of the secondary is connected with the grounding wire. The primary of the induction coil is connected as shown, one end going to key K and the other to the buzzer circuit. The other side of the key is connected to the transmitting battery, while the opposite pole of this battery is connected in the buzzer circuit. The buzzer R is maintained in rapid vibration by its independent auxiliary battery, B1S. When the key is pressed down, the circuit is closed, and current from the transmitting battery B passes through the primary of the coil C, and induces a current of greatly increased potential in the secondary. The current as it passes into the primary, being broken up into short impulses by the tremendously rapid vibrations of the buzzer, induces similarly rapid waves of high potential in the secondary, and these in turn pass to the roof and thence through the intervening air by induction to the telegraph wire. By a continued lifting and depression of the key in the regular manner, these waves are broken up into long and short periods, and are thus transmitted to the station via the wire in Morse characters, dots and dashes. The receiving stations along the line of the railway were similarly equipped as to the apparatus, and generally speaking, the operations of sending and receiving messages were substantially the same as above described. The equipment of an operator on a car was quite simple, consisting merely of a small lapboard on which were mounted the key, coil, and buzzer, leaving room for telegraph blanks. To this board were also attached flexible conductors having spring clips, by means of which connections could be made quickly with conveniently placed terminals of the ground, roof, and battery wires. The telephone receiver was held on the head with a spring, the flexible connecting wire being attached to the lapboard, thus leaving the operator with both hands free. The system as shown in this sketch and elucidated by the text represents the operation of trained telegraphy in a simple form, but combining the main essentials of the art as it was successfully and commercially practiced for a number of years after Edison and Gilliland entered the field. They elaborated the system in various ways, making it more complete, but it has not been deemed necessary to enlarge further upon the technical minutiae of the art for the purpose of this work. End of Appendix 14.
Appendix 15 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Jerome Lawson, January 2008. Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Comerford Martin. Appendix 15, Kinetograph and Projecting Kinetoscope. Although many of the arts in which Edison has been a pioneer have been enriched by his numerous inventions and patents, which were subsequent to those of a fundamental nature, the so-called motion picture art is an exception, as the following, together with 3 other additional patents, see footnote 30, comprise all that he has taken out on this subject. United States Patent Number 589168, issued August 31, 1897, and reissued in 2 parts, namely number 12037, under date of September 30, 1902, and number 12192, under date of January 12, 1904. Application filed August 24, 1891. Footnote 30. Number 491993, issued February 21, 1893. Number 493426, issued March 14, 1893. Number 772647, issued October 18, 1904. There is nothing surprising in this, however, as the possibility of photographing and reproducing actual scenes of animate life are so thoroughly exemplified and rendered practicable by the apparatus and methods disclosed in the patents above cited, that these basic inventions in themselves practically constitute the art, its development proceeding mainly along the line of manufacturing details. That such a view of his work is correct, the highest criterion, commercial expediency, bears witness. For in spite of the fact that the courts have somewhat narrowed the broad claims of Edison's patents, by reason of the investigations of earlier experimenters, practically all the immense amount of commercial work that is done in the motion picture field today is accomplished through the use of apparatus and methods licensed under the Edison patents. The philosophy of this invention having already been described in Chapter 21, it will be unnecessary to repeat it here. Suffice it to say by way of reminder that it is founded upon the physiological phenomenon known as persistence of vision, through which a series of sequential photographic pictures of animate motion projected upon a screen in rapid succession will reproduce to the eye all the appearance of the original movements. Edison's work in this direction comprised the invention not only of a special form of camera for making original photographic exposures from a single point of view with very great rapidity, and of a machine adapted to effect the reproduction of such pictures in somewhat similar manner, but also of the conception and invention of a continuous, uniform, and evenly spaced tape-like film, so absolutely essential for both the above objects. The mechanism of such a camera, as now used, consists of many parts assembled in such contiguous proximity to each other that an illustration from an actual machine would not help the clearness of explanation to the general reader. Hence a diagram showing a sectional view of a simple form of such camera is presented below. In this diagram, A represents an outer, light-tight box containing a lens, C, and the other necessary mechanism for making the photographic exposures. H1 and H2 being cases for holding reels of film before and after exposure. F, the long, tape-like film. G, a sprocket whose teeth engage in perforations on the edges of the film, such sprocket being adapted to be revolved with an intermittent or step-by-step movement by hand or motor, and B, a revolving shutter having an opening and connected by gears with G, and arranged to expose the film during the periods of rest. A full view of this shutter is also represented, with its opening, D, in the small illustration to the right. In practice, the operation would be somewhat as follows, generally speaking. The lens would first be focused on the animate scene to be photographed. On turning the main shaft of the camera, the sprocket G is moved intermittently, and its teeth, catching in the holes of the sensitized film, draws it downward, bringing a new portion of its length in front of the lens, the film then remaining stationary for an instant. In the meantime, through gearing connecting the main shaft with the shutter, the latter is rotated, bringing its opening, D, coincident with the lens, and therefore exposing the film while it's stationary, after which the film again moves forward. So long as the action is continued, these movements are repeated, resulting in a succession of enormously rapid exposures upon the film during its progress from reel H1 to its automatic rewinding on reel H2. While the film is passing through the various parts of the machine, it is guided and kept straight by various sets of rollers between which it runs, as indicated in the diagram. By an ingenious arrangement of the mechanism, the film moves intermittently so that it may have a much longer period of rest than of motion. As in practice the pictures are taken at a rate of 20 or more per second, it will be quite obvious that each period of rest is infinitesimally brief, being generally 1/30th of a second or less. Still, it is sufficient to bring the film to a momentary condition of complete rest, and to allow for a maximum time of exposure, comparatively speaking, thus providing means for taking clearly defined pictures. The negatives so obtained are developed in the regular way, and the positive prints subsequently made from them are used for reproduction. The reproducing machine, or as it is called in practice, the projecting kinetoscope, is quite similar so far as its general conditions in handling the film are concerned. In appearance it is somewhat different. Indeed, it is in two parts, the one containing the lighting arrangements and condensing lens, and the other embracing the mechanism and objective lens. The taking camera must have its parts enclosed in a light-tight box because of the undeveloped sensitized film. But the projecting kinetoscope, using only a fully developed positive film, may, and for purposes of convenient operation, must be accessibly open. The illustration, Figure 2, will show the projecting apparatus as used in practice. The philosophy of reproduction is very simple, and is illustrated diagrammatically in Figure 3, reference letters being the same as in Figure 1. As to the additional reference letters, I is a condenser, J the source of light, and K a reflector. The positive film is moved intermittently but swiftly throughout its length between the objective lens and a beam of light coming through the condenser, being exposed by the shutter during the periods of rest. This results in a projection of the photographs upon a screen in such rapid succession as to present an apparently continuous photograph of the successive positions of the moving objects, which therefore appear to the human eye to be in motion. The first claim of reissue patent number 12192 describes the film. It reads as follows: an unbroken, transparent, or translucent tape-like photographic film, having thereon uniform, sharply defined, equidistant photographs of successive positions of an object in motion as observed from a single point of view at rapidly occurring intervals of time. Such photographs being arranged in a continuous straight-line sequence, unlimited in number save by the length of film, and sufficient in number to represent the movements of the object throughout an extended period of time. End of Appendix 15. Recording by Jerome Lawson, January 2008.
Appendix 16 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melissa. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix 17. Edison's ore milling inventions. The wide range of Edison's activities in this department of the arts is well represented in the diversity of the numerous patents that have been issued to him from time to time. These patents are between 50 and 60 in number and include magnetic ore separators of 10 distinct types, also breaking, crushing, and grinding rolls, conveyors, dust-proof bearings, screens, dryers, mixers, bricking apparatus and machines, ovens, and processes of various kinds. A description of the many devices in each of these divisions would require more space than is available. Hence, we shall confine ourselves to a few items of predominating importance, already referred to in the narrative, commencing with the fundamental magnetic ore separator, which was covered by United States Patent Number 228,329, issued June 1st, 1880. The illustration here presented is copied from the drawing forming part of this patent. A hopper, with adjustable feed, is supported several feet above a bin having a central partition. Almost midway between the hopper and the bin is placed an electromagnet, whose polar extension is so arranged as to be a little to one side of a stream of material falling from the hopper. Normally, a stream of finely divided ore falling from the hopper would fall into that portion of the bin lying to the left of the partition. If, however, the magnet is energized from a source of current, the magnetic particles in the falling stream are attracted by and move toward the magnet, which is so placed with relation to the falling material that the magnetic particles cannot be attracted entirely to the magnet before gravity has carried them past. Hence, their trajectory is altered, and they fall on the right-hand side of the partition in the bin, while the non-magnetic portion of the stream continues in a straight line and falls on the other side, thus effecting a complete separation. This simple but effective principle was the one employed by Edison in his great concentrating plant already described. In practice, the numerous hoppers, magnets, and bends were many feet in length, and they were arranged in batteries of varied magnetic strength, in order that the intermingled mass of crushed rock and iron ore might be more thoroughly separated by being passed through magnetic fields of successively increasing degrees of attracting power. Altogether, there are about 480 of these immense magnets in the plant, distributed in various buildings in batteries as above mentioned, the crushed rock containing the iron ore being delivered to them by conveyors, and the gangue and ore being taken away after separation by 2 other conveyors and delivered elsewhere. The magnetic separators at first used by Edison at this plant were of the same generality as the ones employed some years previously in the separation of seashore sand, but greatly enlarged and improved. The varied experiences gained in the concentration of vast quantities of ore led naturally to a greater development, and several new types and arrangements of magnetic separators were evolved and elaborated by him from first to last, during the progress of the work at the concentrating plant. The magnetic separation of iron from its ore being the foundation idea of the inventions now under discussion, a consideration of the separator has naturally taken precedence over those of collateral but inseparable interest. The ore-bearing rock, however, must first be ground to powder before it can be separated. Hence we will now begin at the root of this operation, and consider the giant rolls, which Edison devised for breaking huge masses of rock. In his application for United States Patent Number 672,616, issued April 23, 1901, applied for on July 16, 1897, he says, "The object of my invention is to produce a method for the breaking of rock which will be simple and effective, will not require the hand sledging or blasting of the rock down to pieces of moderate size, and will involve the consumption of a small amount of power." While this quotation refers to the method as simple, the patent under consideration covers one of the most bold and daring projects that Edison has ever evolved. He proposed to eliminate the slow and expensive method of breaking large boulders manually, and to substitute therefore momentum and kinetic energy applied through the medium of massive machinery, which, in a few seconds, would break into small pieces a rock as big as an ordinary upright cottage piano, and weighing as much as 6 tons. Engineers to whom Edison communicated his ideas were unanimous in declaring the thing an impossibility. It was like driving 2 express trains into each other at full speed, to crack a great rock placed between them; that no practical machinery could be built to stand the terrific impact and strains. Edison's convictions were strong, however, and he persisted. The experiments were of heroic size, physically and financially, but after a struggle of several years, and an expenditure of about $100,000, he realized the correctness and practicability of his plans in the success of the giant rolls, which were the outcome of his labors. The giant rolls consist of a pair of iron cylinders of massive size and weight, with removable wearing plates having irregular surfaces formed by projecting knobs. These rolls are mounted side by side in a very heavy frame, leaving a gap of about 14 inches between them, and are so belted up with the source of power that they run in opposite directions. The giant rolls described by Edison in the above-named patent as having been built and operated by him had a combined weight of 167,000 pounds, including all moving parts, which of themselves weighed about 70 tons, each roll being 6 feet in diameter and 5 feet long. A top view of the rolls is shown in the sketch, one roll and one of its bearings being shown in section. In Figure 2 the rolls are illustrated diagrammatically, as a sketch of this nature, even if given with a definite scale, does not always carry an adequate idea of relative dimensions to a non-technical reader. We present in Figure 3 a perspective drawing of the giant rolls as installed in the concentrating plant. In practice, a small amount of power is applied to run the giant rolls gradually up to a surface speed of several thousand feet a minute. When this high speed is attained, masses of rock weighing several tons in one or more pieces are dumped into a hopper, which guides them into the gap between the rapidly revolving rolls. The effect is to partially arrest the swift motion of the rolls instantaneously, and thereby develop and expend an enormous amount of kinetic energy, which, with pile-driver effect, cracks the rocks and breaks them into pieces small enough to pass through the 14-inch gap. As the power is applied to the rolls through slipping friction clutches, the speed of the driving pulleys is not materially reduced. Hence the rolls may again be quickly speeded up to their highest velocity, while another load of rock is being hoisted in position to be dumped into the hopper. It will be obvious from the foregoing that if it were attempted to supply the great energy necessary for this operation by direct application of steam power, an engine of enormous horsepower would be required, and even then it is doubtful if one could be constructed of sufficient strength to withstand the terrific strains which would ensue. But the work is done by the great momentum and kinetic energy obtained by speeding up these tremendous masses of metal, and then suddenly opposing their progress, the engine being relieved of all strain through the medium of the slipping friction clutches. Thus, the cyclopean operation may be continuously conducted with an amount of power prodigiously inferior in proportion to the results accomplished. The sketch, Figure 4, showing a large boulder being dumped into the hopper, or roll pit, will serve to illustrate the method of feeding these great masses of rock to the rolls, and will also enable the reader to form an idea of the rapidity of the breaking operation, when it is stated that a boulder of the size represented would be reduced by the giant rolls to pieces a trifle larger than a man's head in a few seconds. After leaving the giant rolls, the broken rock passed on through other crushing rolls of somewhat similar construction. These also were invented by Edison, but antedated those previously described, being covered by patent number 567,187, issued September 8, 1896. These rolls were intended for the reducing of one-man-sized rocks to small pieces, which at the time of their original inception was about the standard size of similar machines. At the Edison concentrating plant the broken rock, after passing through these rolls, was further reduced in size by other rolls, and was then ready to be crushed to a fine powder through the medium of another remarkable machine devised by Edison to meet his ever-recurring and well-defined ideas of the utmost economy and efficiency. Note: Figures 3 and 4 are reproduced from similar sketches on page 84 and 85 of McClure's Magazine for November 1897, by permission of S.S. McClure Company. The best fine grinding machines that it was then possible to obtain were so inefficient as to involve a loss of 82% of the power applied. The thought of such an enormous loss was unbearable, and he did not rest until he invented and put into use an entirely new grinding machine, which was called the three-high rolls. The device was covered by a patent issued to him on November 21st, 1899, number 637,327. It was a most noteworthy invention, for it brought into the art not only a greater efficiency of grinding than had ever been dreamed of before, but also a tremendous economy by the saving of power, for whereas the previous efficiency had been 18% and the loss 82%, Edison reversed these figures, and in his three-high rolls produced a working efficiency of 84%, thus reducing the loss of power by friction to 16%. A diagrammatic sketch of this remarkable machine is shown in Figure 5, which shows a front elevation of the casings, hopper, etc. removed, and also shows above the rolls the rope and pulleys, the supports for which are also removed, for the sake of clearness in the illustration. For the convenience of the reader, in referring to Figure 5, we will repeat the description of the three-high rolls, which is given on pages 487 and 488 of the preceding narrative. In the two end pieces of a heavy iron frame were set three rolls, or cylinders, one in the center, another below, and the other above, all three being in a vertical line. These rolls were about 3 feet in diameter, made of cast iron, and had faceplates of chilled iron. The lowest roll was set in a fixed bearing at the bottom of the frame, and therefore could only turn around on its axis. The middle and top rolls were free to move up or down from and toward the lower roll, and the shafts of the middle and upper rolls were set in a loose bearing, which could slip up and down in the iron frame. It will be apparent, therefore, that any material which passed in between the top and middle rolls, and the middle and bottom rolls, could be ground as fine as might be desired, depending entirely upon the amount of pressure applied to the loose rolls. In operation, the material passed first through the upper and middle rolls, then between the middle and lowest rolls. Footnote. The faces of these rolls were smooth, but as 3 high rolls came into later use in Edison's Portland cement operations, the faces were corrugated so as to fit into each other, gear fashion, to provide for a greater rate of feed. End footnote. This pressure was applied in a most ingenious manner. On the ends of the shafts of the bottom and top rolls there were cylindrical sleeves or bearings, having 7 sheaves in which was run a half-inch endless wire rope. This rope was wound 7 times over the sheaves as above, and led upward and over a single groove sheave, which was operated by the piston of an air cylinder, and in this manner the pressure was applied to the rolls. It will be seen, therefore, that the system consisted in a single rope passed over sheaves, and so arranged that it could be varied in length, thus providing for elasticity in exerting pressure and regulating it as desired. The efficiency of this system was incomparably greater than that of any other known crusher or grinder, for while a pressure of 125,000 pounds could be exerted by these rolls, friction was almost entirely eliminated, because the upper and lower roll bearings turned with the rolls and revolved in the wire rope, which constituted the bearing proper. Several other important patents have been issued to Edison for crushing and grinding rolls, some of them being for elaborations and improvements of those above described, but all covering methods of greater economy and effectiveness in rock grinding. Edison's work on conveyors during the period of his ore-concentrating labors was distinctly original, ingenious, and far in advance of the times. His conception of the concentrating problem was broad, and embraced an entire system, of which a principal item was the continuous transfer of enormous quantities of material from place to place at the lowest possible cost. As he contemplated the concentration of 6,000 tons daily, the expense of manual labor to move such an immense quantity of rock, sand, and ore would be absolutely prohibitive. Hence, it became necessary to invent a system of conveyors that would be capable of transferring this mass of material from one place to another. And not only must these conveyors be capable of carrying the material, but they must also be devised so that they would automatically receive and discharge their respective loads at appointed places. Edison's ingenuity, engineering ability, and inventive skill were equal to the task, however, and were displayed in a system and variety of conveyors that in practice seemed to act with almost human discrimination. When fully installed throughout the plant, they automatically transferred daily a mass of material equal to about 100,000 cubic feet, from mill to mill, covering about a mile in the transit. Up and down, winding in and out, turning corners, delivering material from one to another, making a number of loops in the drying oven, filling up bins, and passing on to the next when they were full, these conveyors in automatic action seemingly played their part with human intelligence, which was in reality the reflection of the intelligence and ingenuity which had originally devised them and set them in motion. 6 of Edison's patents on conveyors include a variety of devices which have since come into broad general use for similar work, and have been the means of effecting great economies in numerous industries of widely varying kinds. Interesting as they are, however, we shall not attempt to describe them in detail, as the space required would be too great. They are specified in the list of patents following this appendix, and may be examined in detail by any interested student. In the same list will also be found a large number of Edison's patents on apparatus and methods of screening, drying, mixing, and briquetting, as well as for dust-proof bearings, and for various types and groupings of separators, all of which were called forth by the exigencies and magnitude of his great undertaking, and without which he could not possibly have attained the successful physical results that crowned his labors. Edison's persistence in reducing the cost of his operations is noteworthy in connection with his screening and drying inventions, in which the utmost advantage is taken of the law of gravitation. With its assistance, which cost nothing, these operations were performed perfectly, It was only necessary to deliver the material at the top of the chambers, and during its natural descent it was screened or dried as the case might be. All these inventions and devices, as well as those described in detail above, except magnetic separators and mixing and briquetting machines, are being used by him today in the manufacture of Portland cement, as that industry presents many of the identical problems which presented themselves in relation to the concentration of iron ore. End of Appendix XVI. Recording by Melissa.
Appendix XVII of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix XVII. The Long Cement Kiln. In this remarkable invention, which has brought about a striking innovation in a long-established business, we see another characteristic instance of Edison's incisive reasoning and boldness of conception carried into practical effect in face of universal opinions to the contrary. For the information of those unacquainted with the process of manufacturing Portland cement, it may be stated that the material consists preliminarily of an intimate mixture of cement rock and limestone ground to a very fine powder. This powder is technically known in the trade as chalk, and is fed into rotary kilns and burned. That is to say, it is subjected to a high degree of heat obtained by the combustion of pulverized coal, which is injected into the interior of the kiln. This combustion effects a chemical decomposition of the chalk, and causes it to assume a plastic consistency, and to collect together in the form of small spherical balls, which are known as clinker. Kilns are usually arranged with a slight incline, at the upper end of which the chalk is fed in, and gradually works its way down to the interior flame of burning fuel at the other end. When it arrives at the lower end, the material has been burned, and the clinker drops out into a receiving chamber below. The operation is continuous, a constant supply of chalk passing in at one end of the kiln, and a continuous dribble of clinker balls dropping out at the other. After cooling, the clinker is ground into a very fine powder, which is the Portland cement of commerce. It is self-evident that an ideal kiln would be one that produced the maximum quantity of thoroughly clinkered material with a minimum amount of fuel, labor, and investment. When Edison was preparing to go into the cement business, he looked the ground over thoroughly, and, after considerable investigation and experiment, came to the conclusion that prevailing conditions as to kilns were far from ideal. The standard kilns then in use were about 60 feet in length, with an internal diameter of about 5 feet. In all rotary kilns for burning cement, the true clinkering operation takes place only within a limited portion of their total length, where the heat is the greatest. Hence, the interior of the kiln may be considered as being divided longitudinally into two parts or zones, namely, the combustion or clinkering zone, and the zone of oncoming raw material. In the 60-foot kiln, the length of the combustion zone was about 10 feet, extending from a point 6 or 8 feet from the lower, or discharge, and to a point about 18 feet from that end. Consequently, beyond that point there was a zone of only about 40 feet, through which the heated gases passed and came in contact with the oncoming material, which was in movement down toward the clinkering zone. Since the bulk of oncoming material was small, the gases were not called upon to part with much of their heat, and therefore passed on up the stack at very high temperatures, ranging from 1500 degrees to 1800 degrees Fahrenheit. Obviously, this heat was entirely lost. An additional loss of efficiency arose from the fact that the material moved so rapidly toward the combustion zone that it had not given up all its carbon dioxide on reaching there, and by the giving off of large quantities of that gas within the combustion zone, perfect and economical combustion of coal could not be effected. The comparatively short length of the 60-foot kiln not only limited the amount of material that could be fed into it, but the limitation in length of the combustion zone militated against a thorough clinkering of the material, this operation being one in which the elements of time and proper heat are prime considerations. Thus the quantity of good clinker obtainable was unfavourably affected. By reason of these and other limitations and losses, it has been possible in practice to obtain only about 250 barrels of clinker per day of 24 hours, and that with an expenditure for coal proportionately equal to about 29 to 33% of the quantity of clinker produced, even assuming that all the clinker was of good quality. Edison realized that the secret of greater commercial efficiency and improvement of quality lay in the ability to handle larger quantities of material within a given time, and to produce a more perfect product without increasing cost or investment in proportion. His reasoning led him to the conclusion that this result could only be obtained through the use of a kiln of comparatively great length, and his investigations and experiments enabled him to decide upon a length of 150 feet, but with an increase in diameter of only 6 inches to a foot over that of the 60-foot kiln. The principal considerations that influenced Edison in making this radical innovation may be briefly stated as follows. First, the ability to maintain in the kiln a load from 5 to 7 times greater than ordinarily employed, thereby tending to a more economical output. Second, the combustion of a vastly increased bulk of pulverized coal in a greatly enlarged combustion zone extending about 40 feet longitudinally into the kiln, thus providing an area within which the material might be maintained in a clinkering temperature for a sufficiently long period to ensure its being thoroughly clinkered from periphery to centre. Third, by reason of such a greatly extended length of the zone of oncoming material, and consequently much greater bulk, the gases and other products of combustion would be cooled sufficiently between the combustion zone and the stack so as to leave the kiln at a comparatively low temperature. Besides, the oncoming material would thus be gradually raised in temperature instead of being heated abruptly as in the shorter kilns. Fourth, the material having thus been greatly raised in temperature before reaching the combustion zone would have parted with substantially all its carbon dioxide, and therefore would not introduce into the combustion zone sufficient of that gas to disturb the perfect character of the combustion. Fifth, on account of the great weight of the heavy load in a long kiln, there would result the formation of a continuous plastic coating on that portion of the inner surface of the kiln where the temperatures are highest. This would effectively protect the fire brick lining from the destructive effects of the heat. Such, in brief, were the essential principles upon which Edison based his conception and invention of the long kiln, which has since become so well known in the cement business. Many other considerations of a minor and mechanical nature, but which are important factors in his solution of this difficult problem, are worthy of study by those intimately associated with or interested in the art. Not the least of the mechanical questions was settled by Edison's decision to make this tremendously long kiln in sections of cast iron with flanges bolted together and supported on rollers rotated by electric motors. Longitudinal expansion and thrust were also important factors to be provided for, as well as special devices to prevent the packing of the mass of material as it passed in and out of the kiln. Special provision was also made for injecting streams of pulverized coal in such a manner as to create the largely extended zone of combustion. As to the details of these and many other ingenious devices, we must refer the curious reader to the patents, as it is merely intended in these pages to indicate in a brief manner the main principles of Edison's notable inventions. The principal United States patent on the long kiln was issued October 24, 1905, number 802631. That his reasonings and deductions were correct in this case have been indubitably proven by some years of experience with the long kiln in its ability to produce from 800 to 1,000 barrels of good clinker every 24 hours, with an expenditure for coal proportionately equal to about only 20% of the quantity of clinker produced. To illustrate the long cement kiln by diagram would convey but little to the lay mind, and we therefore present an illustration, Figure 1, of actual kilns in perspective, from which sense of their proportion may be gathered. End of Appendix 17.
Appendix 18 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Jerome Lawson, January 2008. Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Comerford Martin. Appendix 18, Edison's New Storage Battery. Generically considered, a battery is a device which generates electric current. There are two distinct species of battery, one being known as primary and the other as storage. Although the latter is sometimes referred to as a secondary battery or accumulator, every type of each of these two species is essentially alike in its general makeup. That is to say, every cell or battery of any kind contains at least two elements of different nature, immersed in a more or less liquid electrolyte of chemical character. On closing the circuit of a primary battery, an electric current is generated by reason of the chemical action which is set up between the electrolyte and the elements. This involves a gradual consumption of one of the elements and a corresponding exhaustion of the active properties of the electrolyte. By reason of this, both the element and the electrolyte that have been used up must be renewed from time to time, in order to obtain a continued supply of electric current. The storage battery also generates electrical current through chemical action, but without involving the constant repriming with active materials to replace those consumed and exhausted as above mentioned. The term storage, as applied to this species of battery, is however a misnomer, and has been the cause of much misunderstanding to non-technical persons. To the lay mind, a storage battery presents itself in the aspect of a device in which electric energy is stored, just as compressed air is stored or accumulated in a tank. This view, however, is not in accordance with facts. It is exactly like the primary battery in the fundamental circumstance that its ability for generating electric current depends upon chemical action. In strict terminology, it is a reversible battery, as will be quite obvious if we glance briefly at its philosophy. When a storage battery is charged by having an electric current pass through it, the electric energy provides a chemical effect, adding oxygen to the positive plate and taking oxygen away from the negative plate. Thus, the positive plate becomes oxidized and the negative plate reduced. After the charging operation is concluded, the battery is ready for use, and upon its circuit being closed through a translating device, such as a lamp or motor, a reversion discharge takes place, the positive plate giving up its oxygen and the negative plate being oxidized. These chemical reactions result in the generation of an electric current as in a primary battery. As a matter of fact, the chemical actions and reactions in a storage battery are much more complex, but the above will serve to afford the lay reader a rather simple idea of the general result arrived at through the chemical activity referred to. The storage battery, as a commercial article, was introduced into the market in the year 1881. At that time, and all through the succeeding years, until about 1905, there was only one type that was recognized as commercially practicable, namely that known as the lead sulfuric acid cell, consisting of lead plates immersed in an electrolyte of dilute sulfuric acid. In the year last named, Edison first brought out his new form of nickel-iron cell with alkaline electrolyte, as we have related in the preceding narrative. Early in the 80s, at Menlo Park, he had given much thought to the lead type of storage battery, and during the course of 3 years had made a prodigious number of experiments in the direction of improving it. probably performing more experiments in that time than the aggregate of those of all other investigators. Even in those early days, he arrived at the conclusion that the lead sulfuric acid combination was intrinsically wrong, and did not embrace the elements of a permanent commercial device. He did not at that time, however, engage in a serious search for another form of storage battery, being tremendously occupied with his lighting system and other matters. It may here be noted, for the information of the lay reader, that the lead-acid type of storage battery consists of 2 or more lead plates immersed in dilute sulfuric acid and contained in a receptacle of glass, hard rubber, or other special material not acted upon by acid. The plates are prepared and formed in various ways, and the chemical actions are similar to those above stated, the positive plate being oxidized, and the negative reduced during charge, and reversed during discharge. This type of cell, however, has many serious disadvantages inherent to its very nature. We will name a few of them briefly. Constant dropping of fine particles of active material often causes short-circuiting of the plates, and always necessitates occasional washing out of cells. Deterioration through sulfation if discharge is continued too far, or if recharging is not commenced quickly enough. Destruction of adjacent metalwork by the corrosive fumes given out during charge and discharge. The tendency of lead plates to buckle under certain conditions. The limitation to the use of glass, hard rubber, or similar containers on account of the action of the acid, and the immense weight for electrical capacity. The tremendously complex nature of the chemical reactions which take place in the lead-acid storage battery also renders it an easy prey to many troublesome diseases. In the year 1900, when Edison undertook to invent a storage battery, he declared it should be a new type into which neither sulfuric nor any other acid should enter. He said that the intimate and continued companionship of an acid and a metal was unnatural, and incompatible with the idea of durability and simplicity. He furthermore stated that lead was an unmechanical metal for a battery, being heavy and lacking stability and elasticity, and that as most metals were unaffected by alkaline solutions, he was going to experiment in that direction. The soundness of his reasoning is amply justified by the perfection of results obtained in the new type of storage battery bearing his name, and now to be described. The essential technical details of this battery are fully described in an article written by one of Edison's laboratory staff, Walter E. Holland, who for many years has been closely identified with the inventor's work on this cell. The article was published in the Electrical World, New York, April 28, 1910, and the following extracts therefrom will afford an intelligent comprehension of this invention. The A-type Edison cell is the outcome of 9 years of costly experimentation and persistent toil on the part of its inventor and his associates. The Edison invention involves the use of an entirely new voltaic combination in an alkaline electrolyte, in place of the lead peroxide combination, and acid electrolyte, characteristic of all other commercial storage batteries. Experience has proven that this not only secures durability and greater output per unit weight of battery, but in addition there is eliminated a long list of troubles and diseases inherent in the lead-acid combination. The principle on which the action of this new battery is based is the oxidation and reduction of metals in an electrolyte which does not combine with, and will not dissolve, either the metals or their oxides, and an electrolyte, furthermore, which, although decomposed by the action of the battery, is immediately reformed in equal quantity, and therefore in effect is a constant element, not changing in density or in conductivity. A battery embodying this basic principle will have features of great value where lightness and durability are desired. For instance, the electrolyte, being a constant factor as explained, is not required in any fixed and large amount, as is the case with sulfuric acid in the lead battery. Thus the cell may be designed with minimum distancing of plates and with the greatest economy of space that is consistent with safe insulation and good mechanical design. Again, the active materials of the electrodes being insoluble in, and absolutely unaffected by the electrolyte, are not liable to any sort of chemical deterioration by action of the electrolyte, no matter how long continued. The electrolyte of the Edison battery is a 21% solution of potassium hydrate, having, in addition, a small amount of lithium hydrate. The active metals of the electrodes, which will oxidize and reduce in this electrolyte without dissolution or chemical deterioration, are nickel and iron. These active elements are not put in plates as metals, but one, nickel, in the form of a hydrate, and the other, iron, as an oxide. The containing cases of both kinds of active material, Figure 1, and their supporting grids, Figure 2, as well as the bolts, washers, and nuts used in assembling, Figure 3, and even the retaining can and its cover, Figure 4, are all made of nickel-plated steel, a material in which lightness, durability, and mechanical strength are most happily combined, and a material beyond suspicion as to corrosion in an alkaline electrolyte. An essential part of Edison's discovery of active materials for an alkaline storage battery was the preparation of these materials. Metallic powder of iron and nickel, or even oxides of these metals, prepared in the ordinary way, are not chemically active in a sufficient degree to work in a battery. It is only when specially prepared iron oxide of exceeding fineness and nickel hydrate conforming to certain physical as well as chemical standards can be made that the alkaline battery is practicable. Needless to say, the working out of the conditions and processes of manufacture of the materials has involved great ingenuity and endless experiments. The article then treats of Edison's investigations into means for supporting and making electrical connection with the active materials, showing some of the difficulties encountered and the various discoveries made in developing the perfected cell, after which the writer continues his description of the A-type cell as follows. It will be seen at once that the construction of the two kinds of plate is radically different. The negative or iron plate, Figure 5, has the familiar flat pocket construction. Each negative contains 24 pockets, a pocket being 1/2 inch wide by 3 inches long, and having a maximum thickness of a little more than 1/8 inch. The positive or nickel plate, Figure 6, is seen to consist of 2 rows of round rods or pencils, 30 in number, held in a vertical position by a steel support frame. The pencils have flat flanges at the ends, formed by closing the metal case, by which they are supported and electrical connection is made. The frame is slit at the inner horizontal edges, and then folded in such a way as to make individual clamping jaws for each end flange. The clamping in is done at great pressure, and the resultant plate has great rigidity and strength. The perforated tubes into which the nickel active material is loaded are made of nickel-plated steel of high quality. They are put together with a double-lapped spiral seam to give expansion-resisting qualities, and as an additional precaution, small metal rings are slipped on the outside. Each tube is 1/4 inch in diameter by 4 1/8 inches long, and has 8 of the reinforcing rings. It will be seen that the A positive plate has been given the theoretically best design to prevent expansion and overcome trouble from that cause. Actual tests, long continued under very severe conditions, have shown that the construction is right and fulfills the most sanguine expectations. Mr. Holland in his article then goes on to describe the development of the nickel flakes as the conducting factor in the positive element, but as this has already been described in Chapter 22, we shall pass on to a later point, where he says, an idea of the conditions inside a loaded tube can best be had by microscopic examination. Figure 7 shows a magnified section of a regularly loaded tube which has been sawed lengthwise. The vertical bounding walls are edges of the perforated metal containing tube. The dark horizontal lines are layers of nickel flake, while the light-colored thicker layers represent the nickel hydrate. It should be noted that the layers of flake nickel extend practically unbroken across the tube and make contact with the metal wall at both sides. These metal layers conduct current to or from the active nickel hydrate in all parts of the tube very efficiently. There are about 350 layers of each kind of material in a 4 1/8 inch tube, each layer of nickel hydrate being about 0.01 inch thick, so it will be seen that the current does not have to penetrate very far into the nickel hydrate, 1/2 a layer's thickness being the maximum distance. The perforations of the containing tube, through which the electrolyte reaches the active material, are also shown in Figure 7. In conclusion, the article enumerates the chief characteristics of the Edison storage battery, which fit it preeminently for transportation service, as follows. 1. No loss of active material, hence no sediment short circuits. 2. No jar breakage. 3. Possibility of quick disconnection or replacement of any cell without employment of skilled labor. 4. Impossibility of buckling and harmlessness of a dead short circuit. 5. Simplicity of care required. 6. Durability of materials and construction. 7. Impossibility of sulfation. 8. Entire absence of corrosive fumes. 9. Commercial advantages of light weight. 10. Duration on account of its dependability. And 11. Its high practical efficiency. End of Appendix 18. Recording by Jerome Lawson. January 2008.
Appendix 19 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix 19. Edison's Poured Cement House. The inventions that have been thus far described fall into two classes. First, those that were fundamental in the great arts and industries which have been founded and established upon them, and second, those that have entered into and enlarged other arts that were previously in existence. On coming to consider the subject now under discussion, however, we find ourselves at this writing on the threshold of an entirely new and undeveloped art, of such boundless possibilities that its ultimate extent can only be a matter of conjecture. Edison's concrete house, however, involves two main considerations, first of which was the conception or creation of the idea, vast and comprehensive, of providing imperishable and sanitary homes for the wage earner by moulding an entire house in one piece, in a single operation, so to speak, and so simply that extensive groups of such dwellings could be constructed rapidly and at a very reasonable cost. With this idea suggested, one might suppose that it would be a simple matter to make moulds and pour in a concrete mixture. Not so, however, and here the second consideration presents itself. An ordinary cement mixture is composed of crushed stone, sand, cement, and water. If such a mixture be poured into deep moulds, the heavy stone and sand settle to the bottom. Should the mixture be poured into a horizontal mould, like the floor of a house, the stone and sand settle, forming an ununiform mass. It was at this point that invention commenced, in order to produce a concrete mixture which would overcome this crucial difficulty. Edison, with characteristic thoroughness, took up a line of investigation, and after a prolonged series of experiments, succeeded in inventing a mixture that upon hardening remained uniform throughout its mass. In the beginning of his experimentation, he had made the conditions of test very severe by the construction of forms similar to that shown in the sketch below. This consisted of a hollow wooden form of the dimensions indicated. The mixture was to be poured into the hopper until the entire form was filled, such mixture flowing down and along the horizontal legs and up the vertical members. It was to be left until the mixture was hard, and the requirement of the test was that there should be absolute uniformity of mixture and mass throughout. This was finally accomplished, and further invention then proceeded along engineering lines, looking toward the devising of a system of moulds with which practicable dwellings might be cast. Edison's boldness and breadth of conception are well illustrated in his idea of a poured house, in which he displays his accustomed tendency to reverse accepted methods. In fact, it is this very reversal of usual procedures that renders it difficult for the average mind to instantly grasp the full significance of the principles involved and the results attained. Up to this time we have been accustomed to see the erection of a house begun at the foundation and built up slowly, piece by piece, of solid materials. First the outer frame, then the floors and inner walls, followed by the stairways, and so on up to the putting on of the roof. Hence it requires a complete rearrangement of mental conceptions to appreciate Edison's proposal to build a house from the top downward. In a few hours, with a freely flowing material poured into moulds, and in a few days to take away the moulds and find a complete, indestructible sanitary house, including foundation, frame, floors, walls, stairways, chimneys, sanitary arrangements, and roof, with artistic ornamentation inside and out, all in one solid piece, as if it were graven or bored out of a rock. To bring about the accomplishment of a project so extraordinarily broad involves engineering and mechanical conceptions of a high order, and, as we have seen, these have been brought to bear on the subject by Edison, together with an intimate knowledge of compounded materials. The main features of this invention are easily comprehensible with the aid of the following diagrammatic sectional sketch. It should first be understood that the above sketch is in broad outline, without elaboration, merely to illustrate the working principle, and while the upright structure on the right is intended to represent a set of moulds in position to form a 3-story house with cellar, no regular details of such a building, such as windows, doors, stairways, etc., are here shown, as they would only tend to complicate an explanation. It will be noted that there are really 2 sets of moulds, an inside and an outside set, leaving a space between them throughout. Although not shown in the sketch, there is, in practice, a number of bolts passing through these 2 sets of moulds at various places to hold them together in their relative positions. In the open space between the moulds there are placed steel rods for the purpose of reinforcement, while all through the entire structure provision is made for water and steam pipes, gas pipes, and electric light wires being placed in appropriate positions as the moulds are assembled. At the center of the roof there will be noted a funnel-shaped opening. Into this there is delivered, by the endless chain of buckets shown on the left, a continuous stream of special free-flowing concrete mixture. This mixture descends by gravity and gradually fills the entire space between the 2 sets of moulds. The delivery of the material, or pouring as it is called, is continued until every part of the space is filled and the mixture is even with the tip of the roof, thus completing the pouring, or casting, of the house. In a few days afterward the concrete will have hardened sufficiently to allow the moulds to be taken away, leaving an entire house, from cellar to floor to the peak of the roof, complete in all its parts, even to the mantels and picture moulding, and requiring only windows and doors, plumbing, heat, and lighting fixtures to make it ready for habitation. In the above sketch, the concrete mixers A and B are driven by the electric motor C. As the material is mixed, it descends into the tank D, and flows through a trough into a lower tank E, in which it is constantly stirred, and from which it is taken by the endless chain of buckets and dumped into the funnel-shaped opening at the top of the moulds, as above described. The moulds are made of cast iron in sections of such size and weight as will be most convenient for handling, mostly in pieces not exceeding 2 by 4 feet in rectangular dimensions. The subjoined sketch shows an exterior view of several of these moulds as they appear when bolted together, the intersecting central portions representing ribs which are included as part of the casting for the purposes of strength and rigidity. The moulds represented above are those for straight work, such as walls and floors. Those intended for stairways, eaves, cornices, windows, doorways, etc., are much more complicated in design, although the same general principles are employed in their construction. While the philosophy of pouring or casting a complete house in its entirety is apparently quite simple, The development of the engineering and mechanical questions involves the solution of a vast number of most intricate and complicated problems, covering not only the building as a whole, but its numerous parts, down to the minutest detail. Safety, convenience, duration, and the practical impossibility of altering a one-piece solid dwelling are questions that must be met before its construction, and therefore Edison has proceeded calmly on his way toward the goal he has ever had clearly in his mind, with utter indifference to the criticism and jeers of those who, as experts, have professed positive knowledge of the impossibility of his carrying out this daring scheme. End of Appendix 19.
List of United States patents. From Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Comerford Martin. List of United States patents granted to Thomas A. Edison, arranged according to dates of execution of applications for such patents. This list shows the inventions as Mr. Edison has worked upon them from year to year. 1868. Number 90646. Title of patent, Electrographic Vote Recorder. Date executed, October 13th, 1868. 1869. Number 91527. Printing Telegraph. Reissued October 25th, 1870, numbered 4166, and August 5th, 1873, numbered 5519. January 25th, 1869. Number 96567. Apparatus for Printing Telegraph. Reissued February 1st, 1870, numbered 3820, August 17th, 1869. Number 96681. Electrical Switch for Telegraph Apparatus. August 27th, 1869. Number 102320. Printing Telegraph, Pope and Edison. Reissued April 17th, 1877, numbered 7621, and December 9th, 1884, numbered 10542. September 16th, 1869. Number 103924. Printing Telegraphs, Pope and Edison. Reissued August 5th, 1873. 1870. Number 103035. Electromotor Escapement. February 5th, 1870. Number 128608. Printing Telegraph Instruments. May 4th, 1870. Number 114656. Telegraph Transmitting Instruments. June 22nd, 1870. Number 114658. Electromagnets for Telegraph Instruments. June 22nd, 1870. Number 114657. Relay Magnets for Telegraph Instruments. September 6, 1870. Number 111112. Electric Motor Governors. June 29, 1870. Number 113033. Printing Telegraph Apparatus. November 17, 1870. 1871. Number 113034. Printing Telegraph Apparatus. January 10, 1871. Number 123005. Telegraph Apparatus. July 26, 1871. Number 123006. Printing Telegraph. July 26, 1871. Number 123984. Telegraph Apparatus. July 26, 1871. Number 124800. Telegraphic Recording Instruments. August 12, 1871. Number 121601. Machinery for perforating paper for telegraph purposes. August 16, 1871. Number 126535. Printing Telegraphs. November 13, 1871. Number 133841. Typewriting Machine. November 13th, 1871. 1872. Number 126532. Printing telegraphs. January 3rd, 1872. Number 126531. Printing telegraphs. January 17th, 1872. Number 126534. Printing telegraphs. January 17th, 1872. Number 126528. Type wheels for printing telegraphs. January 23rd, 1872. Number 126529. Type wheels for printing telegraphs. January 23rd, 1872. Number 126530. Printing telegraphs. February 14th, 1872. Number 126533. Printing telegraphs. February 14th, 1872. Number 132456. Apparatus for perforating paper for telegraphic use. March 15th, 1872. Number 132455. Improvement in paper for chemical telegraphs. April 10th, 1872. Number 133019. Electrical printing machine. April 18th, 1872. Number 128131. Printing telegraphs. April 26th, 1872. Number 128604. Printing telegraphs. April 26th, 1872. Number 128605. Printing telegraphs. April 26th, 1872. Number 128606. Printing telegraphs. April 26th, 1872. Number 128607. Printing telegraphs. April 26th, 1872. Number 131334. Rheotomes or circuit directors. May 6th, 1872. Number 134867. Automatic telegraph instruments. May 8th, 1872. Number 134868. Electromagnetic adjusters. May 8th, 1872. Number 130795. Electromagnets. May 9th, 1872. Number 131342. Printing telegraphs. May 9th, 1872. Number 131341. Printing telegraphs. May 28th, 1872. Number 131337. Printing telegraphs. June 10th, 1872. Number 131340. Printing telegraphs. June 10th, 1872. Number 131343. Transmitters and circuits for printing telegraph. June 10th, 1872. Number 131335. Printing telegraphs. June 15th, 1872. Number 131336. Printing telegraphs. June 15th, 1872. Number 131338. Printing telegraphs. June 29th, 1872. Number 131339. Printing telegraphs. June 29th, 1872. Number 131344. Unison stops for printing telegraphs. June 29th, 1872. Number 134866. Printing and telegraph instruments. October 16th, 1872. Number 138869. Printing telegraphs. October 16th, 1872. Number 142999. Galvanic batteries. October 31st, 1872. Number 141772. Automatic or chemical telegraphs. November 5th, 1872. Number 135531. Circuits for chemical telegraphs. November 9th, 1872. Number 146812. Telegraph signal boxes. November 26th, 1872. Number 141773. Circuits for automatic telegraphs. December 12, 1872. Number 141776, Circuits for Automatic Telegraphs, December 12, 1872. Number 150848, Chemical or Automatic Telegraphs, December 12, 1872. 1873. Number 139128, Printing Telegraphs, January 21, 1873. Number 139129, Printing Telegraphs, February 13, 1873. Number 140487, Printing Telegraphs, February 13, 1873. Number 140489, Printing Telegraphs, February 13, 1873. Number 138870, Printing Telegraphs, March 7, 1873. Number 141774, Chemical Telegraphs, March 7, 1873. Number 141775, Perforator for Automatic Telegraphs, March 7, 1873. Number 141777, Relay Magnets, March 7, 1873. Number 142688, Electric Regulators for Transmitting Instruments, March 7, 1873. Number 156843, Duplex Chemical Telegraphs, March 7, 1873. Number 147312, Perforators for Automatic Telegraphy, March 24, 1873. Number 147314, Circuits for Chemical Telegraphs, March 24, 1873. Number 150847, Receiving Instruments for Chemical Telegraphs, March 24, 1873. Number 140488, Printing Telegraphs, April 23, 1873. Number 147311, Electric Telegraphs, April 23, 1873. Number 147313, Chemical Telegraphs, April 23, 1873. Number 147917, Duplex Telegraphs, April 23, 1873. Number 150846, Telegraph Relays, April 23, 1873. Number 160405, Adjustable Electromagnets for Relays, etc., April 23, 1873. Number 162633, Duplex Telegraphs, April 22, 1873. Number 151209, Automatic Telegraphy and Perforators Therefore, August 25, 1873. Number 160402, Solutions for Chemical Telegraph Paper, September 29, 1873. Number 160404, Solutions for Chemical Telegraph Paper, September 29, 1873. Number 160580, Solutions for Chemical Telegraph Paper, October 14, 1873. Number 160403, Solutions for Chemical Telegraph Paper, October 29, 1873. 1874. Number 154788, District Telegraph Signal Box, April 2, 1874. Number 168004, Printing Telegraph, May 22, 1874. Number 166859, Chemical Telegraphy, June 1, 1874. Number 166860, Chemical Telegraphy, June 1, 1874. Number 166861, Chemical Telegraphy, June 1, 1874. Number 158787, Telegraph Apparatus, August 7, 1874. Number 172305, Automatic Roman Character Telegraph, August 7, 1874. Number 173718, Automatic Telegraphy, August 7, 1874. Number 178221, Duplex telegraphs, August 19, 1874. Number 178222, Duplex telegraphs, August 19, 1874. Number 178223, Duplex telegraphs, August 19, 1874. Number 180858, Duplex telegraphs, August 19, 1874. Number 207723, Duplex telegraphs, August 19, 1874. Number 480567, Duplex telegraphs, August 19, 1874. Number 207724, Duplex telegraphs, December 14, 1874. 1875. Number 168242, Transmitter and receiver for automatic telegraph, January 18, 1875. Number 168243, Automatic telegraphs, January 18, 1875. Number 168385, Duplex telegraphs, January 18, 1875. Number 168466, Solution for chemical telegraphs, January 18, 1875. Number 168467, Recording point for chemical telegraph, January 18, 1875. Number 195751, Automatic telegraphs, January 18, 1875. Number 195752, Automatic telegraphs, January 19, 1875. Number 171273, Telegraph apparatus, February 11, 1875. Number 169972, Electric signaling instrument, February 24, 1875. Number 209241, Quadruplex telegraph repeaters, reissued September 23, 1879, numbered 8906, February 24, 1875. 1876. Number 180857, Autographic printing, March 7, 1876. Number 198088, Telephonic telegraphs, April 3, 1876. Number 198089, Telephonic or electro-harmonic telegraphs, April 3, 1876. Number 182996, Acoustic telegraphs, May 9, 1876. Number 186330, Acoustic electric telegraphs, May 9, 1876. Number 186548, Telegraph alarm and signal apparatus, May 9, 1876. Number 198087, Telephonic telegraphs, May 9, 1876. Number 185507, Electro-harmonic multiplex telegraph, August 16, 1876. Number 200993, Acoustic telegraph, August 26, 1876. Number 235142, Acoustic telegraph, August 26, 1876. Number 200032, Synchronous movements for electric telegraphs, October 30, 1876. Number 200994, Automatic telegraph perforator and transmitter, October 30, 1876. 1877. Number 205370, Pneumatic stencil pens, February 3, 1877. Number 213554, Automatic telegraphs, February 3, 1877. Number 196747, Stencil pens, April 18, 1877. Number 203329, Perforating pens, April 18, 1877. Number 474230, Speaking telegraph, April 18, 1877. Number 217781, Sextuplex telegraph, May 8, 1877. Number 230621, Addressing machine, May 8, 1877. Number 377374, Telegraphy, May 8, 1877. Number 453601, Sextuplex Telegraph, May 31, 1877. Number 452913, Sextuplex Telegraph, May 31, 1877. Number 512872, Sextuplex Telegraph, May 31, 1877. Number 474231, Speaking Telegraph, July 9, 1877. Number 203014, Speaking Telegraph, July 16, 1877. Number 208299, Speaking Telegraph, July 16, 1877. Number 203015, Speaking Telegraph, August 16, 1877. Number 420594, Quadruplex Telegraph, August 16, 1877. Number 492789, Speaking Telegraph, August 31, 1877. Number 203013, Speaking Telegraph, December 8, 1877. Number 203018, Telephone or Speaking Telegraph, December 8, 1877. Number 200521, Phonograph or Speaking Machine, December 15, 1877. 1878. Number 203019, Circuit for Acoustic or Telephonic Telegraphs, February 13, 1878. Number 201760, Speaking Machines, February 28, 1878. Number 203016, Speaking Machines, February 28, 1878. Number 203017, Telephone Call Signals, February 28, 1878. Number 214636, Electric Lights, October 5, 1878. Number 222390, Carbon Telephones, November 8, 1878. Number 217782, Duplex Telegraphs, November 11, 1878. Number 214637, Thermal Regulator for Electric Lights, November 14, 1878. Number 210767, Vocal Engines, August 31, 1878. Number 218166, Magneto-Electric Machines, December 3, 1878. Number 218866, Electric Lighting Apparatus, December 3, 1878. Number 219628, Electric Lights, December 3, 1878. Number 295990, Typewriter, December 4, 1878. Number 218167, Electric Lights, December 31, 1878. 1879. Number 224329, Electric Lighting Apparatus, January 23, 1879. Number 227229, Electric Lights, January 28, 1879. Number 227227, Electric Lights, February 6, 1879. Number 224665, Automatic Stencils for Printing, March 10, 1879. Number 227679, Phonograph, March 19, 1879. Number 221957, Telephone, March 24, 1879. Number 227229, Electric Lights, April 12, 1879. Number 264643, Magneto-Electric Machines, April 21, 1879. Number 219393, Dynamo Electric Machines, July 7, 1879. Number 231704, Electrochemical Receiving Telephone, July 17, 1879. Number 266022, Telephone, August 1st, 1879. Number 252442, telephone, August 4th, 1879. Number 222881, magneto-electric machines, September 4th, 1879. Number 223898, electric lamp, November 1st, 1879. 1880. Number 230255, electric lamps, January 28th, 1880. Number 248425, apparatus for producing high vacuums, January 28th, 1880. Number 265311, electric lamp and holder for same, January 28th, 1880. Number 369280, system of electrical distribution, January 28th, 1880. Number 227226, safety conductor for electric lights, March 10th, 1880. Number 228617, brake for electromagnetic motors, March 10th, 1880. Number 251545, electric meter, March 10th, 1880. Number 525888, manufacture of carbons for electric lamps, March 10th, 1880. Number 264649, dynamo or magneto-electric machines, March 11th, 1880. Number 228329, magnetic ore separator, April 3rd, 1880. Number 238868, manufacture of carbons for incandescent electric lamps, April 25th, 1880. Number 237732, electric light, June 15th, 1880. Number 248417, manufacturing carbons for electric lights, June 15th, 1880. Number 298679, treating carbons for electric lights, June 15th, 1880. Number 248430, electromagnetic brake, July 2nd, 1880. Number 265778, electromagnetic railway engine, July 3rd, 1880. Number 248432, magnetic separator, July 26th, 1880. Number 239150, electric lamp, July 27th, 1880. Number 239372, testing electric light carbons, Edison and Batchelor, July 28th, 1880. Number 251540, carbon electric lamps, July 28th, 1880. Number 263139, manufacture of carbons for electric lamps, July 28th, 1880. Number 434585, telegraph relay, July 29th, 1880. Number 248423, carbonizer, July 30th, 1880. Number 263140, dynamo electric machines, July 30th, 1880. Number 248434, governor for electric engines, July 31st, 1880. Number 239147, system of electric lighting, July 31st, 1880. Number 264642, electric distribution and translation system, August 4th, 1880. Number 293433, insulation of railroad tracks used for electric circuits, August 6th, 1880. Number 239373, electric lamp, August 7th, 1880. Number 239745, electric lamp, August 7th, 1880. Number 263135, electric lamp, August 7th, 1880. Number 251546, electric lamp, August 10th, 1880. Number 239153, electric lamp, August 11th, 1880. Number 351855, electric lamp, August 11th, 1880. Number 248435, Utilizing electricity as motive power. August 12, 1880. Number 263132. Electromagnetic roller. August 14, 1880. Number 264645. System of conductors for the distribution of electricity. September 1, 1880. Number 240678. Weber meter. September 22, 1880. Number 239152. System of electric lighting. October 14, 1880. Number 239148. Treating carbons for electric lights. October 15, 1880. Number 238098. Magneto signaling apparatus, Edison and Johnson. October 21, 1880. Number 242900. Manufacturing carbons for electric lamps. October 21, 1880. Number 251556. Regulator for magneto or dynamo electric machines. October 21, 1880. Number 248426. Apparatus for treating carbons for electric lamps. November 5, 1880. Number 239151. Forming enlarged ends on carbon filaments. November 19, 1880. Number 12631. Design patent, incandescent electric lamp. November 23, 1880. Number 239149. Incandescing electric lamp. December 3, 1880. Number 242896. Incandescent electric lamp. December 3, 1880. Number 242897. Incandescent electric lamp. December 3, 1880. Number 248565. Weber meter. December 3, 1880. Number 263878. Electric lamp. December 3, 1880. Number 239154. Relay for telegraphs. December 11, 1880. Number 242898. Dynamo electric machine. December 11, 1880. Number 248431. Preserving fruit. December 11, 1880. Number 265777. Treating carbons for electric lamps. December 11, 1880. Number 239374. Regulating the generation of electric currents. December 16, 1880. Number 248428. Manufacture of incandescent electric lamps. December 16, 1880. Number 248427. Apparatus for treating carbons for electric lamps. December 21, 1880. Number 248437. Apparatus for treating carbons for electric lamps. December 21, 1880. Number 248416. Manufacture of carbons for electric lights. December 30th, 1880.
1881. Number 242899. Electric lighting. January 19th, 1881. Number 248418. Electric lamp. January 19th, 1881. Number 248433. Vacuum apparatus. January 19th, 1881. Number 251548. Incandescent electric lamps. January 19, 1881. Number 406824. Electric meter. January 19, 1881. Number 248422. System of electric lighting. January 20th, 1881. Number 431018. Dynamo or magneto electric machine. February 3rd, 1881. Number 242901. Electric motor. February 24th, 1881. Number 248429. Electric motor. February 24th, 1881. Number 248421. Current regulator for dynamo electric machine. February 25th, 1881. Number 251550. Magneto or dynamo electric machines. February 26, 1881. Number 251555. Regulator for dynamo electric machines. February 26, 1881. Number 482549, means for controlling electric generation, March 2nd, 1881. Number 248420, fixture and attachment for electric lamps, March 7th, 1881. Number 251553, electric chandeliers, March 7th, 1881. Number 251554, electric lamp and socket or holder, March 7th, 1881. Number 248424, fitting and fixtures for electric lamps, March 8, 1881. Number 248419, electric lamp, March 30th, 1881. Number 251542, system of electric light, April 19th, 1881. Number 263145, making incandescents, April 19th, 1881. Number 266447, electric incandescent lamp, April 21st, 1881. Number 266447, electric incandescent lamp, April 21st, 1881. Number 251552, underground conductors, April 22nd, 1881. Number 476531, electric lighting system, April 22nd, 1881. Number 248436, depositing cell for plating the connections of electric lamps, May 17th, 1881. Number 251539, electric lamp, May 17th, 1881. Number 263136, regulator for dynamo or magneto-electric machine, May 17th, 1871. Number 251557, Weber meter, May 19th, 1881. Number 263134, regulator for magneto-electric machine, May 19th, 1881. Number 251541, electromagnetic motor, May 20th, 1881. Number 251544, manufacture of electric lamps, May 20th, 1881. Number 251549, electric lamp and the manufacture thereof, May 20th, 1881. Number 251558, Weber meter, May 20th, 1881. Number 341644, incandescent electric lamp, May 20th, 1881. Number 251551, system of electric lighting, May 21, 1881. Number 263137, electric chandelier, May 21st, 1881. Number 263141, straightening carbons for incandescent lamps, May 21st, 1881. Number 264657, incandescent electric lamps, May 21st, 1881. Number 251543, electric lamp, May 24th, 1881. Number 251538, electric light, May 27, 1881. Number 425760, measurement of electricity in distribution system, May 31st, 1881. Number 251547, electrical governor, June 2nd, 1881. Number 263150, magneto or dynamo electric machines, June 3rd, 1881. Number 263131, magneto ore separator, June 4th, 1881. Number 435687, means for charging and using secondary batteries, June 21, 1881. Number 263143, magneto or dynamo electric machines, June 24th, 1881. Number 251537, dynamo electric machine, June 25th, 1881. Number 263147, vacuum apparatus, July 1st, 1881. Number 439389, electric lighting system, July 1st, 1881. Number 263149, commutator for dynamo or magneto electric machines, July 22nd, 1881. Number 479184, facsimile telegraph Edison and Kenny, July 26, 1881. Number 400317, ore separator, August 11th, 1881. Number 425763, commutator for dynamo electric machines, August 20th, 1881. Number 263133, dynamo or magneto electric machine, August 24th, 1881. Number 263142, Electrical Distribution System, August 24th, 1881. Number 264647, Dynamo or Magneto-Electric Machines, August 24th, 1881. Number 404902, Electrical Distribution System, August 24th, 1881. Number 257677, Telephone, September 7th, 1881. Number 266021, Telephone, September 7th, 1881. Number 263144, Mold for Carbonizing Incandescents, September 19th, 1881. Number 265774, Maintaining Temperatures in Weber Meters, September 21st, 1881. Number 264648, Dynamo or Magneto-Electric Machines, September 23rd, 1881. Number 265776, Electric Lighting System, September 27th, 1881. Number 524136, Regulator for Dynamo Electric Machines, September 27th, 1881. Number 273715, Malleabilizing Iron, October 4th, 1881. Number 281352, Weber Meter, October 5th, 1881. Number 446667, Locomotives for Electric Railways, October 11th, 1881. Number 288318, Regulator for Dynamo or Magneto Electric Machines, October 17th, 1881. Number 263148, Dynamo or Magneto Electric Machines, October 25th, 1881. Number 264646, Dynamo or Magneto Electric Machines, October 25th, 1881. Number 251559, Electrical Drop Light, October 25th, 1881. Number 266793, Electric Distribution System, October 25th, 1881. Number 358599, Incandescent Electric Lamp, October 29th, 1881. Number 264673, Regulator for Dynamo Electric Machine, November 3rd, 1881. Number 263138, Electric Arc Light, November 7th, 1881. Number 265775, Electric Arc Light, November 7th, 1881. Number 297580, Electric Arc Light, November 7th, 1881. Number 263146, Dynamo Magneto Electric Machines, November 22nd, 1881. Number 266588, Vacuum Apparatus, November 25th, 1881. Number 251536, Vacuum Pump, December 5th, 1881. Number 264650, Manufacturing Incandescent Electric Lamps, December 5th, 1881. Number 264660, Regulator for Dynamo Electric Machines, December 5th, 1881. Number 379770, Incandescent Electric Lamp, December 5th, 1881. Number 293434, Incandescent Electric Lamp, December 5th, 1881. Number 439391, Junction Box for Electric Wires, December 5th, 1881. Number 454558, Incandescent Electric Lamp, December 5th, 1881. Number 264653, Incandescent Electric Lamp, December 13th, 1881. Number 358600, Incandescing Electric Lamp, December 13th, 1881. Number 264652, Incandescent Electric Lamp, December 15th, 1881. Number 278419, Dynamo Electric Machines, December 15th, 1881. 1882. Number 265779, Regulator for Dynamo Electric Machines, January 17th, 1882. Number 264654, Incandescent Electric Lamps, February 10th, 1882. Number 264661, Regulator for Dynamo Electric Machines, February 10th, 1882. Number 264664, Regulator for Dynamo Electric Machines, February 10th, 1882. Number 264668, Regulator for Dynamo Electric Machines, February 10th, 1882. Number 264669, Regulator for Dynamo Electric Machines, February 10th, 1882. Number 264671, Regulator for Dynamo Electric Machines, February 10th, 1882. Number 275613, incandescent electric lamp, February 10th, 1882. Number 401646, incandescent electric lamp, February 10th, 1882. Number 264658, regulator for dynamo electric machines, February 28, 1882. Number 264659, regulator for dynamo electric machines, February 28, 1882. Number 265780, regulator for dynamo electric machines, February 28, 1882. Number 265781, regulator for dynamo electric machines, February 28, 1882. Number 278416, manufacture of incandescent electric lamps, February 28, 1882. Number 379771, regulator for dynamo electric machines, February 28, 1882. Number 272034, telephone, March 30th, 1882. Number 274576, transmitting telephone, March 30th, 1882. Number 274577, telephone, March 30th, 1882. Number 264662, regulators for dynamo electric machines, May 1st, 1882. Number 264663, regulator for dynamo electric machines, May 1st, 1882. Number 264665, regulator for dynamo electric machines, May 1st, 1882. Number 264666, regulator for dynamo electric machines, May 1st, 1882. Number 268205, dynamo or magneto-electric machine, May 1st, 1882. Number 273488, regulator for dynamo electric machines, May 1st, 1882. Number 273492, secondary battery, May 19th, 1882. Number 460122, process of an apparatus for generating electricity, May 19th, 1882. Number 466460, electrolyte decomposition, May 19th, 1882. Number 264672, regulator for dynamo electric machines, May 22nd, 1882. Number 264667, regulator for dynamo electric machines, May 22nd, 1882. Number 265786, apparatus for electrical transmission of power, May 22nd, 1882. Number 273828, system of underground conductors of electric distribution, May 22nd, 1882. Number 379772, system of electrical distribution, May 22nd, 1882. Number 274292, secondary battery, June 3rd, 1882. Number 281353, dynamo or magneto-electric machine, June 3rd, 1882. Number 287523, dynamo or magneto-electric machine, June 3rd, 1882. Number 365509, filament for incandescent electric lamps, June 3rd, 1882. Number 446668, electric arc light, June 3rd, 1882. Number 543985, incandescent conductor for electric lamps, June 3rd, 1882. Number 264651, incandescent electric lamps, June 9th, 1882. Number 264655, incandescent electric lamps, June 9th, 1882. Number 264670, regulator for dynamo electric machines, June 9th, 1882. Number 273489, turntable for electric railway, June 9th, 1882. Number 273490, electromagnetic railway system, June 9th, 1882. Number 401486, system of electric lighting, June 12th, 1882. Number 476527, system of electric lighting, June 12th, 1882. Number 439390, electric lighting system, June 19th, 1882. Number 446666, system of electric lighting, June 19th, 1882. Number 464822, system of distributing electricity, June 19th, 1882. Number 304082, electrical meter, June 24th, 1882. Number 274296, manufacture of incandescents, July 5th, 1882. Number 264656, incandescent electric lamp, July 7th, 1882. Number 265782, regulator for dynamo electric machines, July 7, 1882. Number 265783, regulator for dynamo electric machines, July 7, 1882. Number 265784, regulator for dynamo electric machines, July 7, 1882. Number 265785, dynamo electric machine, July 7, 1882. Number 273494, electrical railroad, July 7, 1882. Number 278418, translating electrical currents from high to low tension, July 7, 1882. Number 293435, electrical meter, July 7, 1882. Number 334853, mold for carbonizing, July 7, 1882. Number 339278, electric railway, July 7, 1882. Number 273714, magnetic electric signaling apparatus, August 5, 1882. Number 282287, magnetic electric signaling apparatus, August 5, 1882. Number 448778, electric railway, August 5, 1882. Number 439392, electric lighting system, August 12, 1882. Number 271613, manufacture of incandescent electric lamps, August 25, 1882. Number 287518, manufacture of incandescent electric lamps, August 25, 1882. Number 409825, electric meter, August 25, 1882. Number 439393, carbonizing chamber, August 25, 1882. Number 273487, regulator for dynamo electric machines, September 12, 1882. Number 297581, incandescent electric lamp, September 12, 1882. Number 395962, manufacturing electric lamps, September 16, 1882. Number 287525, regulator for systems of electrical distribution, Edison and C. L. Clark, October 4, 1882. Number 365465, valve gear, October 5, 1882. Number 317631, incandescent electric lamp, October 7, 1882. Number 307029, filament for incandescent lamp, October 9, 1882. Number 268209, incandescing electric lamp, October 10, 1882. Number 273486, incandescing electric lamp, October 12, 1882. Number 274293, electric lamp, October 14, 1882. Number 275612, manufacture of incandescent electric lamps, October 14, 1882. Number 430932, manufacture of incandescent electric lamps, October 14, 1882. Number 271616, regulator for dynamo electric machines, October 16, 1882. Number 543986, process for treating products derived from vegetable fibers, October 17, 1882. Number 543987, filament for incandescent lamps, October 17, 1882. Number 271614, shafting, October 19, 1882. Number 271615, governor for dynamo electric machines, October 19, 1882. Number 273491, regulator for driving engines of electrical generators, October 19, 1882. Number 273493, valve gear for electrical generator engines, October 19, 1882. Number 411016, manufacturing carbon filaments, October 19, 1882. Number 492150, coating conductors for incandescent lamps, October 19, 1882. Number 273485, incandescent electric lamps, October 26, 1882. Number 317632, incandescent electric lamps, October 26, 1882. Number 317633, incandescent electric lamps, October 26, 1882. Number 287520, incandescent conductor for electric lamps, November 3, 1882. Number 353783, incandescent electric lamp, November 3, 1882. Number 430933, filament for incandescent lamps, November 3, 1882. Number 274294, incandescent electric lamp, November 13, 1882. Number 281350, regulator for dynamo electric machines, November 13, 1882. Number 274295, incandescent electric lamp, November 14, 1882. Number 276233, electrical generator and motor, November 14, 1882. Number 274290, system of electrical distribution, November 20th, 1882. Number 274291, mold for carbonizer, November 28, 1882. Number 278413, regulator for dynamo electric machines, November 28, 1882. Number 278414, regulator for dynamo electric machines, November 28, 1882. Number 287519, manufacturing incandescent electric lamps, November 28, 1882. Number 287524, regulator for dynamo electric machines, November 28, 1882. Number 438298, manufacture of incandescent electric lamps, November 28, 1882. Number 276232, operating and regulating electrical generators, December 20th, 1882. 1883. Number 278415, manufacture of incandescent electric lamps, January 13th, 1883. Number 278417, manufacture of incandescent electric lamps, January 13th, 1883. Number 281349, regulator for dynamo electric machines, January 13th, 1883. Number 283985, system of electrical distribution, January 13th, 1883. Number 283986, system of electrical distribution, January 13th, 1883. Number 459835, manufacture of incandescent electric lamps, January 13th, 1883. Number 13940, design patent, incandescent electric lamp, February 13th, 1883. Number 280727, system of electrical distribution, February 13th, 1883. Number 359123, circuit controller for dynamo machine, February 13th, 1883. Number 287521, dynamo or magneto-electric machine, February 17th, 1883. Number 287522, molds for carbonizing, February 17th, 1883. Number 438299, manufacture of carbon filaments, February 12th, 1883. Number 446669, manufacture of filaments for incandescent electric lamps, February 17th, 1883. Number 476528, incandescent electric lamp, February 17th, 1883. Number 281351, electrical generator, March 5th, 1883. Number 283984, system of electrical distribution, March 5th, 1883. Number 287517, system of electrical distribution, March 14th, 1883. Number 283983, system of electrical distribution, April 5th, 1883. Number 354310, manufacture of carbon conductors, April 6th, 1883. Number 370123, electric meter, April 6th, 1883. Number 411017, carbonizing flask, April 6, 1883. Number 370124, manufacture of filament for incandescent electric lamp, April 12, 1883. Number 287516, system of electrical distribution, May 8, 1883. Number 341839, incandescent electric lamp, May 8, 1883. Number 398774, incandescent electric lamp, May 8, 1883. Number 370125, electrical transmission of power, June 1st, 1883. Number 370126, electrical transmission of power, June 1st, 1883. Number 370127, electrical transmission of power, June 1st, 1883. Number 370128, electrical transmission of power, June 1st, 1883. Number 370129, electrical transmission of power, June 1st, 1883. Number 370130, electrical transmission of power, June 1st, 1883. Number 370131, electrical transmission of power, June 1st, 1883. Number 348300, gauge for testing fibers for incandescent lamp carbons, June 1st, 1883. Number 287511, electric regulator, June 25th, 1883. Number 287512, Dynamo electric machine, June 25th, 1883. Number 287513, Dynamo electric machine, June 25th, 1883. Number 287514, Dynamo electric machine, June 25th, 1883. Number 287515, System of electrical distribution, June 25th, 1883. Number 297582, Dynamo electric machine, June 25th, 1883. Number 328572, commutator for dynamo electric machines, June 25th, 1883. Number 430934, electric lighting system, June 25th, 1883. Number 438301, system of electric lighting, June 25th, 1883. Number 297583, dynamo electric machines, July 27th, 1883. Number 304083, Dynamo electric machines, July 27th, 1883. Number 304084, device for protecting electric light systems from lightning, July 27th, 1883. Number 438302, commutator for dynamo electric machine, July 27th, 1883. Number 476529, system of electrical distribution, July 27th, 1883. Number 297584, Dynamo electric machine, August 8, 1883. Number 307030, electrical meter, August 8, 1883. Number 297585, incandescent conductor for electric lamps, September 14, 1883. Number 297586, electrical conductor, September 14, 1883. Number 435688, process and apparatus for generating electricity, September 14, 1883. Number 470922, manufacture of filaments for incandescent lamps, September 14, 1883. Number 490953, generating electricity, October 9, 1883. Number 293432, electrical generator or motor, October 17, 1883. Number 307031, electrical indicator, November 2nd, 1883. Number 337254, telephone, Edison and Bergman, November 10th, 1883. Number 297587, dynamo electric machine, November 16th, 1883. Number 298954, dynamo electric machine, November 15th, 1883. Number 298955, dynamo electric machine, November 15th, 1883. Number 304085, system of electrical distribution, November 15th, 1883. Number 509517, system of electrical distribution, November 15th, 1883. Number 425761, incandescent lamp, November 20th, 1883. Number 304086, incandescent electric lamp, December 15th, 1883. 1884. Number 298956, operating dynamo electric machine, January 5th, 1884. Number 304087, electrical conductor, January 12th, 1884. Number 395963, incandescent lamp filament, January 22nd, 1884. Number 526147, plating one material with another, January 22nd, 1884. Number 339279, system of electrical distribution, February 8th, 1884. Number 314115, chemical stock quotation telegraph, Edison and Kenny, February 9th, 1884. Number 436968, method and apparatus for drawing wire, June 2nd, 1884. Number 436969, apparatus for drawing wire, June 2nd, 1884. Number 438303, arc lamp, June 2nd, 1884. Number 343017, system of electrical distribution, June 27th, 1884. Number 391595, System of Electric Lighting, July 16, 1884. Number 328573, System of Electric Lighting, September 12, 1884. Number 328574, System of Electric Lighting, September 12, 1884. Number 328575, System of Electric Lighting, September 12, 1884. Number 391596, Incandescent Electric Lamp, September 24, 1884. Number 438304, Electric Signaling Apparatus, September 24, 1884. Number 422577, Apparatus for Speaking Telephones, Edison and Gilliland, October 21, 1884. Number 329030, Telephone, December 3, 1884. Number 422578, Telephone Repeater, December 9, 1884. Number 422579, Telephone Repeater, December 9, 1884. Number 340707, Telephonic Repeater, December 9, 1884. Number 340708, Electrical Signaling Apparatus, December 19, 1884. Number 347097, Electrical Signaling Apparatus, December 19, 1884. Number 478743, Telephone Repeater, December 31st, 1884. End of Section 50. Section 51 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Section 51. List of United States Patents. 1885. Number 340709. Telephone Circuit, Edison and Gilliland, January 2nd, 1885. Number 378044. Telephone Transmitter, January 9th, 1885. Number 348114. Electrode for Telephone Transmitters, January 12th, 1885. Number 438305. Fuse Box, January 14th, 1885. Number 350234. System of Railway Signalling, Edison and Gilliland, March 27th, 1885. Number 486634. System of Railway Signalling, Edison and Gilliland, March 27th, 1885. Number 333289. Telegraphy, April 27th, 1885. Number 333290. Duplex Telegraphy, April 30th, 1885. Number 333291. Way Station Quadruplex Telegraph, May 6, 1885. Number 465971. Means for transmitting signals electrically, May 14, 1885. Number 422072. Telegraphy, October 7, 1885. Number 437422. Telegraphy, October 7, 1885. Number 422073. Telegraphy, November 12, 1885. Number 422074. Telegraphy, November 24th, 1885. Number 435689. Telegraphy, November 30th, 1885. Number 438306. Telephone, Edison and Gilliland, December 22nd, 1885. Number 350235. Railway Telegraphy, Edison and Gilliland, December 28th, 1885. 1886. Number 406567. Telephone, January 28, 1886. Number 474232. Speaking Telegraph, February 17, 1886. Number 370132. Telegraphy, May 11, 1886. Number 411018. Manufacture of Incandescent Lamps, July 15, 1886. Number 438307. Manufacture of Incandescent Electric Lamps, July 15, 1886. Number 448779. Telegraph, July 15, 1886. Number 411019. Manufacture of Incandescent Electric Lamps, July 20th, 1886. Number 406130. Manufacture of Incandescent Electric Lamps, August 6, 1886. Number 351856. Incandescent Electric Lamp, September 30th, 1886. Number 454262, incandescent lamp filaments, October 26, 1886. Number 466400, cutout for incandescent lamps, Edison and J.F. Ott, October 26, 1886. Number 484184, manufacture of carbon filaments, October 26, 1886. Number 490954, manufacture of carbon filaments for electric lamps, November 2, 1886. Number 438308, system of electrical distribution, November 9, 1886. Number 524378, system of electrical distribution, November 9, 1886. Number 365978, system of electrical distribution, November 22, 1886. Number 369439, system of electrical distribution, November 22, 1886. Number 384830, railway signaling, Edison and Gilliland, November 24, 1886. Number 379944, commutator for dynamo electric machines, November 26, 1886. Number 411020, manufacture of carbon filaments, November 26, 1886. Number 485616, manufacture of carbon filaments, December 6, 1886. Number 485615, manufacture of carbon filaments, December 6, 1886. Number 525007, manufacture of carbon filaments, December 6, 1886. Number 369441, system of electrical distribution, December 10, 1886. Number 369442, system of electrical distribution, December 16, 1886. Number 369443, system of electrical distribution, December 16, 1886. Number 484185, manufacture of carbon filaments, December 20th, 1886. Number 534207, manufacture of carbon filaments, December 20th, 1886. Number 373584, dynamo electric machine, December 21st, 1886. 1887. Number 468949, converter system for electric railways, February 7th, 1887. Number 380100, pyromagnetic motor, May 24th, 1887. Number 476983, pyromagnetic generator, May 24th, 1887. Number 476530, incandescent electric lamp, June 1st, 1887. Number 377518, magnetic separator, June 30th, 1887. Number 470923, railway signaling, August 9th, 1887. Number 545405, system of electrical distribution, August 26, 1887. Number 380101, system of electrical distribution, September 13th, 1887. Number 380102, system of electrical distribution, September 14th, 1887. Number 470924, electric conductor, September 26, 1887. Number 563462, method of and apparatus for drawing wire, October 17, 1887. Number 385173, system of electrical distribution, November 5, 1887. Number 506215, making plate glass, November 9, 1887. Number 382414, burnishing attachments for phonographs, November 22, 1887. Number 386974, phonograph, November 22, 1887. Number 430570, phonogram blank, November 22, 1887. Number 382416, feed and return mechanism for phonographs, November 29, 1887. Number 382415, system of electrical distribution, December 4, 1887. Number 382462, phonogram blanks, December 5, 1887. 1888. Number 484582, duplicating phonograms, January 17, 1888. Number 434586, electric generator, January 21, 1888. Number 434587, thermoelectric battery, January 21, 1888. Number 382417, making phonogram blanks, January 30, 1888. Number 389369, incandescent electric lamp, February 2, 1888. Number 382418, phonogram blank, February 20th, 1888. Number 390462, making carbon filaments, February 20th, 1888. Number 394105, phonograph recorder, February 20th, 1888. Number 394106, phonograph reproducer, February 20th, 1888. Number 382419, duplicating phonograms, March 3rd, 1888. Number 425762, cutout for incandescent lamps, March 3rd, 1888. Number 396356, magnetic separator, March 19th, 1888. Number 393462, making phonogram blanks, April 28, 1888. Number 393463, machine for making phonogram blanks, April 28, 1888. Number 393464, machine for making phonogram blanks, April 28, 1888. Number 534208, induction converter, May 7th, 1888. Number 476991, method of and apparatus for separating ores, May 9th, 1888. Number 400646, phonograph recorder and reproducer, May 22nd, 1888. 488190, phonograph reproducer, May 22nd, 1888. Number 488189, phonograph, May 26, 1888. Number 470925, manufacture of filaments for incandescent electric lamps, June 21st, 1888. Number 393465, preparing phonograph recording surfaces, June 30th, 1888. Number 400647, phonograph, June 30th, 1888. Number 448780, device for turning off phonogram blanks, June 30th, 1888. Number 393466, phonograph recorder, July 14th, 1888. Number 393966, recording and reproducing sounds, July 14th, 1888. Number 393967, recording and reproducing sounds, July 14th, 1888. Number 430274, phonogram blank, July 14th, 1888. Number 437423, phonograph, July 14th, 1888. Number 450740, phonograph recorder, July 14th, 1888. Number 485617, incandescent lamp filament, July 14th, 1888. Number 448781, turning off device for phonographs, July 16th, 1888. Number 400648, phonogram blank, July 27th, 1888. Number 499879, phonograph, July 27th, 1888. Number 397705, winding field magnets, August 31st, 1888. Number 435690, making armatures for dynamo electric machines, August 31st, 1888. Number 430275, magnetic separator, September 12th, 1888. Number 474591, extracting gold from sulfide ores, September 12th, 1888. Number 397280, phonograph recorder and reproducer, September 19th, 1888. Number 397706, phonograph, September 29th, 1888. Number 400649, making phonogram blanks, September 29th, 1888. Number 400650, making phonogram blanks, October 15th, 1888. Number 406568, phonograph, October 15th, 1888. Number 437424, phonograph, October 15th, 1888. Number 393968, phonograph recorder, October 31st, 1888. 1889. Number 406569, phonogram blank, January 10th, 1889. Number 488191, phonogram blank, January 10th, 1889. Number 430276, phonograph, January 12th, 1889. Number 406570, phonograph, February 1st, 1889. Number 406571, treating phonogram blanks, February 1st, 1889. Number 406572, automatic determining device for phonographs, February 1st, 1889. Number 406573, automatic determining device for phonographs, February 1st, 1889. Number 406574, automatic determining device for phonographs, February 1st, 1889. Number 406575, automatic determining device for phonographs, February 1st, 1889. Number 406576, phonogram blank, February 1st, 1889. Number 430277, automatic determining device for phonographs, February 1st, 1889. Number 437425, phonograph recorder, February 1st, 1889. Number 414759, phonogram blanks, March 22nd, 1889. Number 414760, phonograph, March 22nd, 1889. Number 462540, incandescent electric lamps, March 22nd, 1889. Number 430278, phonograph, April 8th, 1889. Number 438309, insulating electrical conductors, April 25th, 1889. Number 423039, phonograph doll or other toys, June 15th, 1889. Number 426527, automatic determining device for phonographs, June 15th, 1889. Number 430279, voltaic battery, June 15th, 1889. Number 506216, apparatus for making glass, June 29th, 1889. Number 414761, phonogram blanks, July 16th, 1889. Number 430280, magnetic separator, July 20th, 1889. Number 437426, phonograph, July 20th, 1889. Number 465972, phonograph, November 14th, 1889. Number 443507, phonograph, December 11th, 1889. Number 513095, phonograph, December 11th, 1889. 1890. Number 434588, magnetic ore separator, Edison and W.K.L. Dixon, January 16th, 1890. Number 437427, making phonogram blanks, February 8th, 1890. Number 465250, extracting copper pyrites, February 18th, 1890. Number 434589, propelling mechanism for electric vehicles, February 18th, 1890. Number 438310, lamp base, April 25th, 1890. Number 437428, propelling device for electric cars, April 29th, 1890. Number 437429, phonogram blank, April 29th, 1890. Number 454941, phonograph recorder and reproducer, May 6, 1890. Number 436127, electric motor, May 17th, 1890. Number 484583, phonograph cutting tool, May 24th, 1890. Number 484584, phonograph reproducer, May 24th, 1890. Number 436970, apparatus for transmitting power, June 2nd, 1890. Number 453741, phonograph, July 5th, 1890. Number 456301, phonograph doll, July 5th, 1890. Number 484585, phonograph, July 5th, 1890. Number 456302, phonograph, August 4th, 1890. Number 476984, expansible pulley, August 9th, 1890. Number 493858, transmission of power, August 9th, 1890. Number 457343, magnetic belting, September 6th, 1890. Number 444530, leading in wires for incandescent electric lamps, reissued October 10th, 1905, number 12393. September 12th, 1890. Number 534209, incandescent electric lamp, September 13th, 1890. Number 476985, trolley for electric railways, October 27th, 1890. Number 500280, phonograph, October 27th, 1890. Number 541923, phonograph, October 27th, 1890. Number 457344, smoothing tool for phonogram blanks, November 17th, 1890. Number 460123, phonogram blank carrier, November 17th, 1890. Number 500281, Phonograph, November 17, 1890. Number 541924, Phonograph, November 17, 1890. Number 500282, Phonograph, December 1st, 1890. Number 575151, Phonograph, December 1st, 1890. Number 605667, Phonograph, December 1st, 1890. Number 610706, Phonograph, December 1st, 1890. Number 622843, Phonograph, December 1st, 1890. Number 609268, Phonograph, December 6, 1890. Number 493425, Electric Locomotive, December 20th, 1890. 1891. Number 476992, Incandescent Electric Lamp, January 20th, 1890. Number 470926, Dynamo Electric Machine or Motor, February 4th, 1890. Number 496191, Phonograph, February 4th, 1891. Number 476986, Means for Propelling Electric Cars, February 24th, 1891. Number 479987, Electric Locomotive, February 24th, 1891. Number 465973, Armatures for Dynamos or Motors, March 4th, 1891. Number 470927, Driving Mechanism for Cars, March 4th, 1891. Number 465970, Armature Connection for Motors or Generators, March 20th, 1891. Number 468950, Commutator Brush for Electric Motors and Dynamos, March 20th, 1891. Number 475491, Electric Locomotives, June 3rd, 1891. Number 475492, Electric Locomotives, June 3rd, 1891. Number 475493, Electric Locomotives, June 3rd, 1891. Number 475494, Electric Railway, June 3rd, 1891. Number 463251, Bricking Fine Ores, July 31st, 1891. Number 470928, Alternating Current Generator, July 31st, 1891. Number 476988, Lightning Arrestor, July 31st, 1891. Number 476989, Conductor for Electric Railways, July 31st, 1891. Number 476990, Electric Meter, July 31st, 1891. Number 476993, Electric Arc, July 31st, 1891. Number 484183, Electrical Depositing Meter, July 31st, 1891. Number 485840, Bricking Fine Iron Ores, July 31st, 1891. Number 493426, Apparatus for Exhibiting Photographs of Moving Objects, July 31st, 1891. Number 509518, Electric Railway, July 31st, 1891. Number 589168, Kinetograph Camera, reissued September 30th, 1902, numbered 12037 and 12038, and January 12th, 1904, numbered 12192. July 31st, 1891. Number 470929, Magnetic Separator, August 28th, 1891. Number 471268, Ore Conveyor and Method of Arranging Ore Thereon, August 28th, 1891. Number 472288, Dustproof Bearings for Shafts, August 28th, 1891. Number 472752, Dustproof Journal Bearings, August 28th, 1891. Number 472753, Ore Screening Apparatus, August 28th, 1891. Number 474592, Ore Conveying Apparatus, August 28th, 1891. Number 474593, Dustproof Swivel Shaft Bearing, August 28th, 1891. Number 498385, Rollers for Ore Crushing or Other Material, August 28th, 1891. Number 470930, Dynamo Electric Machine, August 8, 1891. Number 476532, Ore Screening Apparatus, October 8, 1891. Number 491992, cutout for incandescent electric lamps, November 10th, 1891. 1892. Number 491993, stop device, April 5th, 1892. Number 564423, separating ores, June 2nd, 1892. Number 485482, magnetic ore separation, July 9th, 1892. Number 485841, mechanically separating ores, July 9th, 1892. Number 513096, method of and apparatus for mixing materials, August 24th, 1892. 1893. Number 509428, composition brick and making same, March 15th, 1893. Number 513097, phonograph, May 22nd, 1893. Number 567187, crushing rolls, December 13th, 1893. Number 602064, conveyor, December 13th, 1893. Number 534206, filament for incandescent lamps, December 15th, 1893. 1896. Number 865367, fluorescent electric lamp, May 16th, 1896. 1897. Number 604740, governor for motors, January 25th, 1897. Number 607588, phonograph, January 25th, 1897. Number 637327, rolls, May 14th, 1897. Number 672616, breaking rock, May 14th, 1897. Number 675056, magnetic separator, May 14th, 1897. Number 676618, magnetic separator, May 14th, 1897. Number 605475, drying apparatus, June 10th, 1897. Number 605668, mixer, June 10th, 1897. Number 667201, flight conveyor, June 10th, 1897. Number 671314, lubricating journal bearings, June 10th, 1897. Number 671315, conveyor, June 10th, 1897. Number 675057, screening pulverized material, June 10th, 1897. 1898. Number 713209, duplicating phonograms, February 21st, 1898. Number 703774, reproducer for phonographs, March 21st, 1898. Number 626460, filament for incandescent lamps and manufacturing same, March 29th, 1898. Number 648933, dryer, April 11th, 1898. Number 661238, machine for forming pulverized material in briquettes, April 11th, 1898. Number 674057, crushing rolls, April 11th, 1898. Number 703562, apparatus for bricking pulverized material, April 11th, 1898. Number 704010, apparatus for concentrating magnetic iron ores, April 11th, 1898. Number 659389, electric meter, September 19th, 1898. 1899. Number 648934, screening or sizing very fine materials, February 6, 1899. Number 663015, electric meter, February 6, 1899. Number 688610, phonograph recording apparatus, February 10, 1899. Number 643764, reheating compressed air for industrial purposes, February 24, 1899. Number 660293, electric meter, March 23, 1899. Number 641281, expanding pulley, Edison and Johnson, March 28, 1899. Number 727116, grinding rolls, June 15, 1899. Number 652457, phonograph, reissued September 25, 1900, numbered 11857, September 12, 1899. Number 648935, apparatus for duplicating phonograph records, October 27, 1899. Number 685911, apparatus for reheating compressed air for industrial purposes, November 24th, 1899. Number 657922, apparatus for reheating compressed air for industrial purposes, December 9th, 1899. 1900. Number 676840, magnetic separating apparatus, January 3rd, 1900. Number 660845, apparatus for sampling, averaging, mixing, and storing materials in bulk, January 9th, 1900. Number 662063, process of sampling, averaging, mixing, and storing materials in bulk, January 9th, 1900. Number 679500, apparatus for screening fine materials, January 24th, 1900. Number 671316, apparatus for screening fine materials, February 23rd, 1900. Number 671317, apparatus for screening fine materials, March 28th, 1900. Number 759356, burning Portland cement, clinker, etc., April 10th, 1900. Number 759357, apparatus for burning Portland cement, clinker, etc., April 10th, 1900. Number 655480, phonograph reproducing device, April 30th, 1900. Number 657527, making metallic phonograph records, April 30th, 1900. Number 667202, duplicating phonograph records, April 30th, 1900. Number 667662, duplicating phonograph records, April 30th, 1900. Number 713863, coding phonograph records, May 15th, 1900. Number 676841, magnetic separating apparatus, June 11th, 1900. Number 759358, magnetic separating apparatus, June 11th, 1900. Number 680520, phonograph records, July 23rd, 1900. Number 672617, apparatus for breaking rock, August 1st, 1900. Number 676225, phonographic recording apparatus, August 10th, 1900. Number 703051, electric meter, September 28th, 1900. Number 684204, reversible galvanic battery, October 15th, 1900. Number 871214, reversible galvanic battery, October 15th, 1900. Number 704303, reversible galvanic battery, December 22nd, 1900. 1901. Number 700136, reversible galvanic battery, February 18th, 1901. Number 700137, reversible galvanic battery, February 23rd, 1901. Number 704304, reversible galvanic battery, February 23rd, 1901. Number 704305, reversible galvanic battery, May 10th, 1901. Number 678722, reversible galvanic battery, June 17th, 1901. Number 684205, reversible galvanic battery, June 17th, 1901. Number 692507, reversible galvanic battery, June 17th, 1901. Number 701804, reversible galvanic battery, June 17th, 1901. Number 704306, reversible galvanic battery, June 17th, 1901. Number 705829, reproducer for sound records, October 24th, 1901. Number 831606, sound recording apparatus, October 24th, 1901. Number 827089, calcining furnaces, December 24th, 1901. 1902. Number 734522, process of nickel plating, February 11th, 1902. Number 727117, reversible galvanic battery, September 29th, 1902. Number 727118, manufacturing electrolytically active, finely divided iron, October 13th, 1902. Number 721682, reversible galvanic battery, November 13th, 1902. Number 721870, funnel for filling storage battery jars, November 13th, 1902. Number 723449, electrode for storage batteries, November 13th, 1902. Number 723450, reversible galvanic battery, November 13th, 1902. Number 754755, compressing dies, November 13th, 1902. Number 754858, storage battery tray, November 13, 1902. Number 754859, reversible galvanic battery, November 13th, 1902. Number 764183, separating mechanically entrained globules from gases, November 13th, 1902. Number 802631, apparatus for burning Portland cement clinker, November 13th, 1902. Number 852424, secondary batteries, November 13th, 1902. Number 722502, handling cable-drawn cars on inclines, December 18th, 1902. Number 724089, operating motors in dust-laden atmospheres, December 18th, 1902. Number 750102, electrical automobile, December 18th, 1902. Number 758432, stockhouse conveyor, December 18th, 1902. Number 873219, feed regulators for grinding machines, December 18th, 1902. Number 832046, automatic weighing and mixing apparatus, December 18th, 1902. 1903. Number 772647, photographic film for moving picture machine, January 13th, 1903. Number 841677, apparatus for separating and grinding fine materials, January 22nd, 1903. Number 790351, duplicating phonograph records, January 30th, 1903. Number 831269, storage battery electrode plate, January 30th, 1903. Number 775965, dry separator, April 27th, 1903. Number 754756, process of treating ores from magnetic gangue, May 25th, 1903. Number 775600, rotary cement kilns, July 20th, 1903. Number 767216, apparatus for vacuously depositing metals, July 30th, 1903. Number 796629, lamp guard, July 30th, 1903. Number 772648, vehicle wheel, August 25th, 1903. Number 850912, making articles by electroplating, October 3rd, 1903. Number 857041, can or receptacle for storage batteries, October 3rd, 1903. Number 766815, primary battery, November 16th, 1903. Number 943664, sound recording apparatus, November 16th, 1903. Number 873220, reversible galvanic battery, November 20th, 1903. Number 898633, filling apparatus for storage battery jars, December 8th, 1903. 1904. Number 767554, rendering storage battery gases non-explosive, June 8th, 1904. Number 861241, Portland cement and manufacturing same, June 20th, 1904. Number 800800, phonograph records and making same, June 24th, 1904. Number 821622, cleaning metallic surfaces, June 24th, 1904. Number 879612, alkaline storage batteries, June 24th, 1909. Number 880484, process of producing very thin sheet metal, June 24th, 1904. Number 827297, alkaline batteries, July 12th, 1904. Number 797845, sheet metal for perforated pockets of storage batteries, July 12th, 1904. Number 847746, electrical welding apparatus, July 12th, 1904. Number 821032, storage battery, August 10th, 1904. Number 861242, can or receptacle for storage battery, August 10th, 1904. Number 970615, methods and apparatus for making sound records, August 23rd, 1904. Number 817162, treating alkaline storage batteries, September 26, 1904. Number 948542, method of treating cans of alkaline storage batteries, September 28, 1904. Number 813490, cement kiln, October 29, 1904. Number 821625, treating alkaline storage batteries, October 29, 1904. Number 821623, storage battery filling apparatus, November 1, 1904. Number 821624, gas separator for storage battery, October 29, 1904. 1905. Number 879859, apparatus for producing very thin sheet metal, February 16, 1905. Number 804799, apparatus for perforating sheet metal, March 17, 1905. Number 870024, apparatus for producing perforated strips, March 23, 1905. Number 882144, secondary battery electrodes, March 29, 1905. Number 821626, process of making metallic films or flakes, March 29, 1905. Number 821627, making metallic flakes or scales, March 29, 1905. Number 827717, making composite metal, March 29, 1905. Number 839371, coating active material with flake-like conducting material, March 29, 1905. Number 854200, making storage battery electrodes, March 29, 1905. Number 857929, storage battery electrodes, March 29, 1905. Number 860195, storage battery electrodes, April 26, 1905. Number 862145, process of making seamless tubular pockets or receptacles for storage battery electrodes, April 26, 1905. Number 839372, phonograph records or blanks, April 28, 1905. Number 813491, pocket filling machine, May 15, 1905. Number 821628, making conducting films, May 20th, 1905. Number 943663, horns for talking machines, May 20th, 1905. Number 950226, phonograph recording apparatus, May 20th, 1905. Number 785297, gas separator for storage batteries, July 18th, 1905. Number 950227, apparatus for making metallic films or flakes, October 10th, 1905. Number 936433, tube filling and tamping machine, October 12th, 1905. Number 967178, tube forming machines, Edison and John F. Ott, October 16th, 1905. Number 880978, electrode elements for storage batteries, October 31st, 1905. Number 880979, method of making storage battery electrodes, October 31st, 1905. Number 850913, secondary batteries, December 6, 1905. Number 914342, storage battery, December 6, 1905. 1906. Number 858862, primary and secondary batteries, January 9th, 1906. Number 850881, composite metal, January 19th, 1906. Number 964096, process of electroplating, February 24th, 1906. Number 914372, making thin metallic flakes, July 13th, 1906. Number 962822, crushing rolls, September 4th, 1906. Number 923633, shaft coupling, September 11th, 1906. Number 962823, crushing rolls, September 11th, 1906. Number 930946, apparatus for burning Portland cement, October 22nd, 1906. Number 898404, making articles by electroplating, November 2nd, 1906. Number 930948, apparatus for burning Portland cement, November 16, 1906. Number 930949, apparatus for burning Portland cement, November 26, 1906. Number 890625, apparatus for grinding coal, November 23, 1906. Number 948558, storage battery electrodes, November 28, 1906. Number 964221, sound records, December 28, 1906. 1907. Number 865688, making metallic films or flakes, January 11, 1907. Number 936267, feed mechanism for photographs and other machines, January 11, 1907. Number 936525, making metallic films or flakes, January 17, 1907. Number 865687, making nickel films, January 18, 1907. Number 939817, cement kiln, February 8, 1907. Number 855562, diaphragm for talking machines, February 23, 1907. Number 939992, phonographic recording and reproducing machine, February 25, 1907. Number 941630, process and apparatus for artificially aging or seasoning Portland cement, February 25, 1907. Number 876445, electrolyte for alkaline storage batteries, May 8, 1907. Number 861819, discharging apparatus for belt conveyors, June 11, 1907. Number 954789, sprocket chain drives, June 11, 1907. Number 909877, telegraphy, June 18, 1907. 1908. Number 896811, metallic film for use with storage batteries and process, February 4, 1908. Number 940635, electrode element for storage batteries, February 4, 1908. Number 909167, waterproofing paint for Portland cement buildings, February 4, 1908. Number 896812, storage batteries, March 13, 1908. Number 944481, process and apparatus for artificially aging or seasoning Portland cement, March 13, 1908. Number 947806, automobiles, March 13, 1908. Number 909168, waterproofing fibers and fabrics, May 27, 1908. Number 909169, waterproofing paint for Portland cement structures, May 27, 1908. Number 970616, flying machines, August 20th, 1908. 1909. Number 930947, gas purifier, February 15th, 1909. Number 40527, design patent for phonograph cabinet, September 13th, 1909. Foreign patents. In addition to the United States patents issued to Edison as above enumerated, there have been granted to him, up to October 1910, by foreign governments 1,239 patents as follows. Argentine, 1. Australia, 6. Austria, 101. Belgium, 88. Brazil, 1. Canada, 129. Cape of Good Hope, 5. Ceylon, 4. Cuba, 12. Denmark, 9. France, 111. Germany, 130. Great Britain, 131. Hungary, 30. India, 44. Italy, 83. Japan, 5. Mexico, 14. Natal, 5. New South Wales, 38. New Zealand, 31. Norway, 16. Orange Free State, 2. Portugal, 10. Queensland, 29. Russia, 17. South African Republic, 4. South Australia, 1. Spain, 54. Sweden, 61. Switzerland, 13. Tasmania, 8. Victoria, 42. West Australia, 4. Total of Edison's foreign patents, 1,239. End of section 51.
Appendix, Foreign Patents, from Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix, Foreign Patents. In addition to the United States patents issued to Edison as above enumerated, there have been granted to him up to October 1910 by foreign governments 1,239 patents as follows. Argentine, 1. Australia, 6. Austria, 101. Belgium, 88. Brazil, 1. Canada, 129. Cape of Good Hope, 5. Ceylon, 4. Cuba, 12. Denmark, 9. France, 111. Germany, 130. Great Britain, 131. Hungary, 30. India, 44. Italy, 83. Japan, 5. Mexico, 14. Natal, 5. New South Wales, 38. New Zealand, 31. Norway, 16. Orange Free State, 2. Portugal, 10. Queensland, 29. Russia, 17. South African Republic, 4. South Australia, 1. Spain, 54. Sweden, 61. Switzerland, 13. Tasmania, 8. Victoria, 42. West Australia, 4. Total of Edison's foreign patents, 1,239. End of Appendix, Foreign Patents. End of Edison, His Life and Inventions, by Frank Lewis Dyer and Thomas Comerford Martin.